Hey guys, here I welcome you to our brand new course, Algorithm Design Techniques, Live Problem Solving in Java. Algorithms are everywhere. One great algorithm applied sensibly can result into a system like Google. Larry Page, founder of Google, designed PageRank algorithm that is behind the search in Google. That's why when we search on Google, we generally find the most relevant result on the first page itself. So, every computer programmer should learn how to design algorithms which are not only correct but also efficient in terms of time and space. Computer scientists have worked from hundreds of years and derived some of the techniques that can be applied to write and design algorithms. So, why to reinvent the wheel? Let's go through some of the most famous algorithm design techniques in this course. Once you will come to know these design techniques, it will become very easy for you to approach a problem by identifying which technique to apply to solve that correctly and efficiently. We will start this course with some measurement techniques in algorithms called complexity analysis so that we can measure the time and space in an algorithm when we design that algorithm. Then we will start understanding recursion and we will deep dive into that. Recursion is the base of any algorithm design because most of the algorithms has to be solved using recursion. Recursion is executed in computers in a very special way using stack frames, and we will understand all that. There are many types of recursion and we will have a look into that. We will solve some classic problems like Tower of Hanoi, binary subtree to understand recursion deeply. And we will write the code line by line in Java to make it very easy to understand and code. Then we will move into another design technique, backtracking. Backtracking algorithms are enhanced recursion where we can revert our decision from inside a recursion. We will understand how to identify and approach these kind of problems. Also, we will solve some classical problems, rat and maze and queen's problem, knight's tour problem, and code them line by line. Then we will move to the next section, divide and conquer. After that, greedy algorithms, and we will take the same approach to understand, identify, and solve these problems and code some classic problems. Then there will be a very important section, dynamic programming. That is not only important for algorithm design but also for interviews. This is a very favorite paradigm for interviewer to ask questions from. So we will solve a lot of problems in this section along with code. And we will understand how to approach these kind of problems. All in all. So by the end of this course, you will understand how to design algorithms, a lot of coding practice, and design live problems in Java, algorithm complexity analysis, and if you are preparing for coding interviews or doing competitive programming, this course will be a big help for you. So I think this is enough to create the thrill. I welcome you to the course and I'm sure that this will be fun. But if it is not, it comes with a 30 days money back guarantee. So don't think twice to give it a shot. So see you guys in the course. Hey guys, I'm very happy to welcome you to this course. In this lecture, we're gonna get familiar with algorithms. So you may be familiar with usual Googled definitions. For example, algorithm is a process or a set of rules to be followed in calculations or other problem solving operations, especially by the computer. With that, the term algorithm might sound technical, but actually it can be defined as a set of instructions to perform anything, to perform any task. For instance, the non-technical example of algorithm would be something like a recipe that gives you a set of instructions on how to put together several ingredients and get a product, for example, a cake. Similarly, if we put it technically, algorithm is a set of instructions that enable a computer to put together different sources of information and generate a result or generate a solution to a problem. So yes, algorithm is indeed step-by-step, unambiguous instructions to solve the given problem or to solve the given task. Now, why would we need any algorithm to perform any task or to solve any problem? Why there are billions of algorithms in large systems and what exactly are they doing? We need these lists of instructions or algorithms because in this growing tech world, we have to deal with a lot of data. That data could be anything. Data could be a list of highways in USA. It could be number of tweets. And dealing with this data may consist of tasks like to figure out which highway can get you to your destination and which tweet is going to show up at the top of the list. So basically data goes in, goes through instruction, result comes out. Algorithms are used everywhere, from a dating app where you meet people based on your interest to a large criminal justice system. Algorithm is not language specific. It is just a set of instructions that you have to code in a language to make your computer understand. Let's take a small set of instructions as an example. Let's add two numbers. Step 1, where we start. Next step is to declare variables for number 1, number 2 and for sum. So these are the variables num1, num2 and sum. Step 3 is to read values num1 and num2, and step 4 will be to add number 1 and number 2, then assign the result to the sum. Next step is to display the result sum and then end. Again, algorithm is a step-by-step procedure for solving problem or completing any task. It always has a definite start and desired end. Note that even to perform a task or to solve one problem, algorithms may differ as per different needs. That is, for a single problem, there can be multiple solutions or there can be different algorithms. The important point is it should be correct. That is, it should solve the given problem and it should be efficient. Here we identify how much resources in terms of time and memory or space does it takes to execute. Hey guys, welcome back. So let's start with our very first section of the course, complexity analysis of algorithms. There are two critical things when we think of designing algorithms. First is the correctness of the expected output, and the second is time taken on various input sizes. The whole idea of this course is to make you aware of various design techniques of algorithms from these two perspectives. So in this section, we will discuss complexity analysis in terms of time taken by an algorithm to execute, ignoring all the computer hardware factors. First, we will discuss the various notations and then the techniques to analyze the algorithm runtime. Our focus mainly will remain on big O notation for worst time complexity, means time taken by an algorithm in worst case scenario. So big O is widely accepted notation in the industry to analyze the algorithm. So let's start the section from next lecture and try analyzing pieces of code and blocks. So see you guys in next lecture. Hey guys, welcome back. This lecture is on complexity analysis. It's very crucial to know about how to analyze the complexity of any algorithm. And here, the complexity is concerned about how fast or slow a particular algorithm or a piece of code performs. So in previous lecture, we were discussing that a problem may have more than one solutions. Question is, are they all equally good and efficient as each other? Answer is no. So what makes a solution better than others? Well, obviously, it's the efficiency or the performance of the algorithm. And we judge performance of any algorithm with complexity analysis. There are two kinds of complexities that we do care about: time complexity and space complexity. Time complexity, where we check how fast the algorithm runs, and the space complexity is about how much space or memory the algorithm uses up. We will discuss these in detail later. For now, just remember, algorithm having better complexity is a better solution. Though some algorithms may have better time complexity but are not good in case of space complexity, or vice versa. It just depends on the problem or the situation that how you want your code to work. Now let's see, how do we calculate complexity. In case of time complexity, we check how fast our algorithm can execute. But how can we express it? In seconds? In milliseconds? Well, if you try to compare them with time, you may find a single algorithm taking slightly different time at every execution, as there may be a lot of stuff going on in our system that may affect the execution time. Because there can be multiple factors affecting the execution time. For example, the execution time depends on how fast the code or algorithm fetches data from cache or main memory while getting processed. It depends on how many processes or tasks are running at the same time, etc. Other than these system-specific dependencies, the runtime for any algorithm also depends on the fact that how much data it is going to process, that is on the size of input data. For instance, think of a case: you have an array of size 10 and your function returns the sum of its elements. Maybe for that it's gonna take few nanoseconds or something. It will be quick even for 100 or 1000 elements, but it won't be that quick in case of 10,000 or a million or a billion elements. So the most important factor that affects the execution time is input size. And here we got that time complexity is not just about how fast your algorithm is, it actually cares about how fast the algorithm runs when the size of input increases. Now if you go ahead and start measuring it with some time unit like seconds or milliseconds, then it would be senseless. It is senseless to say that for this particular size of input, the algorithm is taking 5 seconds, 5 milliseconds, 10 milliseconds, or a second. We cannot say that. So to actually define it, there is more reasonable way. We won't measure time complexity in seconds. Instead of doing that, we will measure the change of speed of the function as the input size increase. And here in this function, sum, it's going through every element. So increasing the size of input array will affect the execution time linearly. So the complexity here we represent by writing ON. We symbolize the complexity using notations, and this O here stands for big O notation. If we draw it in a graph, where at x-axis we are having number of inputs and at y it's the number of operations, then the result will be like this. So it shows the linear relationship between the both. For n number of inputs, system has to perform n elementary operations. So the unit we use to analyze the complexity is the number of elementary operations in case of time complexity and number of memory slots that our algorithm is going to use in case of space complexity. Now let me sum up things that we discussed till now and let me clear this more to you. In order to analyze complexity of any algorithm, we actually analyze the behavior of function as input of the function increases and tends toward a value like infinity. And that's called asymptotic analysis, where in analyzing space-time complexity, we actually care about the growth of time or space taken by the algorithm with respect to the input we pass to it. We'll mostly discuss about time complexity throughout the course, but the space complexity is equally important and is calculated in same way. Now in computer science, we mostly use big O notation to represent the complexity because it calculates the complexity in worst case scenario. That is, we analyze functions behavior in worst case. Like what's the worst complexity this algorithm may have. So we think of the worst situation that is possible for that algorithm. For example, in an array, you need to search a particular element. For that, you need to traverse through the array. You need to check each element. Here, the best case is that we may find the element at the very beginning of the array. And average case is when we find it somewhere like in the middle. And the worst case is where we find the element at the end. So we calculate complexity for the worst case. Other than that, there are notations like theta, omega, and many more that are used to define complexity but are not accurate and useful. So we use big O notations. So by now, I hope you have better idea of what complexity analysis is about and what unit and notations we use to measure the complexities of any algorithm. So that's all about this lecture. Let's move forward and see how we can calculate complexities for algorithm and what are the basic and most used complexity values in detail. So guys, see you there in the next lecture. Hey guys, welcome back. In last lecture, we had an overview about how we measure complexity of an algorithm. In this lecture, we'll see some basic complexity values that we mostly use to show complexities in different cases. Let's look into these common growth rates. We'll move from the most performant to the worst one. And the first one is constant time. Constant time means a function or an algorithm will always work in the same way, irrespective of input. For example, if your function is adding 3 to the first element of this array, it will be executed in constant time. In this, we are accessing the array element on the specified index and then adding 3 to it. Now it doesn't matter of what the size of the input or the size of the array is. If it will be 1,000, million, or billion in size, it won't affect the execution time of the function. It will anyways be constant. Why? Because we don't have to iterate through the array to get to that index. We already know the index and we're just getting the value from that index and then adding 3 to it. If we show it in a graph for any value n, the elementary operation will be constant. So it will be just a straight line. One thing to notice here is that the 1 in O1 is not the exact number of elementary operations. You might think accessing an element includes 4 elementary operations as an int takes 4 slots in the memory to get stored. And adding it to another integer again is another operation. It should be a number like 08 or something. But it is not like that. We don't care about how many operations it's gonna perform. Instead, we compare the performance with growth of input, and since O1, O2, O3 and so on doesn't have any relation with the size of input, so we write it like O1. Every operation which is not depending on input is considered a constant time operation. Like addition, multiplication, accessing any data, returning result, these all are constant time operations. Next is logarithmic complexity. Logarithmic or log n complexity is also very powerful. However, the best one is constant time complexity because constant time complexity does not vary if input changes or input increases. This logarithmic complexity is also good because it does not increase as fast as the input increase. Let's look into it. If we know about logs, log of any number x with base b is equal to y. This implies that b to the power y will be x. Yes, I know we are getting into maths now, and that's why most of the people are always scared of logarithmic complexity and don't really know what it means and how it works in complexity analysis. But trust me, once we get the maths and concept behind this, we'll understand logarithmic complexity a bit easily. So this is what log actually means. The base p here is important, like log base 10 of 10, and log base 3 of 10 will be having different value for sure. Generally in mathematics, if you remember, we work with base 10 mostly. But in complexity analysis or even in computer science, we take binary log, that is base 2. As our system works on binary representation of data, it stores data in form of 0, 1 in memory, so computer works on binary log. That means log n is equals to y implies that 2 raised to power y is equals to n because the base is 2 here. And that means log 4 would be 2 because 4 is 2 raised to power 2. Log 8 will be 3 because 8 is 2 raised to power 3. And log 16 will be 4 because it's 2 raised to power 4. So look at the growth in n here. We are doubling n, but binary log of these is increasing by just a tiny amount. This is increasing by tiny amount, which is 1, as we are having 2, 3, and 4 here. So if we tie this back to complexity analysis, if your algorithm is having log n complexity, that means your number of operations or number of memory slots used by the algorithm increases with just a tiny amount even when you are doubling the input size, which is incredible. Now look at this graph. Initially it increases a bit faster, but as the input increases, it just increases with tiny amount. And at very larger values, it will be almost like constant. It is indeed what we really wanted. For instance, input is 10, then number of operations will be 3. If the input is increased to 100, the number of operations will be 7. And then if the number of input size grows to 1000, the operations will only be 10. So for a million input size, see the difference? There you see only 20 operations are required. And for a billion, only 30. So you see the difference in number of operations with respect to the increase in input. It is going towards being constant. Let's take an example. Suppose you're having an array and your function is working like at every step it is eliminating half of the array. For such algorithm, if your array size is 4, it will take 2 steps to execute. So it will be log 4, which is 2 steps. And now if you double your input size, then it will just take 1 extra step to cut it in half. And the total steps would be log 8, which is 3 steps. So function having log n complexity are very performant. However, I'm again reminding you that best one is constant time complexity, but next comes this logarithmic complexity. Another perfect example to logarithmic is binary search implementation, where at every step we deal with half of the tree nodes. Now let's move to next complexity, which is linear time complexity. In this, runtime taken by function increases in linear manner as the number of input increases. We do write such code often that has linear complexity, like using any loop. It can be a for loop, it can be a while loop. For example, iterating over an array. This will include n time iteration through the array. For input size 10, 100, even for 1000 it's still decent because 10 At 10, it will perform 10 operation. At 100, it will perform 100 operation. At 1000, it will perform 1000 operation. But at input size like a million or a billion, it will definitely get slow and will take more time. So the algorithms having O(n) complexity are quite good and acceptable, but yes, at larger input size, they're not much performant. That you can see in this graph, it increases as n increases. So this was linear time complexity. Now complexities after this are a bit horrible. Next we have quadratic time complexity. It is, as you can see, is O(n) square. So in this type of complexity, the performance of function is directly proportional to the squared size of input data. For example, whenever we are writing a loop inside a loop, this complexity will occur. Like if you are given an array of size 10, you need to find the duplicate in this array. For this, a nice solution will be something like iterating through the array and iterating again. Compare the outer iteration element to inners, and if both are equal, you get the element, you end both the loops. So for 10 elements, it will perform 100 elementary operations, and for 100, it will perform 10,000. So it is just squaring the value, thus taking n square iterations. So if your input size is 1000, then iteration will be 1 million, which is not acceptable. So this is O(n) square complexity. Its graph grows like this. There are also O(n) cube, O(n)4, these kind of complexity. That means more and more nested loops in your function. That slows down execution even more. Even worse than this, we have exponential and factorial complexities. Exponential complexity is 2 raised to power n. That means number of operations increases exponentially as you increase number of inputs. For example, whenever we implement loop inside recursion, where function calls itself, so in that case, it increases exponentially. Yeah, terrible. And worse than this is factorial, which is n multiplied by n minus 1, n minus 2. It goes on until value of n becomes 0. So like we have recursion inside a loop for n minus 1 times, we get such terrible performance. So these were the most used complexities that we come across while coding and writing algorithms. Now while solving any problem, you might get the case where our algorithm is having complexity mix of these values, like iterating through any array in forward and backward direction, that will be 2n, and performing some constant operation along with that, which will be O(1). Now to solve this, we don't need to take these constant values 2 and 1, as O(n) is much bigger than these, so it will not affect the overall complexity of the algorithm that much. So we will be having O(n) in this case. Similarly, if you have complexity like O(n) square plus O(n), then you can eliminate the O(n) here, because at larger values of n, O(n) will be nothing as compared to O(n) square. And in equations like this, we are having O(n) raised to power 4 O(n) square plus O log n. This can be written as O(n) raised to power 4 plus n square plus log n. So here log n and even n square can be eliminated, because with larger input size, the value of n raised to power 4 is much larger compared to log n and n square. So from asymptotic analysis point of view, this complexity can be written as O(n) raised to power 4. Another important thing to mention here is that suppose you have more than one type of inputs and your algorithm is having complexity like O(n) square plus O(m), or something like O(n) raised to power 4 plus O log m. As both of inputs are different and cannot be compared and eliminated, in these cases the complexity will be on squared plus m and on raised to power 4 plus log m. Alright, so that was all about this lecture. Hope you have a better idea of complexity analysis, the key complexity values, and how we can calculate complexity of any algorithm. Complexity analysis was the fundamental concept that you must need to know before actually learning the techniques to write algorithms. Because you should know what solution or which solution is better and efficient to execute. It's actually quite simple if you think whatever problem you are solving, your solution should be efficient on larger inputs because with time, data increases gigantically. And our solution should be decent enough to handle that. Therefore, having a good knowledge of complexity is mandatory. From next lecture, we will start discussing on basic algorithm design techniques. So see you guys there in the next lecture. Hey guys, welcome back. So let's sum up what we have learned so far in this section about complexity analysis. First, we understood why to analyze complexity of any algorithm and what are the important factors to be included in doing so. We understood that we ignored the optimizations available at compiler or CPU level and we just focus on how much CPU we are burning when we ignore these self-performing optimizations completely. Then we had a deep look at big O notation and we tried to explain you in a way so that a non-mathematical background student can also understand this. We had a check on O1, that is constant complexity, logarithmic complexity log n, linear time complexity n, quadratic complexity, exponential complexity, and factorial complexity, along with the pseudocode. I think after this section, you will be able to analyze complexity along with us of the algorithms we're going to design in this course. So this was it for this part of the course. See you guys in the next. Hey guys, welcome back. This section is about recurrence relation. Recurrence relation is not an algorithm, but it is quite important topic. It is having mathematical touch, but don't worry, we will try to make you understand this in simplest way possible. So in this section, first we will see what is recurrence relation, why it is important to know recurrence relation, then how to solve the recurrence relation, and then how to solve this recurrence relation using Master's theorem. So let's start from next lecture onwards. Hey guys, welcome back. In this lecture, we're going to talk about a fundamental tool in analysis of algorithms, and it is recurrence relation. This is kind of mathematical topic, but extremely useful in complexity analysis. But we will try to keep it very simple so that if you just know some basic mathematics, you will be able to understand it. So don't get scared. So what is recurrence relation? And why we are going to understand it at this point in time. Let's first know what recurrence relation is. A recurrence relation for the sequence A0, A1, A2 going all the way to AN is an equation that relates AN to certain of its predecessors A0, A1, A2 going all the way to AN minus 1. Sounds so mathematical? Let's exemplify it. So simplest example we can take here is a factorial. Factorial of any number n we all know is fn equals to n multiplied by fn minus 1, or you can say factorial of n equals to n multiplied by factorial of n minus 1. You see here we have defined this relation of fn or the relation of n with its predecessor, which is n minus 1. So this is recurrence relation. Let's take another example of Fibonacci sequence. Fibonacci series is a series of numbers such that each number is sum of two preceding ones. So how do we calculate the nth Fibonacci number? Like this, Fib of n is equals to fib of n minus 1 plus fib of n minus 2. That is the sum of two preceding numbers. As each number is sum of two preceding numbers in Fibonacci series. Again, we have to find the relation of n with its predecessors. So this is again a recurrence relation with some initial conditions f0 equals to 0 and f1 equals to 1. Or you can say fib of 0 is 0 and fib of 1 is 1. This is always true. And in case of factorial, the initial conditions are value of factorial 0 and the value of factorial 1 is 1. So clearly the recursive algorithm for calculating the nth Fibonacci number and calculating the factorial of a number n uses this relation to solve the problem. Without this relation, there is no recursion. So whenever we are going to write a recursive solution to a problem, we first need to know the recurrence relation. And the initial conditions of recurrence relations are generally the base case in the recursive algorithm. So the first important thing about the recurrence relation we just saw is that recursive algorithm is an implementation of recurrence relation. Recursion is base of many algorithm design techniques. Whenever we are able to find the recurrence relation, we can fit in the recursive part in those algorithms, as well as in pure recursive algorithm. Now, another big thing about recurrence relation is about finding out the complexities of such algorithms. Recurrence relation can also be used to know the complexity of those recursive steps used in the algorithm. For example, if we want to find out the time complexity of the algorithm to find out a factorial of a number n, you know the recurrence relation. Write the recurrence relation. Now write it in terms of time consumed or write it in terms of t. So convert fn to tn and write tn minus 1 at the place of fn minus 1. Right. Now multiplied by n is a constant operation. So we directly write its part of complexity. Multiplication is constant time operation, so let's write 1 unit for it. So this is the recurrence relation. Tn equals to Tn minus 1 plus 1 unit for multiplication. However, there is one more unit for n minus 1 subtraction that we have with Tn minus 1 term. So total of 2 units along with Tn minus 1 calculation. But we'll go with 1 as both 1 and 2 are constants and it is not going to make any impact. So this relation is also a recurrence relation. But it is the recurrence relation to get time complexity of getting the nth factorial. It is not the one to calculate the factorial itself. So this is the time consumed by the algorithm to find the factorial of any number n. But to get the actual value of time complexity, we need to solve this equation. And that we are going to see in next lecture. Hey guys, welcome back. In this lecture, let's see how we can solve the recurrence relation to get the time complexity. So this is the time consumed to calculate the nth factorial by an algorithm, which is Tn, and it is equal to Tn minus 1 plus 1. So this is the recurrence relation we are having. But actually, by seeing this equation, I cannot tell the actual complexity. And I know you can't either. We need to get it in terms of big O notation. Basically, we need to solve this equation to get the time complexity in big O. So now let's go ahead and jump into learning how to solve this recurrence relation. The most common way to solve this equation is using the substitution method. In this method, you just keep replacing the values for the preceding terms up to a very few steps to know the exact pattern. And from that pattern, we get a generalized equation which gets solved very easily. So let's try this. Here in this equation, we need to find out the value of Tn minus 1 so that we can put it here in this equation. So let's get the value of Tn minus 1, which we can get by replacing n with n minus 1 in this equation. So when we do this, we get Tn minus 1 equals to Tn minus 1 minus 1 plus 1. And this results to the equation Tn minus 1 equals to Tn minus 2 plus 1. Now again here, we are going to write the equation for Tn minus 2. That again we can get by replacing n with n minus 2 in the first equation. And when we do so, we get Tn minus 2 equals to Tn minus 3 plus 1. So these are the three equations. We don't need to find out more. Now we're going to start substituting the values. Take the equation 1 and substitute the value of Tn minus 1 from equation 2 into this equation. When we do this, we will get Tn equals to Tn minus 2 plus 1 plus 1. So 1 and 1 adds to 2, and the final equation we get is Tn equals to Tn minus 2 plus 2. Now in this equation, in the same equation, we're going to put the value of Tn minus 2 from the third equation. So after putting this value in this equation, we will get Tn equals to Tn minus 3 plus 3. Now this is a pattern. Observe this pattern. First we have Tn equals to Tn minus 1 plus 1. Then we have Tn equals to Tn minus 2 plus 2. And then we have Tn equals to Tn minus 3 plus 3. So you can write this equation in a general form like this. Tn equals to Tn minus k plus k. So here we got the equation, and now we need to reach to the base case, right? We have to calculate the time taken till we go through each element till the base case. And the base case is when we reach to n equals to 1 or n equals to 0. Take either of them in case of factorial. Here in the last equation, we have taken 3 steps. And to reach the base case, we need to take n steps, right? If we take n steps, then this equation becomes Tn equals to Tn minus n plus n. So here we have replaced k with n. And now this equation becomes Tn equals to T0 plus n. Always remember, you want to get this equation in terms of T0. You can see this equation, it is having the term T0. Once you get this term T0, you can remove it, and now you're only left with Tn equals to n. And you can simply wrap it with O. That's it. This is the time complexity of the algorithm to calculate n factorial. Now here, if you go with the base case n equals to 1, then from here you have to take n minus 1 steps to reach to n equals to 1. That is to the base case, right? So here we will replace k with n minus 1. Or you can simply put n minus k equals to 1 as you want to get the t1 term this time. So this results to Tn equals to T1 plus n. So this is what we wanted. We wanted to get T1 in this equation because T1 is the time consumed by the base case. Base case is n equals to 1. And as we're not calculating anything for the base case, the value is already there. We're not calculating anything. That's why we ignore this term T1. And finally, we're left with Tn equals to n minus 1. N is much larger than minus 1. Again, ignoring minus 1, we get the complexity On. So this is how we calculate the time complexity, or we solve this recurrence relation. Let's take another example. Again, the one that we talked about a few minutes ago. Let's write the recurrence relation for getting the nth Fibonacci number and then solve this relation. So the general recurrence relation is Fn equals to Fn minus 1 plus Fn minus 2. Now let's write it in terms of t. So replace Fn with Tn, Fn minus 1 with Tn minus 1, and Fn minus 2 with Tn minus 1 minus 2, and 1 unit to add both the values. And now we're going to start solving this equation, and to make it a little easier, we're going to make an approximation here. It is that time to calculate Tn minus 1 is almost equal to the time taken to calculate Tn minus 2. So if we take this approximation, then we can replace Tn minus 1 with Tn minus 2 in this equation. So we get Tn equals to 2Tn minus 2 plus 1. But precisely the time taken to calculate Tn minus 1 is slightly greater than Tn minus 2, right? So we say that here we are calculating the lower bound of Tn. So this is the first equation. Now let's get the equation for Tn minus 2 so that we can substitute it in the equation 1. So Tn minus 2 we can get by replacing n with n minus 2 in the first equation. So it is Tn minus 2 equals to 2Tn minus 4 plus 1. And now the equation for Tn minus 4. Tn minus 4 equals to 2Tn minus 6 plus 1. Now let's substitute the value of Tn minus 2 into the first equation. When we substitute the value of Tn minus 2 in the first equation, we get Tn equals to 2 multiplied by 2Tn minus 4 plus 1 plus 1. So this becomes Tn equals to 4Tn minus 4 plus 2. And now we're going to put the value of Tn minus 4 from the third equation into this equation. So let's put the value. When we put this value in this equation, we get Tn equals to 4 multiplied by 2 Tn minus 6 plus 1 plus 2. This becomes Tn equals to 8 Tn minus 6 plus 3. Now see the pattern. The first equation was Tn equals to 2 Tn minus 2 plus 1, and then we have Tn equals to 4 Tn minus 4 plus 2, and then Tn equals to 8 Tn minus 6 plus 3. So see the pattern. Let's write it in a generalized form. Here 2, 4, 8, we have them in powers of 2, right? The respective values are 1, 2, 3. 2 raised to power 1, 2 raised to power 2, 2 raised to power 3. And there can be a relation of these powers 1, 2, 3 with these values getting subtracted here. So here we have n minus 2, n minus 4, n minus 6. So this we can write these values as n minus 2 multiplied by 1, and then 2 multiplied by 2, and then 2 multiplied by 3, right? And this value getting added at the last 1, 2, 3, these are also the same. So the relation we get is Tn equals to 2 raised to power k T n minus 2k plus k, right? Now we have to get this equation in terms of T0 because n equals to 0 is a base case. So to get the term T0 in this equation, what is needed? For that, the value of n minus 2k must be 0, which gives us n equals to 2k, right? And from here we get k equals to n divided by 2. Now let's put this value in the equation. When we put this value in the equation, we get 2 raised to power n divided by 2 Tn minus n plus n divided by 2. So here we get the T0 term, which we can ignore, and 2 raised to power n divided by 2 is much larger than n divided by 2, so we can ignore n divided by 2. And finally we get Tn equals to 2 raised to power n divided by 2. Let's wrap it in O, and this is how we get the complexity. This is the lower bound for the time taken to get the nth Fibonacci number, as we took approximation considering the lower bound n minus 2. We can also calculate it using the upper bound when we replace Tn minus 2 with Tn minus 1. I want you to try that on your own. So the complexity that you'll get in that case will be 2 raised to power n. Hope you understood these patterns, that how we solve the recurrence relations. So this was all for this lecture. See you guys in next lecture. Hey guys, welcome back. In last lecture, we saw how we can solve the recurrence relation to get the time complexity of an algorithm using the substitution method. There is another way to solve the recurrence relation that help us solve the relation fairly quickly, and it is using the master's theorem. If the recurrence relation you find out is of form Tn equals to Atn divided by b plus Fn, where the value of A is greater than or equal to 1 and the value of B is greater than 1, then you can apply the master's theorem to solve that recurrence relation. Master's theorem is a kind of shortcut of solving the recurrence relation. So using this theorem, the solution is calculated as Tn equals to n raised to power log A base b multiplied by un. Here the value of A and B will be known to us. The only concern is how we're gonna know the value of un. So the value of un is dependent on hn. We do have a table between un and hn. From there, we get the value of un. But before writing that table, let's see how to calculate the value of hn. The formula is hn equals to fn divided by n raised to power log a base b. Here fn will be given, a and b will also be given. Now let's see the table to get the value of un from the hn. So if the value of hn we get is n raised to power r, where the value of r is greater than 0, then the value of un is or square. And if the r is negative, then un is o1, constant time. And if the value of hn is log n raised to power I, where I is greater than or equal to 0, then the value of un is O log base 2n I plus 1 divided by I plus 1, where I is any number that we are getting as a power to the log n here in the hn. Now let's try this theorem. Let's take an example. Let's say the recurrence relation that we're given is Tn equals to 16Tn divided by 2 plus n squared. After applying the master's theorem, the value of Tn is n raised to power log 16 base 2 plus un. Now here we have to calculate the value of un, which we can get by first getting the value of hn. So if we calculate the value of hn, we will have n squared divided by n raised to power log 16 base 2. So if we solve this, log 16 base 2 is 4, so it becomes n raised to power 4, and n raised to power 2 divided by n raised to power 4 is 1 divided by n squared, which is indeed n raised to power minus 2. Now it is time to get the value of un according to this hn from the table. So here we are getting n raised to power minus 2. So we are getting minus 2, which is the value of r, and it is negative, so value of un is o1. So here we're going to put this constant time o1 in the equation for Tn. So here we put the value of un, which is o1, and this is the final value. Let's solve this. So n raised to power log 16 base 2 is n raised to power 4. So the final solution is O n raised to power 4. So this is how we can find out the time complexity using master's theorem. If you can remember these formulas and table, you can go with this easy way of directly applying the master's theorem. Else use the substitution method. And also don't forget to check on the form of the recurrence relation. It must be Tn equals to A T n divided by b plus fn, where a must be greater than or equal to 1 and b must be greater than 1. If you have a relation something like this, Tn equals to 4 Tn minus 3 plus n squared, see here the value of a is 4 which indeed satisfy the constraint, but the value of b here is 1, which does not satisfy the constraint because the value of b must be greater than 1. So this relation can be solved using Master's theorem. You have to go with the substitution method here. So hope this section was helpful in making you understand what are recurrence relations, why they are so important to understand, and how to solve them and where we're gonna need them. So this was all for this topic. Hey guys, welcome back. It's time to wrap up this section. So let's see what we learned in this section. We saw what are recurrence relations, why they are so important, where we can use them, and then we saw how to solve these relations. And then we saw how we can apply Master's theorem to solve recurrence relations. Now it's time to move to the next section. So see you guys in next section. Hey guys, welcome back. In this section of the course, we're gonna learn recursion. Before actually going to deal with most of the other design techniques, understanding recursion is very critical. Because recursion is the base of algorithm design, and if you will understand and practice enough about recursion, I'm sure there will be no problem for you to understand other design techniques fairly quickly. So I recommend you to put extra focus on this section and practice enough before moving to the next section. So in this section, we will understand what is recursion, how it works internally in the memory. We will go through every detail of that. Believe me that you need to believe on your recursive step. After defining the step, you don't need to visualize all the steps after verifying some initial steps. And we will learn it how. Then we will see types of recursion and recurrence relation. After this, we will actually understand how to identify if a problem can be solved using recursion and how to approach the problem. Then the most important stuff, that is practicing problems. We have selected few of classic practice problems which are most helpful in understanding recursion. We will not only solve them but also code them live. In last part of the course, we will see where to apply recursion and where not, what's good and bad about it, and tail call optimization or tail call recursion. If you will put good amount of focus on this, I'm sure next few sections will become relatively easy for you. So let's start this from next lecture. See you guys in next lecture. Hey guys, welcome back. This section is all about recursion. All about how you can solve big problems very quickly. Let's talk a bit about recursion. Simply put, recursion is just a method calling itself. For the people getting to know the recursion for the first time, recursion might appear to be obscure, difficult, and mystical, but it all settles down with practice. So what do you do if you're having a big problem to solve? You break it into similar subproblems and use the same method to solve all the subproblems and eventually get to the solution of the original problem. Because all these subtasks help constructing the final result of the main problem by returning back the values calculated or constructed by them. So it's like a method foo, again calling method foo for solving its subproblem. Now you'll say, how is this possible? This piece of code will go into an infinite loop and will never terminate, right? If you remember the initial days when we started doing code, you will relate it to writing a while loop having a hard-coded true written as a condition that never terminates. So as the loops have conditions that decides when to terminate the loop, when we are solving a problem recursively, there is always a base condition that prevents the method calls to go into an infinite loop. So if you think about it, a base condition is a condition after which we don't have more recursive steps or calls. There most of the time you will be having a known value or a constructible value without making further recursive calls. Don't worry, let's take an example to illustrate this. The simplest example to explain this, is of calculating factorial of a number. If you want to calculate the factorial, the formula is factorial of n is equals to n multiplied factorial of n minus 1, which if expanded is same as saying factorial of n is equal to factorial of n multiplied by n minus 1 multiplied by n minus 2, and this is how decreasing the value of n until it reaches 0. So this is the formula, right? So if you create a method that calculates the factorial of n, you can use the same method to calculate the factorial of n minus 1. And you can use the same method for calculating the factorial of n minus 2 and so on, until the value of n reaches 0. And the value of factorial 0 is 1. And here it should stop and should provide the solution of this step to the previous call, which in turn calculates its part and pass this on upwards, and this is how all the previous recursive calls are dependent on the space condition. Let's see this whole example using a call stack. Hope you all know about call stack. If not, call stack is a memory area where program stores the local variables, references to objects, and each method call has its own space called a stack frame or an activation record inside the stack, where it stores all of its local variables references belonging to it. Let's take a very simple example. Suppose your application is calling a method m1 which is calling a method m2 internally, and this method m2 is again calling method 3. Here each method call, as we mentioned earlier, occupies a frame in the call stack. When m1 is called, a stack frame for m1 will be there on the stack with all its local variables, references and all, and then when m1 calls m2, a stack frame for m2 is created right over m1 stack frame, and then same for m3 in the sequence. And a stack always follows last in first out order, so the first method to completely get executed is the one that got added last, the one at the top of the stack, which is m3. So it will get executed, and after its execution, m2 executes, and at last m1 executes. So this is how it works. Now let's jump back to the example of finding factorial and see how its call stack will be arranged. When we will call the factorial method for the first time, let's say for 4, so here the first call would be for n equals to 4, which will perform the multiplication of 4 to factorial of n minus 1, which is factorial of 3. So this first call halts until it finds the value for factorial 3. Second call happens with n equals to 3, which again performs the multiplication of 3 to factorial of n minus 1, which in this case is factorial of 2. Again it halts to get the value of factorial 2 so that it can calculate the value for the current call. Now the third call happens, which is 2 multiplied by factorial of 1. In this case the value of n is 2. Again it halts to get the value of factorial 1. And it's the last call where we have no more recursive calls. It is a base condition, so it returns 1. It is given back to the previous call where it calculates the value to be returned by this current call back to its previous call, and this way this goes on, and finally we get the value of the factorial n. So this is how recursion works. Hope you understood that in recursion we compute the result with the help of one or more recursive calls to the same function, but with inputs reduced in size or complexity, going closer towards the base case. So this was all for this lecture. in next lecture, we will talk about identifying if a problem can be solved recursively or not. So let's go there. Hey guys, welcome back. In last lecture, we discussed about what is recursion, how recursion works. In this lecture, let's talk a bit about how we can identify if a problem can be solved using recursion or not. And in this order, we will also try out identifying some problems if they can be solved using recursion. This identification activity will actually be helpful when you will practically deal with recursive problems. So the two things that we need to know if a problem is recursive. First one, problem will always be breakable into subproblems. Exactly identical to the original problem but smaller than the original problem. And second, there will always be a base case. Let's try out these 2 points to identify if a problem can be solved recursively. We will take example with different data types to develop a light idea on how to divide the task if you get a specific type of structure to solve in front of you, so that you can think on how to divide the problem correctly. So first we are taking an example of calculating the sum of first n natural numbers. So let's say the value of n given is 7 and the sum of first 7 natural numbers is 28, right? Which is also equal to the sum of first 6 natural numbers and the current value of n, 7. So we can call the same method to calculate the sum of first 6 natural numbers. Now 6 can again delegate the task of calculating the sum till 5 to the same method in recursion. This will go up to 1. And now 1 is a base condition. If n becomes 1, we will return 1. So yes, this can be solved using recursion, where at each step the value of n is decreasing. So this is how we broke the task, where the smallest subtask is n equals to 1. And here you can see all the tasks from the smallest to the biggest. Now let's see the next case. For a given array A of integers, compute the sum of the elements in this array. This is almost same as the previous one. The only difference is that the type is an array. So first you will only deal with the nth input, that is the current input, else everything will be solved by recursive calls. This will keep on going until the base case. And finally we reach to the base case, and the base case is when we reach to the 0th index. So if we reach to the 0th index, return 0, else keep on adding the current element to the sum till n minus 1th element. So here we are dealing with complete array, not with a single number. So how did we divide it? The smallest subtask was array with a single element, and this increases. So the value of n from the original task, which is the largest array with n elements, towards the smallest or the base task is decreasing. So let's go ahead with another example of again a different type. This time we're taking string. So how we can break it or how we can solve it? We can take the responsibility to concat the last letter, and for remaining string we can call the method recursively. This will do the job for us. And when we have no more words left, that is, the string becomes empty, in this case we will return back the empty string, as we're not going to do anything with it. We will just stop the recursion. So this is how we broke it up. Initially it had the complete length, then it decreases by n minus 1 till the base case. Now next example. Next is not a problem statement in particular, but it's a binary tree, and we're going to talk about how to divide a problem into subtasks if the problem is completely about a binary tree. If you see, binary tree object itself is a recursive object or itself a recursive structure. And while breaking up your problem into subproblems, you must remember this point. Always look at it like a recursive structure. How it is a recursive structure? This tree itself visually have repetitive structure. If you look at the root node, it is further having left tree and a right tree. And again, if you see its left child, which itself is a node, again it's having left child and right child, or left tree or right tree. So at all the nodes, the structure is same. Each of its part is identical to the entire object. So it's a recursive structure. So when you solve problems for such structure, you don't have to think much about how to break it up. It is already visible. Because what you will do for the smallest part will be exactly same to what you will do for the entire object. And if there are no more nodes attached to a node, then we should stop. And this will be the base condition. So this is how you can approach problems with binary trees. Further in this section, we have taken an example of binary tree to understand this whole thing. But in this lecture, we are not going to code anything because this lecture was only about how should we think of breaking a task into subtasks. So this lecture, along with the identification, was mainly about how do we break the problems. This was all about this lecture. See you guys in next lecture. Hey guys, welcome back. So we talked about how a problem is solved recursively, how the cause happened, but an interesting point about approaching a recursive problem is that you actually don't need to think recursively while solving the problem. You don't need to know what is happening in every step. If you want to start solving recursive problems, you must be willing to take a leap of faith. You have to believe because assumptions will need to be made and is necessary for solving these type of problems. Now let's talk about steps that can be followed for writing a recursive solution. First is know what your function should do. Pick a subproblem and just assume that your function already works on it. And third one, using the value returned from the previous problem, that is from the subproblem, to construct the solution of original problem. And the fourth one, identify the base condition. So let's take an example and go step by step. So first is know what your function should do. You should know what the function should return and what the user is going to provide to calculate that result. For example, see this function. This function is going to return an integer sum from 1 to n. So user is going to provide the value for n and it is going to return the sum till that value. Now the second step is pick a subproblem and just assume that your function already works on it. A subproblem is a problem that is exactly identical to the original problem but smaller than the original problem. So we also talked about how to divide a problem in previous lecture, right? For example, if the first call or the top level call is for n, then the subproblem can be for n minus 1. So which you can see here we are calling sum n minus 1 to get the solution to the subproblem. So here n is our original problem and n minus 1 is our subproblem, which is returning the sum from 1 to n minus 1. We're making an assumption that the sum n minus 1 will give us the sum of all the elements from 1 to n minus 1 without iterating through or going through each step. Alright, now moving to the next step. Next step is using the value returned from the previous problem to construct the solution of original problem. So to solve the original problem, we just need to add n to the sum of elements till n minus 1, right? That we're doing here, we're returning n plus solution to the subproblem. There may be other values other than the return value which may be required to construct the original result using the previous step, but here we're just having one input parameter to this function sum. So I'm talking about the other parameters. There can be also other parameters that help in constructing the original solution. And this step can help us do that. That we'll see in some of the examples after this lecture. So as you saw, we took the solution to our subproblem and found how it is used to solve the original problem. And this is known as finding the recurrence relation. Now the last step is identifying the base condition. This will eventually prevent the execution to go in an infinite loop. This also provides the result to the last step. or we can say it provides the result to the smallest subproblem of the original problem. In our case, this would be n equals to 1, which is the smallest problem and can be solved without using recursive calls. So these are the 4 steps that can help us write a recursive solution to a problem if it can be solved recursively. There can be a little to and fro between these steps when you're writing a recursive program for a complex problem. You might not get all the variables or input parameters to be passed into the recursive function at first, so you have to take care that you're not skipping any variable. However, recursion is always very straightforward for straight problems. So this was all for this lecture. Let's start practicing recursion practically from next lecture onwards. Hey guys, welcome back. So in this video, we are going to solve the Tower of Hanoi problem using recursion. Let's discuss the problem statement. What is Tower of Hanoi problem? Tower of Hanoi is a mathematical game or a puzzle. It consists of 3 rods as you can see on the screen and a number of discs of different sizes, which can slide onto any rod. So the puzzle starts with the discs in a neat stack in ascending order of size on one rod, the smallest one at the top, thus making a conical shape. So the objective of this puzzle is to move the entire stack on another rod. But while doing so, there are certain rules that must be followed. Only one disc can be moved at a time. Each move consists of taking the upper disc from one of the stacks and placing it on the top of another stack on an empty rod. No larger disc may be placed on the top of the smaller disc. So, for example, if we have 4 discs, then how will we identify that this problem can be solved using recursion? We will analyze if this problem can be solved by breaking it up into smaller identical problems until we get to some base case. Then we can solve this problem recursively. Alright, here we have 4 disks. We can reduce the program size by decreasing the n to get similar smaller problems. For example, if we have solved the Tower of Hanoi for 3 disks, that is for n equals to 3, then we can add up the implementation to solve the problem with 4 disks. So let's go through the steps to solve this problem. So first is knowing what the function should do. So we will be having a function Tower of Hanoi, and this function is not going to return anything. It will just print how we are moving the disks. So we will only be having print statements. We will not have any return type, or will have void as return type. And what the user is going to provide us? He's going to provide us n, which is the number of disks we want to move from a rod to the 2 rod. So in this game we have 3 rods, one where the disks are placed currently, which is the from rod, and one where we have to place the disk, which is the 2 rod, and one more is the auxiliary rod to help the shifting. So these also must be taken as these all are variables. So we're taking them as input parameters. Now the second step is picking the subproblem and assuming that the function will work for that problem. So if our original problem is for 4 disks, then we can assume that this function will work for 3 disks. See this method. Here I'm taking aux at second position, where for original problem we are taking the 2 rod. Because to complete the original problem we need these 3 disks at this auxiliary rod, so that we can take them and can directly shift them to the original 2 rod. So for n equals to 3, the from rod is same as the from rod of n equals to 4, but the 2 rod for n equals to 3 is the aux rod of n equals to 4, because it is a helper rod for n equals to 4 problem. Now the third step is adding up or using the result from the previous problem to construct the solution of the original problem. So now if 3 disks are already solved, how we can use this result for 4 disks? We can shift the 4th disk from the from rod to the to rod, and then move the 3 disks over it. So this is the solution to the Tower of Hanoi problem. First we shifted all the disks other than the nth disk from rod to the auxiliary rod. And then we moved the remaining, that is the nth disk, from rod to the to rod. And then finally we shifted all the disks present at auxiliary rod to the to rod. Now comes the 4th step, which is identifying the base condition. So if we only have one disk, that is if n is equal to 1, we can directly put it to the to rod, right? So we'll take it and we'll move it from rod directly to rod. That's it. So if you can solve the problem for the current step correctly, considering all the variables, then rest everything would be solved by these recursive calls. Now let's try out the solution in IDE. So I've already created a class puzzle with main method inside it. Now I'm writing Tower of Hanoi method. So return type for Tower of Hanoi is void, as we'll only be having print statements inside this method. And now the input parameters, first is n, which is number of disks. And now we need the 3 rods. So we'll take character for these. So first is from rod, and then to, and then auxiliary rod. Now the implementation is pretty straightforward. So first we will call the Tower of Hanoi recursively for n-1 problem. So for all the disks other than the nth disk, we will be having from as the from rod, but we'll be using aux to shift all these n-1 disks to this auxiliary rod so that we can take all the disks back from that auxiliary rod to the to rod. So from is from, aux, and to this time is aux, and then the auxiliary will be to. And now for the nth problem, for the original problem, we'll print moving the disk, which is the nth disk. So let's take disk n, and from the from rod to the to rod. So here comes 2 plus, and then rod. Yes. And now we'll shift back all the n-1 disks from the auxiliary rod, Tower of Hanoi, n-1. So we'll take them from auxiliary rod and we'll shift them to the to rod, right? So this time the from rod is the aux rod and the to rod is the to rod, and from will be the auxiliary rod. So this is the implementation of Tower of Hanoi. Now remains the base condition, which is if we have only one disk. So if n is 1, then print, and here we'll write moving disk 1 from rod to the to rod. So that's it, and here rest everything should be enclosed inside else. So now this implementation of Tower of Hanoi is complete. We can call it from within the main. So let's try calling it. from within main, and here let's write Tower of Hanoi. So first we need n. Let's say n is 4, and now the characters for from rod. Let's say the from rod is x and the to rod is y, and the aux rod is z. So now we can call this program to test if this Tower of Hanoi function is working properly or not. So let's run this and see this, moving the disk 1 from X to the Z rod. And then moving the disk 2 from X to the Y, and then finally we have to check if we are getting all the disks at the 2 rod, which is the Y rod. So we're getting 1 at the Y rod, we're getting disk 2 at the Y rod, and we're getting the disk 3 at Y rod. So this program works perfectly fine. Now let's analyze the complexity of Tower of Hanoi problem. First, let's talk about time complexity. So we have 2 recursive calls inside a call to make, right? These 2 recursive calls will further make 4 recursive calls, and those 4 recursive calls will further make 8 recursive calls. So it will keep on increasing until we reach to the base case, right? When we reach to the base case, including the base case, we would be having total 2 raised to power n calls. So the time complexity is order of 2 raised to power n, which is exponential. We can also verify this or calculate this using the recurrence relation. So let's create the equation or the recurrence relation. We need to calculate the time taken by program to execute when we have n number of disks, right? And this will be equal to time taken by the subproblems. Here we had 2 subproblems, one to shift n minus 1 disks to aux rod, and one to bring back those n minus 1 disks from aux rod and place them on the 2 rod, right? So this will be Tn minus 1 plus Tn minus 1, and between these calls we had a constant operation of moving the current disk, or you'll say the nth disk, to the 2 rod, right? So now it is Tn equals to 2Tn minus 1 plus 1. So we got the recurrence relation, and now we're going to solve this relation using the substitution method. So we can get the value for Tn minus 1 by substituting n with n minus 1, right, in this equation. So this becomes Tn minus 1 equals to 2Tn minus 2 plus 1. Now let's substitute the value of Tn minus 1 from this equation in the original one. Let's put the value of Tn minus 1 here, which is 2Tn minus 2 plus 1, and this equation now becomes 2 raised to power 2 Tn minus 2 plus 3. Now again we can find out the value of Tn minus 2 by substituting n with n minus 2 in the original equation. This is the original equation, Tn equals to 2Tn minus 1 plus 1. Now let's replace n with n minus 2. So this becomes Tn minus 2 equals to 2Tn minus 3 plus 1. And now let's put this value for Tn minus 2 in this equation. So now this equation for Tn becomes 2 raised to power 2 multiplied by the value for Tn minus 2, which is 2Tn minus 3 plus 1, and then comes plus 3. So this equation now becomes Tn equals to 2 raised to power 3 Tn minus 3 plus 4. So these are the 3 equations. Now let's bring all these 3 equations for n here at the same place and compare them. So when we compare these 3 equations, we get the generalized equation, which is Tn equals to 2 raised to power k Tn minus k plus c. Here the first step towards the solution is complete. Now the next step is to substitute the value of k in this equation so that we can get this equation in terms of n only. That we can get by going to the base case, right? Or you can say by writing this equation in terms of base case. The base case is when we have n equals to 1, right? That is, we are only having one disk. So we need that term T1 here in this equation. For that, we have to replace n minus k in this equation with 1. So if n minus k is equal to 1, then the value of k will be n minus 1. So let's substitute k with n minus 1 here in this equation. Now the equation becomes Tn equals to 2 raised to power n minus 1, T1 plus c. Here T1 stands for n equals to 1 disk case, which is taking constant time to get placed to the 2 rod, right? So we can ignore or we can remove this term T1 here, and C is a constant, so we can remove it or ignore it here as well. So now this equation becomes Tn equals to 2 raised to power n minus 1, which is approximately equal to Tn equals to 2 raised to power n. So this is the complexity we are getting for Tower of Hanoi. So it's having exponential time complexity. Here I've shown you how you can calculate or verify complexity using recurrence relation. But we are not going to solve the recurrence relation each time for every recursive problem, because we don't need to. And one more reason to solve this recurrence relation here was to prove that if we are having a certain number of recursive calls that ends up doing constant time operations in the base case, for those calls, the complexity is branching factor raised to the power n, where n is the number of times we are doing the branching. Here in Tower of Hanoi, the branching factor was 2, as we were making 2 recursive calls inside each call, and we were performing constant time operation in the base case, which was of printing the string. So that's why its complexity was 2 raised to power n. So if we were having 3 recursive calls inside the call, then the complexity would be 3 raised to power n. So this is how we can directly jump to the time complexity of a recursive solution in some of the cases. So now let's talk about space complexity and let's analyze it deeply. In Tower of Hanoi problem, we are not taking any kind of container to store anything. We are directly printing the string, signaling the movement of disks on the console, right? So in our analysis, space complexity we are getting till now is constant space. But the analysis is not complete yet. We have not considered the space required by the call stack. When we are making recursive calls, the call stack is obviously going to create entries for those calls, and the space actually gets occupied there. Consider if we are having 3 disks. The call for n equals to 3 is further going to make 2 recursive calls for n minus 1, that is for 2 disks, one to put the top 2 disks on the aux rod and the other one to bring back those 2 disks from aux rod and place them on the 2 rod, right? And these calls are again going to make calls for n equals to 1. So this is the recursion tree for this problem. Now how stack is going to get occupied with these calls? Whenever we execute lines of code or a program, we go depth first. The 2 recursive calls we are making inside the function are not getting executed in parallel, okay? So the call coming first gets executed first. And after the complete execution of that call comes the turn for the next call. So here, The first call happens is for n equals to 3, so it gets its space or its stack frame inside the call stack. After that, the left call for n equals to 2, or you can say the first call for n equals to 2 starts getting executed. And it also gets its space in the stack. This is followed by the next call for n equals to 1. Again, n equals to 1 call gets its space on the stack, and now it is the base case. We have no further recursive calls. So after it completes, space occupied by it on the stack is released, and the execution comes back to n equals to 2 call. And now comes the turn for the other n equals to 1 call. Again, it needs the space on the stack, so it occupies the space, and after its execution, space is released, and this goes on. Hope you understood how this whole thing works. Now let's focus back on space complexity. As you've seen that the space occupied on the stack is not constant. It keeps varying. So in space complexity analysis for call stack, we always consider the maximum space that can get occupied on stack at any point in time. And this will be equal to the depth of the recursion tree, which is equal to n. So here in case of Tower of Hanoi, maximum number of entries that can get created on stack is n. You cannot have more than 3 entries on the stack, right? So the space complexity is order of n here. So I hope this lecture was helpful enough to make you understand some of the very basic things about space and time complexities, which sometimes are not analyzed carefully. Going forward, it will be more easy for you to deeply understand time and space complexities. Hey guys, welcome back. In this lecture, we will find all the subsequences of a given word or a given sequence. So let's discuss the problem statement. So the problem statement is about finding all the possible subsequences for a given sequence. What is a subsequence? Subsequence is basically a set of elements present in a sequence in same order that they appear in that sequence. For example, if we have a string as a sequence and the string is ABC, then subsequences for this string will be A, AB, ABC, B, BC, and C. Also, we include empty string as one of the valid subsequence. So I hope you got the problem statement. Now let's try to solve this problem stepwise. If you remember all the steps, first is identifying what the function should do. So this function is named getSubsequences. We are going to get all the subsequences for that string. So input parameter to this function is a string. So this word here is of type string. And this method getSubsequences also returns a string because we can concat every subsequence separated by comma and then return it as a string. So the return type is also string. Now the second step, let's see how we can divide this problem into subproblems. So to get an n-1 or length-1 subproblem, we can exclude a letter and we can assume that for the remaining substring, our function already works. So if we call the function for the remaining substring, which is BC, it will give us all the subsequences of BC, right? We're assuming it. Now the third step. Third step is adding up or using the result from the previous problem to construct the solution of the original problem. So from these subsequences of BC, how we can form the subsequences of ABC. It is for sure that these subsequences of BC are also subsequences of ABC, right? So let's again see what would be the subsequences of ABC. So if we concat the letter A to all the subsequences of BC, we can get the remaining part. So see, it becomes ABC, AB, AC and A. So to get this remaining part, we just need to concat the current letter or the first letter to all the subsequences returned by the recursive call. That's it. So we first detach the first letter from the sequence and then call method recursively to get the subsequences of remaining substring, and then we concat all the comma separated subsequences to first letter. Along with that, we also return the subsequences of remaining letters that we add up in the result. Now the fourth and the last step is identifying the base condition. So when you reach at the end of the string, you're just left with empty string. So in base case, we'll return an empty string. So let's create a class and I'm going to name it as string subsequence, and let's include the main method. So we get the class with main inside it. Now let's start off by writing the method. So it is private static. It will return string, so string. Let's call it get subsequence. And let's pass in the word or the sequence, so string word. Now let's get the first character of the string, which is present at index 0. So word, let's invoke char add to get the first word or first character. So let's pass in the index. It will give us the first character. So let's call it first. Now we need to apply recursion to rest everything, that is on the remaining string. So let's call the substring method on this word to get the remaining string. So word dot substring, and let's pass the begin index. Begin index is 1. This will give us the remaining string on which we are going to call the get subsequence recursively. So this will again give us the string having all the subsequences present in the word we are passing to this method. Let's call it rest. Next, we need to concat the first character to all the subsequences returned by this recursive call. But this rest will be having all the sequences separated by comma as a single string. So we cannot concat the first cat directly to this rest. First, we need to split the rest string by comma to get the subsequences one by one. Along with that, we'll keep concatenating the first character. So let's take for each loop. So for each string subsequence present in rest, and let's split it by comma. And now we will concatenate the first with every subsequence present in this rest variable or in this rest string. So I'm taking a variable result and I'm initializing it with empty string, and now in this result let's add first comma and then the first and then the subsequence. So along with this value where we are concatenating the first with the subsequence, we also need the subsequence itself. So in this result, it's string, let's say string. So in this result, we also need to have the subsequence itself. So again, appending it subsequence. So we are separating each subsequence again with comma, and as you can see, initially the result is an empty string. So we will be having one extra comma at the beginning. So to remove this extra comma, we will return result dot substring and will start it from 1. So this will remove that one extra comma at the beginning. Now it's time to write the base condition. Base condition is when the word becomes empty. So if the word we are passing to this get subsequence is empty, so is empty, then return empty string. So now this implementation of get subsequence method is complete. We can test it, and for that we will invoke this get subsequence method within main method. So here let's take a string word, and let's take ABC, and now let's invoke string get subsequence method on this string. Let's pass word, and this will return us subsequences. And now let's print the string subsequence. So sys out subsequence. Yeah. Now let's run this program and see the subsequences for ABC. So see here, we are getting all the subsequences ABC, BC, AC, C, AB, B, A along with the empty string. Now let's change this input and let's try it again. So again, we're having all the subsequences present in this given word along with the empty string. Now talking about the complexity for this problem, if we see the recursive calls, the complexity is order of n, as we are calling this get subsequences recursively for the remaining word, or you can say for the n minus 1 letters. And then we're getting all these subsequences for that remaining word in this variable rest. After that, we are running for loop in which we're making 2n iterations. How? Let's say we are having all the subsequences returned by recursive call for ABC. So we are having 8 subsequences here. Now let's say the original problem is for ZABC. So to get all the subsequences for ZABC, first we will concat Z to all the 8 subsequences from that we are getting from get subsequences function for ABC, and then we will also have to iterate through these 8 subsequences of ABC again, right? So we will be having total of 16 subsequences this time. So each time we add a character in the string or we increase the value of n, the number of subsequences gets doubled. And that's why it is having complexity order of 2 raised to power n, which is exponential. Here the total complexity will be order of n plus 2 raised to power n, but we can ignore the term n as 2 raised to power n is quite bigger than n, thus resulting into exponential complexity. Now talking about space complexity, we are having maximum n minus 1 depth of the recursive calls, which leads to order of n complexity. Hey guys, welcome back. So let's move forward to our next example. Next example or next problem is about finding out the product sum of an array. Product sum of a special array. Special array is an array consisting numbers as well as other arrays. For example, see this array. It's having elements 1, 2, 6, 7, but it's also having other arrays as its elements. Like at position 2, it is having another array with elements 3 and 2, and at position 4, it's having another special array with again an array and 1 as its elements. So now let's discuss what problem statement wants us to solve. So you need to calculate sum of all the elements and multiply with the depth of the array. For this special array, the outer special array, the depth is 1. And for the array 3 having elements 3 and 2, the depth is 2 because it's an array inside an array. And similarly for array 2, 4, the depth is 3. So basically, to get the product sum, when you have numbers in an array, you just add them, and when you have array itself as element, you add all of its elements and then multiply the sum with the depth of that array. For example, for this array having elements 3, 2, it will be 3 plus 2 multiplied by 2. And for this array having elements 2, 4, it will be 2 plus 4 multiplied by 3 because the depth is 3. And then adding up all the elements. Well, if you see, the problem itself is pretty much recursive. You have arrays in arrays. So let's see how we can solve this problem. So let's go stepwise. First is knowing what the function should do. Our function will have a special array as its argument. This special array is a collection of objects. So it's a list. And we will calculate the sum. So the return type will be int. Now the next step is to find a subproblem and assume that the function already works for that subproblem. So the problem is to calculate the sum of all elements present in the array. Now special arrays can further have arrays. So the subproblem is to find out the sum of all the elements present in the subarray. And by assuming that our function is already working, we will get the sum of the subarray with this recursive call. It's saying if the element itself is another list or another array, then add the product sum of this array to the sum variable. So here we are calling the product sum recursively to get the product sum of the subarray. Next step is to use the result of the subproblem to solve the original problem. Now that we have the result of the subproblem, that is the sum of the subarray, so to construct the result of original problem, we just need to multiply it with the depth of the list, and then we can add it to the sum. And to handle the depth, we will add another parameter in function named depth. Initially it would be 1, as the depth is 1 for the input array or the top level array, and then whenever you come across the special array, you just increment it with 1 and the depth increases by 1. We can also write it in a helper function and invoke inside other function by passing depth as 1, as the client doesn't need to know anything about the depth. So when you have your sum result of the subarray, you can multiply with depth and then you can add it to the sum. Now next and the last step is to find out the base condition. So when you have number, you don't need to go recursive. You can add it up with the previous subproblem's result. So this will also be the base case. Now let's implement the solution in code. So I've created a class called productSum having main method inside it. So let's start writing the method static int productSum, which will return us the product sum of the special array. So this will be having the array, the special array, which will actually be the list. So it's list, that's import list, and the other input parameter to this method will be the depth. So depth. Now in this method, we will iterate through the list and we'll find out if any object is a list itself, if object instance of list, then we will call this product sum recursively to get the product sum of that sub array. So product sum, and here we will pass this object which is actually a sub array. So object, and we need to cast it to list, and the other parameter is depth. We will increment it each time by 1, so it will be depth plus 1. And now let's add it to the sum. Let's take a variable called sum and initialize it with 0. So if it's a special array or subarray, we will call the product sum recursively. Otherwise, it will be an element. We can directly add it to the sum. So sum plus the element, which is object. And let's cast it to int. And then finally, when the sum is ready, we have to multiply it by the depth. So here we will return sum multiplied by the depth. And now comes the base condition, and this else block here is also covering that. So we don't have to write the base condition separately. So now this implementation of product sum is complete. We can invoke it from main method. So first we need to construct an special array. So let's take list of object, and let's call it A1, and let's create a list of elements 2, 3. And then again let's have another list A2 and then A3, and this A2 let's say is having 2, 4, and this A3 is having, let's say, at the first position at 0th index it's having A1, which is another list, and let's say it's having another element 1, and then we are creating another list. This is the list that we're going to pass to the product sum method. So let's call it array or special array. And now in this list, let's pass elements 1, 2, and let's say at third position we are having another list A1, and then 6, and then let's say A3, which is again another array, but it's again a special array having another array as its element, and then finally 7. And now let's print the sum, the product sum of the special array. So let's pass array here and the depth, which is initially 1. Now we can run this program. So let's run this to see the output, and see we get 58, which is, if we calculate 1 and then 2, it becomes 3, and then A1, which is 5 multiplied by 2, 10, so 13, and then 6, which is 19, and then A3. A3 is again having A1 as element, so this time the depth of A1 will be 3, so it will be 5 multiplied by 3, which is 15, and 15 plus 1, which becomes 16, and 16 multiplied by 2, which is 32. So 19 plus 32 becomes 51, and then adding 7 to it gives us 58. So the method is working this way. Now let's talk about the time complexity of the solution. The time complexity will be order of n. It will execute in linear time, and here all elements in the subarray are included individually in this n, because we're gonna visit each element once, whether it is inside main array or inside subarray. So here n is not the number of elements in the outermost array, it is actually the number of all individual values. Now let's talk about the space complexity. In this case, space complexity is the maximum size of stack that can be occupied at any point in time while executing the algorithm, and this will be equal to the depth of the array. and the depth is 3, we can get maximum 3 frames filled in stack with these recursive calls. So the space complexity is order of D. Hey guys, welcome back. Let's go ahead with another problem that we're gonna solve using recursion. So the problem is finding out if a given binary tree is a subtree of another binary tree. So before jumping into the discussion, I want to tell you one thing, that this problem just needs you to know that how we exactly traverse a binary tree. If you know that, you exactly know how to write the solution. So it is, I guess, very simple to understand the problem. We will be having two trees, let's say tree 1 and tree 2. We have to check if tree 2 is a subtree of tree 1 or not. And as you can see, this tree here is actually a subtree of tree 1. So our function must return true. So this was the problem statement. Now let's talk about how we're going to approach this problem. Approach we can take is, first we can traverse and store the elements of both the trees in separate arrays in a particular order. For example, in order. In order, the left child comes first, and then the node itself, and at last comes the right child. You might know there can be some other order too, like pre-order, post-order. Pre-order means that the node itself comes first, and then its left child, and then the right child. And you can guess post-order means node coming at the last. First the left child, then right child, and then the node itself. So after traversing these two trees and getting the arrays for both the trees, we check if the smaller tree is a subset of larger array. So here the recursive strategy is only needed for traversing the trees. So if the in order of tree 1 and tree 2 are these arrays, then you can say that this tree 2 is a subset of tree 1. But that's not always the case. Nodes with same value arranged in different manner may also produce a subset of in-order set like this. But this is not the subtree, right? So for that, we need to take another traversal to validate the same. So along with in-order, we also need to find either pre-order or post-order for both the trees. So in this example, if we check the pre-order for this tree, then we find out that clearly it is not the subset of the pre-order of tree 1. Whereas if given binary tree is a subtree, both in-order and pre-order arrays of given subtree will be subset of the main tree. So how are we gonna do these traversals recursively? Or how are we gonna write the solution using recursion? If we are going to go with in order first, then first we need to go to the left and then to the node itself and then to the right child. Similarly with pre-order, we first go to the node itself and then the left and then the right. So let's have a dry run to the solution. Remember all the steps, first identifying what the function should do. So the function is, let's say in order, it will take the tree and will return an array, right? As we mentioned this. Same with pre-order. Next is picking a subproblem and then assuming that function already works on it. Subproblems for a tree are its subtrees because it's a recursive structure, remember? So how are we gonna break this problem up? We'll first traverse the left tree at every node, then the root, and then the right, in case of in order. So first traverse the left node, which again is a tree, so this in order function call recursively traverses that tree and adds the nodes from that tree into the array or the list, and then comes the node itself, and it's get added in the array, and then comes the right node, which again is a tree, and this recursive calls makes that happen again. Now the same goes with pre-order. The difference is just in the order. First comes the node, and then the left, and then right. Okay, now the third step is using the recursive steps and constructing the solution for the original problem. And that we already did here. To construct the original problem, we just needed to read the current node, and other nodes are just being read by these calls. So the third step is complete, and now comes the base case, the fourth step, which is identifying the base condition. If the current node is null, then simply return from there. That is it. This is the recursive code. Now we just need to check if the array 1 contains all the elements of array 2 or not, in both in order and pre-order. And they should be consecutive. So here we can get the string for both and go for substring method. That's it. Now let's talk about the time complexity of the solution. If the length of the first tree is n and the length of the second tree is m, then the complexity will be O n plus m, as it is going to meet each node only once. So it's O m plus n. Now let's move to the IDE to try out the solution. So this is the node class that we are using to create the trees. It's having data, right and left. So this is the first tree. It starts from root, and here we are setting up all the edges. And now this is the tree 2, which is starting from root 2, and we have added right and left to it. Now let's create function in order where we will do the in order traversal. So let's create the function public static void in order, and here in this function we will pass the root node from where we are going to start the traversal, and we are going to pass list to store the data, the node data in order. And in order we know that first we traverse the left, so left is again a tree, so we are going to call in order recursively for node.left, and again we're going to pass this list so that it will store the data in list. And now we are going to call in order recursively for right, and we're going to pass the list. And these are the subtasks. Now the main task will complete, the original task will complete when we will read the current node. And you know the order, first comes left and then the node itself. So here we are directly adding the data of the node in the list. So now the sequence is perfect, and now the base case is if node itself is null, then return from here without doing anything. This is it. So this is the in order function. So we are going to do two traversals here, first in order and the another is pre-order, right? So here let's say this is pre-order, and you know the order in pre-order, first we add data in the node and data for the node itself, and then comes the left and then the right. So just change the order and function call here, everything else is correct. So we have created in order and pre-order. So here we are storing the in order traversal in list, and here we are storing the pre-order traversal in list. So these were the two prerequisites for our main function. So here let's create our main method. Let's say this function is to check if given tree is subtree or not. So here let's write this public static boolean, and let's say check subtree. This is the main function, and here we're gonna pass the tree 1 and tree 2, right? So this is tree and this is the subtree. Here we will check if the subtree is null, then we can say that the subtree is actually subtree of the tree, right? So if the subtree is null, we will return true from here. And if tree itself is null, if tree is null, then we can't say this and we will return false from here. And now we will do the in order traversal. So let's create two lists to store in order traversals for tree and for the subtree. So this is the first list in which we are going to store the in order traversal for tree. So this is the first array list, and now let's call in order by passing the tree and this list first. And now let's create the list in which we are going to store the traversal for the subtree, and we are going to call it second. And here let's change this to sub and let's change first to second. So after getting these lists filled up with data, we are going to convert these lists to strings so that we can compare these lists. So here let's create a function to convert these lists to string. So private static string, and let's call this method list to string, and let's pass the list that we want to convert to string. So this is list integer, and now here let's return list dot to string dot replace, and here we are going to replace the brackets and commas, right? So replace the bracket with empty string. Now replace the close bracket with empty string, close bracket, and here let's replace it with empty string. And now after this we're gonna replace comma with empty string, comma, and here let's write empty string. So this is the function that will convert the list to string. Now let's invoke this function for getting the equivalent strings for first and second. So here list to string, and here let's pass the first, and now check if this contains list to string, and in this let's pass second, and we are going to do it reverse. In reverse we are going to check if the first does not contain second, then return false, else go ahead with pre-order traversal. So here again we are going to do traversal, so we will be needing first and second to store the result for the traversals. So we are going to clear the data from first and second, and now let's call pre-order, and in this, as the tree pass tree and as the structure in which we are going to store the data pass first, and now here pass the subtree and pass second. So this will result to pre-order traversals for first and second, and we are going to do the same thing. We are going to convert these lists to string. We are going to check if the first contains the second. If the first contains second, that means it is the substring of first, and the tree is subtree of the tree one. And here column. So that's it. This is the implementation. Now let's go to the main method and check if the subtree that we have created is subtree of the main tree or not. So here in main method we are going to print the boolean results. So we are going to sys out it. So system.out.println, and here let's call check subtree. But before verifying the result with the subtree that we have created, let's pass root.left as the subtree. It must return true as its own left is its subtree. So it returns true, and now let's check it with the subtree that we have created. So here at the place of root.left we are going to pass root2. And now let's save this and again run this. So this time it must return false as 456 is not a subtree of this tree. So let's save this and let's run this. So see if it returns false. Now let's analyze the complexity for this problem. Let's first talk about time complexity. So in order to check if given tree is subtree or not, we need to find in-order and pre-order traversals of both the trees. So that is going to take n plus m number of operations, where n and m are the number of nodes present in these trees, because it will go through each node to get these traversals. So the time complexity is order of n plus m. And for storing the tree information, we will be needing m plus n storage here. So the auxiliary space consumed by this algorithm will be O n plus m space. Hey guys, welcome back. In this lecture, we are going to talk a bit about the reasons of using recursion or avoiding recursion. If you're writing a code for any algorithm, then given the same algorithm, the iterative version will generally be faster than the recursive version. The big reason is function calls used in recursion are expensive operations. A function call requires recording the current state of variables and making a copy of them in stack memory so that they can be restored when the function returns. Some languages, however, use tail call optimization to avoid this. We will talk about tail call optimization in next lecture, but for many problems, recursion is much more intuitive approach because it can do the job in few lines of code. Developers often start with a recursive version and then convert it to an iterative version only if they need to get every last bit of performance out of the program. So these were the very few obvious reasons of using recursion or not using recursion. Hey guys, welcome back. After understanding recursion, let's see how recursion is categorized. So broadly and conceptually, these are the main categories: direct recursion, indirect or mutual recursion, multi-recursion, head recursion, and tail recursion. Let's go ahead and try and understand each one of them. So first is direct recursion. Recursion is direct recursion when the method directly calls itself. For example, here the factorial method is calling itself with different input. Next is indirect recursion or mutual recursion. It is when a function, say a function A, calls another function, function B, and function B again calls function A. This is called indirect or mutual recursion. Now, multi-recursion. When there are multiple recursive calls in a function, for example, finding the nth Fibonacci number, here we are calling the same Fibonacci function twice in the same function. Now, head recursion. Head recursion is when there is some operation left to be performed after the recursive step. And if there is no operation to be performed after the recursive step, then it is tail recursion. We will understand this difference deeply in one of the lecture. So these were the categories for recursion. But to develop understanding of how recursive algorithms takes few different forms, we can divide them into more categories. This categorization that we're going to see now is a bit helpful from algorithm perspective. And these categories are linear recursive functions, tree recursive functions or binary recursive functions, exponential recursive functions, nested recursive functions. And there can be more according to how the recursive function is behaving. So let's start with the first one, linear recursive function. A linear recursive function is a function that only makes a single call to itself each time the function runs. Again, The factorial function is a good example of linear recursion. Now next is tree recursion or binary recursion. Some recursive functions don't just have one call to themselves, they have two or more. Functions with two recursive calls are binary recursive functions, and if there are more than two calls, you can refer as tree recursion or tree recursive function. Now, next is exponential recursive function. An exponential recursive function is one that, if you were to draw a representation of all the function calls, would have an exponential number of calls in relation to the size of the dataset. For example, if it is when you loop inside the recursion. Now next is nested recursive functions. In nested recursion, one of the arguments to the recursive function is the recursive function itself. These functions tend to grow extremely fast. So these were the main categories. Here we have explained these types only to develop understanding of how you can understand what is going on in recursive function. But there can be more types or categories depending on how the recursive function grows. So this was all for this lecture. Hey guys, welcome back. In the first lecture, we saw how recursion works, right? It creates the stack frames and then starts executing the stuff from the top of the stack. All other frames wait for the result returned by the previous calls, right? And we also discussed what are the drawbacks of recursion. All we talked till now was about regular recursion. But there is another kind of recursion that is as efficient as iteration. Yes, and it is called tail call recursion. And in compiler terms, we also call it tail call optimization. Let's go ahead and discuss what is it. You all know how recursive programs works internally. For instance, how the recursive program of finding factorial of a given number behaves internally, right? An activation frame or stack frame gets created on each recursive call. Now these frames waits for the value returned by the previous frame so that it can calculate the right value for the current frame and again pass it down, right? So this is regular recursion. Now let's write the same code in slightly different way. See this code here. We are calling this function tail fact recursively. There are two input parameters to this tail fact. One is n, and the second one, which is an extra parameter, it's called accumulator. So this is a tail recursive code. Let's see what happens in this case. Let's say for the first call, the value of n is 4. So it again calls itself with n minus 1, which becomes 3, and n multiplied by a, which is 4 multiplied by 1, which is 4. So here completes the first call. Now notice it's not having any further operation to perform on the value returned by the next call. So it does not have any value to hold in this stack frame. So now it doesn't have to come back to this call and this frame can be removed. Now the second call, for this call n becomes 3. So it again call itself with n minus 1, which is 2, and accumulator, which is n multiplied by a. In last execution, the accumulator was 4, so this time it becomes 3 multiplied by 4. So the new accumulator is now 12. For n equals to 3. Again, it does not have to come back to this call, and this frame can be removed. Now the third call happens for n equals to 2. Again, it calls itself with new n minus 1, which is 2 minus 1, that is 1, and the new accumulator, n multiplied by a, which is 24 because n is 2 and a by previous call was 12. And now with the next call, the frame is removed. Now the fourth and the last call where we have the if condition or the base condition where the value of n is 1. So in this case, it directly returned the accumulator passed to it. So hope you got the difference. In case of regular recursion or head recursion, it keep holding on to the stack because there are further operations to be performed. So when the input is large, such recursion can result to stack overflow error. Whereas in case of tail recursion, we are having an accumulator to store the product in it. It's not holding on to the stack for the operations. That's why during each call, there was only one frame shown in the stack in case of tail recursion. In modern compilers like compilers of Scala, Kotlin, etc., tail recursive calls are converted into pure iteration or imperative loops at compile time to optimize the code. So this is the advantage of using tail recursion that you don't have with regular recursion, because compilers can't convert regular recursion into iteration. However, every recursion cannot be written in tail recursive way. But for any problem, if you can figure out the tail recursive code, you must go with that one. So this was all about tail recursion or tail call optimization. Hey guys, welcome back. So here comes the end of the section. Let's quickly sum up what we have learned in this section. In this section, we discussed what is recursion, how it works internally in the memory. We also discussed that after verifying recursion, for some initial step, you do not need to visualize all the steps. You just need to have faith on the recursion that recursion will do it for you. Then we learned types of recursion and recursion relations. After this, we understood how to identify a problem. We discussed how to approach a problem. We discussed several classical problems to practice recursion and we coded them. Then we discussed some pros and cons of recursion and tail call optimization. I'm sure by now you're very well familiar with recursion and can code recursive problems. So let's move to our next section from here. See you guys there in the next section. Hey guys, welcome back. In this section of the course, we will discuss an algorithm design technique called backtracking. This design technique is a kind of extended form of recursion, but with some special properties, as the name suggests. The problem that falls under backtracking are the problems where we need to take our decision back. It means we change the decision at runtime and take a step or multiple steps back. These type of algorithms and design techniques are very useful if you are into game programming, especially strategy games. So in this section of the course, or say in this design technique, we will focus on what is backtracking, how to identify that the problem can be solved using backtracking, how to approach the solution of a given problem using backtracking. We will solve some of the problems on backtracking. We will code them. And we will solve few classical backtracking problems, not only theoretically, but through pseudocode and actual live coding. So let's quickly introduce backtracking in next lecture. Hope you might be excited to learn this new algorithm technique. Let's make it more fun with good and interesting problems to solve. So see you guys there in the next lecture. Hey guys, welcome back. Backtracking. Backtracking is very interesting algorithm. If you have a little idea about it, then you must be knowing that backtracking is going back to change the already taken decision and then resuming from there with a different decision until we get to the solution, right? This is how people generally think of backtracking. And in more technical terms, backtracking is the technique to solve a problem recursively. by making series of choices, and if any of the choice fails, we abandon the choice and try a different one. This is the big picture of backtracking, which is actually made up of few important elements internally. So after starting with a light introduction to backtracking, we are going to get deep into it and start understanding all the important things related to it. First of all, before trying to write the solution to a backtracking problem, we must know what is backtracking, which I guess you now know, and how we're going to identify if the problem can be solved using backtracking. So let's talk about how we will identify if a problem is a backtracking problem in next lecture. Don't worry if you're not able to visualize backtracking yet. You will start getting more into backtracking with next few lectures where we will be discussing identification and the standard approach to solve backtracking problems. So let's meet in the next lecture. Hey guys, welcome back. We started discussing about backtracking in previous lecture. By now you might have got the general idea what the technique is about. Now how we can actually identify that the given problem can be solved using backtracking. For that, let's see what we will be given in the problem statement. In problem statement, you will be given a set of choices to be made and certain constraints. For instance, consider the Sudoku problem. In this, you're given a Sudoku board and you have to fill the digits 1 to 9 in empty cells of the board in such a way that the digit appears exactly once in each row, in each column, and in the subgrid. So here the choices are the digits from 1 to 9, and the constraint is that the digit cannot appear more than once in row, column, and outline subgrid. So talking about the Sudoku problem, at each cell you make a decision by keeping all the choices and constraints in mind. So you keep on making decisions with given candidates and try to solve the Sudoku recursively. But if at some point there is no right digit left to be placed at the certain cell in the board, you will take a step back and refill the cell with a different digit. That's how we do it. So the key thing you check in your program is that if it consists of decision-making cells that you make on the basis of given choices and constraints, and if the decision doesn't work out, you backtrack and make another decision with different choice. Then the problem is a backtracking problem. And in backtracking, you do make recursive calls. But unlike recursion, you don't just keep moving forward in a single direction to solve the problem, as you have multiple choices at each step in case of backtracking. So whenever one choice fails, we go back and we move to the other choice. So I hope you got the difference between these two. So these were the points to be noticed to identify backtracking problem. You will get the clear idea on it once you see how we actually approach the solution. That we're gonna see in the next lecture, where we will cover each and every element required to solve the backtracking problem. So see you guys in next lecture. Hey guys, welcome back. Until now, we tried understanding what is backtracking and how to identify backtracking. In this lecture, we will see a blueprint to solve the backtracking problem. In a real problem, initially you'll be given a matrix that may be having zeros or maybe ones or maybe the combination of both. So you'll be given a matrix with all the cells filled up with some initial values. Now there are 4 elements that we think on to solve almost any backtracking problem. Let's observe these 4 elements. First is the choices. To build a solution for a problem, at each step we will be having choices. Because if it is a backtracking problem, we definitely be having more than one choice at each step. Because backtracking is all about going forward with a choice, and if the choice proves to be a wrong choice, then going back and discarding that choice and trying other options until we get to the solution. So, when we are going to approach a backtracking problem, we have to think of the core choices that we have at each step, or let's say at each cell. This is like a fundamental element to solve backtracking problems because at each step you'll be having same choices, which means there will be same decision space each and every time. So when you will solve the problem at any step, you don't change the decision space. For example, if you're given a matrix, or let's call this matrix a maze, and you have been told that you have to find a path to reach from the top leftmost cell to the bottom rightmost cell. Given that you can only walk on the cells having value 0. So see this matrix, the path that can be traversed to reach the destination is this one, right? Telling the answer straight just by seeing this is easy, but how will you do it programmatically? So that the program runs fine not only for this path but for any given matrix. The first fundamental element to write the solution is the choices, as I said. So see the first cell. At this cell, we have two choices to move forward. We can either move one step in X direction towards the next column or in Y direction downwards, that is towards the next row right below. This decision space is same at each cell. So if you are at the second cell, again there are two options, one of which we can choose. So this is how we identify choices. Now the next element is constraints, using which we validate if the current step is inclusive or safe to update. Now think of the second cell. We said at each cell we have same decision space, right? But at the second cell, you cannot make any step forward towards the X direction because the next element there is 1. And we cannot move to a cell which is having value 1. And also think of the third cell in the next row, that is in the second row. If we reach here, we cannot make any step forward in X direction because there is no cell after it in the same row. So these are the areas where constraints kick in. There are always some constraints to handle the boundary conditions or to validate the current step. So we always do a constraint check before making any move. So if I talk in terms of this example, see this function is valid. It will return true only if it satisfies these constraints. The row must be greater than or equal to 0 and the row must be less than 2. And similarly, column and the cell must be having value 0. So if all these constraints are satisfied by the current candidate, then only we include that candidate. And if we are including the candidate, we are setting the value for that candidate as 0. And then we move forward with next moves. Now to make the next moves, we need our third element, which is recursion. It is safe to include the cell in the solution, then we can go further, right? And how we can go further? Simply by calling the same function again for the next cell, right? So we can call the recursion then. Recursion is always about how we want to move forward to cover next cells, keeping all the choices in mind. So for this example, we already identified that either we go in X direction. For this recursive call to go in X direction, we increment the X by 1 and we keep the Y same. X is column, so we increment the column by 1 and we keep the row same. And to go forward in y direction, we call the function recursively by keeping x same but incrementing the y. So we are incrementing the row by 1. Now if going forward in x direction does not work out, then the execution come out of that recursion back to the current stack frame and it tries for the next option. Next option is to go forward in y direction. So it starts towards y, goes deep into the recursion, creates some path in these directions. From there, if reaches the destination, it wins and comes out of the recursion with a solution. Else it comes back failing from the next frame back to the current frame and start again from there with other choice. And if all the choices for current candidate fails, the only option left is to reject the current candidate because the current cell cannot lead us to the solution anyways. So we have to discard or undo our decision or undo the already set value for that cell. This is what we call backtracking. Discarding the current decisions on the basis of future results. I like it to state it this way rather than saying we go back and revert the decision. However, both statements are trying to say the same thing. So here either if the current cell fails on the constraint or going forward with any choice does not work out, in both the cases it marks the current cell 1 to say that this candidate or this choice can't be a part of the solution. Now the last element. The last element is goal. This is the element which tells us when we're gonna get the result. Clearly, this is the element which get us to the base case or base condition for the function. The base case is when we get to the final solution. For example, here the goal or the last step is to reach to the bottom rightmost cell. When we reach here, we will be having the final solution in our hand, right? So here we should stop. We don't need to make more recursive calls then. So reaching the cell at n-1th row and n-1th column is a base condition. If it reaches here, we can return true and the maze will be fully updated here with the final path. Let's see the complete solution to the problem we took. This is the complete solution of the problem. And here we have the constraints, we have recursive calls in x direction, we have recursive calls in y direction. These recursive calls are associated with choices. We have backtracking step and we have goal. Let me also tell you one secret that algorithms are very natural and I started getting how to solve them when I solved a bunch of these problems. And I'm very sure this will happen to you as well. So start solving some problems along with me from next lecture and then I strongly recommend coming back to this lecture after solving some of the backtracking problems. Then it will start making very much sense to you. So let's stick to these elements and start solving backtracking problems from next lecture onwards. Hey guys, welcome back. So the next problem we're going to talk about, which can be solved using backtracking, is the rat in a maze problem. So basically you're given a maze. A rat starts from the top left corner and it has to reach the destination, which is the lower rightmost corner, to get out of this maze. There are some obstacles or dead ends in this maze. The rat cannot cross these. So the rat can go in forward direction or it can go down. In the real problem, you'll be given a matrix having zeros and 1. 0 means dead end and 1 is the valid path to be traversed by the rat. So if we are solving this problem using backtracking, then let's see how the solution is going to move back and forth. How do we actually deal with this problem or how do we approach the problem? We know all the 4 elements, the choices we make, the constraints we adhere to, recursion, and the final goal or the base case. So first is choices. That gives us the hints about how to draw recursive steps, right? We have to think of the core choice we're making at each step or at each cell. So the decision space is either we can move in X direction or we can go forward in Y direction. So these are the only two choices we have to make at each step. Now the second element is the constraints, using which we validate if the current step is inclusive or safe to update. So we can move here in two directions, forward and downwards, right? But there are constraints that restrict us to move in these directions. The current cell can only be included in the path if it is inside the maze and is having value 1. For example, if the cell value is 0, that means it's a wall, so you cannot move forward. And when you reach at the last cell of a row, that means you cannot move forward in that same direction because it will be outside of the maze. And similarly, if you reach to the last cell of any column, that means you cannot move forward after this because it will be outside of the maze. So before including any cell in the path, we must adhere to these constraints. The value of the cell must be 1. It should be inside of the maze. So now if it is safe to include the cell in the path, then we can go further, right? So we can call the recursion then. So recursion is decided by the choices. We already talked about the choices. Either we can go in X direction, and for this recursive call to go forward in X direction, we increment the X by 1 and we keep the Y same. But if we cannot go forward in X direction due to the mentioned constraints, then we will go in Y direction. And for going in Y direction, in the recursive calls, we will keep the X same, but we will increment the Y by 1. And if we cannot go forward in both the directions, then we unmark the current cell by overwriting it with 0. Basically to remove or undo our decision for that cell. That is, if all choices fails, then for the current cell, the last choice always is to discard or undo the already set value. Because if going forward with any choice cannot work out at this cell, then this cell cannot take us to the right path. And this is the backtracking step, as you know. So see, either we go in X direction using the recursive call, and see here in this recursive call where we are calling solve maze, we're incrementing the X, but we're keeping the Y same. But if going forward in X direction does not work out, then we go forward in Y direction. And when we go forward in Y direction, we keep the X same, but we increment the Y. And if going forward in both the direction does not work out, then we undo our decision for the current cell. So we put 0 at that cell. Now the last element, which is the goal. So the last step is to find out the base condition, and it is when the red reaches its goal. The goal is of getting out of this maze, right? So the red will reach to its goal of getting out of this maze when it will be at the final cell of this maze, which is the cell at n-1th row and at n-1th column. So this will be the base condition. If it reaches there, we can return true and the maze will be fully updated here with the final path. So we update the value for the current cell and we return true. And with this base condition, our solution to this maze problem completes. And this is the complete solution to this maze problem, where we have constraints according to which we set the value for the cell. And then we have the recursive steps which are based on the choices. We can do recursive calls in x direction, we can do recursive calls in y direction, because going forward in x direction and going forward in y direction were the two choices we had. Then we have the backtracking move. If the choices do not work out, we can undo our decision for the current cell. And then finally we have the base case, which makes us reach to our goal. So let's see how the complete solution will work. So this rat can move in x direction and it can also move in y direction. First it will try to move in x direction and the next cell is having 1, so it can move to the next cell. Now again it will try to move in the x direction, but it will fail to go in x direction, but it have other option to go in y direction. And from here again it will try to go in x direction and again in x direction, again in x direction, but it will fail to go in x direction because it will be out of the maze. Now from here it also cannot go to the y direction because y direction is a wall, it's a 0 cell, so it cannot go in y direction. So it will move, so it undo its decision for the current cell. Again, it cannot move in y direction because there is a wall, so it goes back and undo its decision for the current cell. And from here, it can happily move in y direction because the next cell in y direction is having value 1. Now again, it tries to go in x direction. It cannot go forward in x direction, it's a wall, so it goes in y direction. From here, again, it goes in x direction and it happily moves, and again happily moves, and it reaches to the end of this maze, which is the goal. Now let's try out the solution in IDE. So this is red in maze class. See here, we have given a maze. It's a 4x4 matrix having zeros and ones. Now let's go ahead with creating and calling a method to solve this maze or to find the path to be traversed by the rat. So let's call it solve the maze, and the first argument to this method is the maze itself. Now we have to make the rat start from somewhere, and the position from where the rat starts its journey is the first cell, where the value for both row and the column is 0. So let's pass x and y, and solve the maze is gonna return a boolean. So to accumulate the result, we don't have anything yet. So we need another matrix of same size. Let's take n, which would be equal to the maze dot length, which for this maze is 4. And now let's create another matrix of same dimensions. Let's call it sol, and it's new int n. And after creating it, I'm going to pass this matrix and the n in this method. And let's start the main implementation. So when we implement backtracking problem, first we check for constraints. So the first element is constraints, right? To check the constraints on the current cell, let's create a separate method and let's call it isSafe. And let's pass maze xy. Let's name I and j, replace with x and y. If this is true, then mark the current cell of the solution matrix, which is sol xy, mark it 1. So we will put 1 here in this cell in our solution matrix. Let's tell the program when to include this cell by implementing this isSafe method. So here in this isSafe method, what are the constraints we are going to pass? First condition is that X and Y both must be present inside the maze. So X must be greater than or equal to 0 and it should be less than N. And similarly, we have Y. Y should be greater than equal to 0 and Y must be less than N. And the current cell must be having value 1. So maze xy must be equal to 1. So if this is true, then this is safe method is going to return true. So when the cell is safe to be included in the path traversed by the red, we're marking it with 1. Now comes recursion. We have two choices. First, we can go in x direction. So let's check if we can go forward in x direction. If solve maze, so here comes the recursion where we are calling the solve the maze method recursively, and let's pass the maze. We're going to go in x direction, so we have to increase the x by 1 and we will keep the y same and then pass the solve matrix and n. So if we can go forward in x direction, we're gonna return true. Otherwise, we can go in y direction. So let's again call solve the maze recursively. It's gonna return boolean, so let's change the return type and now solve the maze, pass the maze, and we'll keep x same and we will increment the y and we will pass the solve matrix and n. So if we can go forward in y direction, we're gonna return true here. But if none of the above movements work, then we have to backtrack. So let's backtrack. How are we gonna backtrack the solution? Let's write the backtracking step. Here we set the value for this current cell with 1. So here we are going to undo our decision. So let's unmark XY cell as part of the solution. And to do that, we just have to overwrite it with 0 and now return false, saying that this current cell cannot be included in the solution. So almost the solution is complete. Now comes the base case. So if we reach to the goal, when we will reach to the goal, when the x will be n minus 1 and y will be n minus 1, because this is the last cell. So here we will update the value for this last cell and we will return true. So these are the preconditions, that x must be n minus 1, y must be n minus 1 and the cell must be having value 1. If this is true, then we will update the last cell of the solve matrix with 1 and will return true. So this is how we will get the final updated path as the solve matrix. Let's add the return statement. So if it is not safe to include the current cell, then we are not going to do anything. We will just return false. Now the implementation is complete. Let's go back to our main method and here let's print the solution matrix. So for first loop is for, let's say, rows. So for I equals to 0 until I is less than n, we're gonna increment the I, and inside this we're going to take another loop for columns j starting from 0 till n, and increment the j, and here we're going to print each element of this solve matrix. So solve ij, and we're gonna separate these elements with spaces. So we're gonna put some spaces between these elements and one space after this element, and then one row completes. After that we will change the line. and here it should be print. So this everything we are going to print only when the solve the maze is going to return true. So if solve the maze return true, then print the solution matrix, else print that path not available or no path available. So now this is the complete solution of the red in maze problem. Let's try running it and see what we get. So this is the solution matrix where we have this path from this maze that we initially had. Now let's change this and again run this. This time we have two paths, right? So let's run this. This time the path we get is this one because first we are taking x and here x is standing for rows. So if we are going recursively towards x, that is we're changing rows each time. So that's why this is the solution path. And this is how we can solve the rat in the maze problem using backtracking. Let's meet in next lecture with a different problem. Now let's analyze the complexity of rat in maze. At each step, you're allowed to either go in x direction or in y direction, right? The matrix is of size n cross n. So in worst case, you might take n step in x direction, and if it doesn't work, you take n step in y direction. So here the branching factor will be 2 as you're making 2 recursive calls at each step in worst case. And there will be n cross n recursive calls in total. Hence the complexity will be 2 raised to power n square, where n is number of rows, or you can say number of columns if it's a square matrix, right? So otherwise it will be 2 raised to power n cross m. So this is the time complexity of rat and maze. Now let's talk about the space complexity. So we are taking an output matrix to store the result, right? So an extra space of n cross n for output matrix will be required. Hence the space complexity will be O n square space. Hey guys, welcome back. We have discussed a lot on backtracking. Now let's start to solve problems based on backtracking. So the first one we're gonna work on is n queens problem. The problem is you will be given a board of n cross n size and you have to put n queens in this board in such a way that they don't attack each other. Interesting. For example, if we place the first queen here and the second queen will be placed in such a way that it won't attack this first one. The first queen is at cell 0, 0 and the other queen is at 1, 2. So if you know the basic chess, the queen can move horizontally, that is in its right side, vertically in its left side, upside and downside, and it can move diagonally in all the 4 directions. But it can move one cell at a time. So these are the directions in which a queen can move. Keeping that in mind, let's see how we can solve this problem. We will be given n cross n matrix that is filled with value 0. What we need to do, we need to place n number of ones representing queen in non-attacking way. So to solve it, we need to think of 4 elements that we discussed in previous lecture. First is the choices. To place a queen in the board, we can either go row by row or we can go column by column. So here to place the queen 2, we have 4 choices. To place it in row 1 or in row 2 or in row 3 or in row 4. That's the case when we are going column by column. The other way can be you can place it in column 1 or column 2 or in column 3 or in column 4. These are the 4 choices we have for this queen. That's when we are going row by row. So these are the four choices when we are going row by row. That's up to you how you want to make these recursive calls. We're gonna go column by column. So the choices to put a queen in a column are four. Either we can put it in row 1 or in row 2 or in row 3 or in row 4. So these are the choices we have. Now coming to the second element is constraints. To validate if the current step is safe or not. So we'll check where we cannot place the queen. Basic constraints are if you have any queen present in horizontal, vertical or diagonal directions, you cannot place the queen at that cell. And as we will be going column by column, we don't need to check vertically. So we will validate if the cell is not facing the other queen horizontally and diagonally. So we cannot put it horizontally or diagonally. So the conditions will be like this. If we have any queen already placed to the left of this current queen, then we're gonna return false. We cannot place this queen there. And now we have to check diagonally. So if we are having any queen present diagonally to this current queen in the upper left portion, then we will return false. And similarly, if we have it in lower left portion, we are going to return false. In these two cases, when we are looking in upper left and the lower left, we are only looking if there is any queen placed diagonally to the current queen. And finally, if all these conditions return true, we can return true from is safe method because the queen can be placed at the current cell. Now the next element is recursion. When our choice is safe to be made, then we can make recursive calls to find the solution with the current choice. We saw the choices. For every column, we have rows as a choice to place the queen. We have 4 rows that represents 4 choices. Now, what if the choices do not work out? Like here, we can place the queen 1 here, and then we can place the queen 2 here in this column 2 at the 3rd row. And now what about this queen 3? We don't have any row left to place this 3rd queen because if we place it in this column anywhere or in any row, it will be attacked by some other queen. So in this case, any of the choice is not working out. So we will go back and revert our decision for the cell because putting the queen in the cell is not working out. So we will undo this decision by marking the cell with 0 and we will move on. This is called the backtracking step where we undo the current decision and we go back to our previous step. First, we are going to place the queen at the current cell by marking it with 1 and then we are going to go column by column by making the recursive calls. So we're calling the save the queen method and passing column plus 1 to it. If this choice is going to work out, then this method is going to return true. Otherwise, if somewhere it does not work out, then it's going to go back to this execution, this current stack frame, and then we are going to execute the backtrack move. So here it will undo our decision to place the queen at the current cell. For doing this, it will mark back the current cell with 0 and will return false to say that this cell is not suitable to place the queen. Now the next and the last element, which is the goal. The goal or the objective is to place the queens at every column at the proper place so that they don't attack each other. And from there you get your base condition, which is basically to reach at the last column and place your last queen. When this is done, our goal is accomplished. Then we can stop the recursion, right? So the condition will be if the column index exceeds or crosses the last column index, then return true. The last column will be n minus 1, so we have to stop when it becomes n. So we have to stop right at n. So let's shape all this in single frame. What we will do, for every column, we're gonna go loop over the rows, which are the choices, and by putting a constraint check, we will see if the position where we're gonna place the queen is safe or not. If it is safe, we do make recursive calls for the next column, and if it is not safe, we will be out of the loop and go for different choice from the previous column, which is the backtracking move. And finally, when we will cross all the columns, that means we have reached to our goal. So this will be the base case. Let's start solving it. We will be given a 4 cross 4 matrix filled up with zeros, and wherever we find the safe cell, we will update 1. Let's code the solution. So this is the n queens class, and we are given a board. It's a 5 cross 5 matrix having zeros. Now let's go ahead with creating and calling a method to place n number of queens on this board. So let's call it save the queens, and the first argument to this method is the board itself, and the second argument is the column index from where we're gonna start. We are going to start from 0th index. So we are taking column index as 0, and we're taking column because we're gonna go column by column. Now let's get the length of this board and let's call it n, and we are already passing this n in the save the queens method. Now let's start the main implementation. Let's create this method, and here let's start implementing save the queens. Let's change I to call because it's a column index, and now first comes choices. We have to find out the row for every column where the queen can be placed. So at every column, we have to make a choice between these rows. So we're gonna take a for loop that is going to start from 0 till the length. So row is less than n and row plus plus. So first, if we're going to place the queen at the current cell, we have to check is this placement safe or not. So comes the constraints. Let's check if is safe, and let's pass board, row, column, and n to this method. If the placement is safe, let's place the queen here, board, row, column, and here we'll place 1. Let's implement this is safe method. So first we will check if there's any queen already present horizontally to the current queen. So let's take a for loop. Let's take two variables I and j, and this loop is going to start from 0 and will go till the current column, so less than column, and will increment the I. So in the left of this current placement, we have any queen present horizontally that we can check by saying board row I equals to 1. If this is true, then return false. That means there is already a queen present horizontally to the current queen. Now we have to check diagonally. First we will check for the upper half. So we'll take I will start from the row, and the j will start from the column, and they will go until they are greater than 0, greater than equal to 0, j and j is greater than equal to 0. I should also be greater than equal to 0, and then we'll decrement the I. So we are going diagonally. So if the current placement is 1, 2, then the previous placement will be 0, 1. So it is going diagonally. So here we'll check if there's any queen placed diagonally in the upper half. So bold I and j equals to 1, and then return false. And now we have to check in the lower half. So let's copy this for loop. This time we're gonna go diagonally downwards. So I will start from row and it will go up to n. So increment the I, everything else will be same. Oh, we are having a semicolon here. Let's put a comma here. And finally, if all these conditions fails, then we will return true. Now the next element is recursion. If we are placing the queen at the current cell, then we are going to check if we can place any queen in the next column at any row or not. So let's call save the queens and let's pass the board, and as we're going to check for the next column, let's pass column plus 1 and then the value of n. So if it returns true, then return true. Return true. But if this does not work out, we have to revert our decision back to 0. So now comes the backtracking step. So backtrack and let's change the value from 1 to 0 again. So row column equals to 0. And after everything, return false. Now comes the base case. Base case is when we reach to our goal, that is when we have traversed all the columns. So the base case is if column is greater than or equal to n. When it becomes equal to n, then return true. So this is the implementation to save the queens method. Now the implementation of the logic is complete. Let's get back to the main method, and here if the save the queens returns true, then we are going to print the matrix. So if this is true, then print the matrix. First take the for loop for rows, which will go till n, and now the for loop for columns. So j equals to 0 till n j plus plus. And now let's print the element. Separate by space and bold ij and space again. We'll be getting error. Let's change it to small j and remove this 0. And then after the for loop of column, we'll change the line. There's another error. Okay, let's insert this parenthesis, and now the else condition, else the save the queens is returning false, and there is no solution to this problem or to this for this board. Change it to print. Now let's run this. So the solution has placed all the queens at right positions where they are not attacking each other. And this is how we can solve this n queens problem using backtracking. This was all for this lecture. See you in the next lecture. Now let's analyze the complexity for n queens problem. For every column, we are traversing through n rows to check the possibility to place the queen. So the maximum branching factor is n, and the depth of the recursive calls will also be n. So the complexity will be n raised to power n, which is the upper bound. However, if we go deeper and see, the recursive call will happen for the remaining n queens only. Like after placing the first queen, we will be having n minus 1 options to place the others. So this recursive part is going to take n t n minus 1 time. And considering the isSave call, that will run for n times for n columns, so the time complexity will be order of n square for this. And if we solve the equation, the recurrence relation, which is Tn equals to order of n square plus ntn minus 1, we gonna get Tn equals to On square On minus 2 factorial, which is approximately or almost equal to n factorial. So it is having order of n factorial complexity. That's pretty bad, but generally backtracking is used when we need to check all the possibilities to find a solution, right? Hence, it is expensive. Now, the space complexity. There will be n recursive calls at a time on the call stack, so complexity will be linear. Here, you might think that for n cross n board, it will require On square space, but that isn't actually the part of algorithm. In algorithm complexity analysis, we analyze how much auxiliary space our algorithm will consume. And our algorithm isn't consuming any additional space. The board is already given to us, so we are not including it in the analysis. So the space complexity will be order of n. Hey guys, welcome back. The next problem is Knight's tour problem. In this problem, we are given n cross n chessboard and a knight. A knight in chess can move 2 squares vertically and 1 square horizontally. Or it can move 2 squares horizontally and 1 square vertically in all directions. So this is how a knight can move on the chessboard. Now the problem is we have to make this knight visit every cell of the board exactly once. That is, the knight must cover every square and can move to the next square only once. So for this problem, we will be actually given n cross n matrix similar to n queens problem filled up with 0. Let's see how we can solve this problem using backtracking. To solve this, let's think of the 4 elements again in context of this problem. First is the choices. As we saw, we have maximum 8 possible moves for the knight. So the 8 moves that this knight can make are these. These are the coordinates for these 8 cells where this knight can be placed. So these are the choices. Now the next element is constraints. To validate if we made the right choice, we need to think of the constraints that we have in for the problem. So for this problem, the only constraint is that knight can move a cell only once. The knight here can go to all the possible cells, but not the cell which it has already visited. Other than that, it cannot move out of the matrix. Therefore, the move is valid only when the row and columns are within range and value of the cell is 0. So it cannot be placed at a cell which is already visited, and it cannot be placed outside the board. Now the next element is recursion. With choices, you make a decision, and with that decision, you check if you can find a solution or not by making further recursive calls. So we continue to make decisions by making these choices, which were to move in any of these possible directions in this matrix. Knight can move to these 8 directions, but if all these choices fails, if going forward these recursive calls returns false, then we go back to the current stack frame and we undo our decision. This is the backtracking step, and then we go forward with other available choices. So first we place the knight at the current cell and then we decide the next cell recursively. If the choice does not work out, we backtrack and reset the decision or undo our decision. Now the last element is the goal. The goal is to find the path that knight takes to visit each cell exactly once. With that, you get the base condition, which is to complete all the steps n multiplied by n minus 1 steps. So when the step is 63rd, as we started from 0, we return true and print the solution. Alright, let's have a look on the merged code snippet to solve the problem. We loop through every choice and we update the row column as per the choice. Then we apply the constraint. If the selected move is valid, we increment the step and update it on the cell. Then we do make recursive calls by passing the current row column and the step and check if with the move we can achieve the solution. If we cannot achieve the solution, we step back and update the cell again with 0. That's the backtracking move here. And at last we reach to our goal, which is the last step. So this is how we can achieve the solution. One thing to address here is that we will update the row and column as per the coordinates that we saw in the choices. To go through each choice, we will take two arrays having row and column path coordinates. By iterating through these arrays, we will make choice and solve the problem. So let's get started. So we are given 8 cross 8 board and we've already created path row and path column, these two arrays for the choices. So these are arrays for the choices. If we are going to go 2 steps row wise, then we'll go 1 step column wise. And if we're going 2 step column wise, then we can go 1 step row wise. So these are the 8 moves that are possible from each cell. Now let's create the method night tour and let's pass the board and 0, 0 and 0. First 0 is for row, second is for column, and the last one is the step count. So let's implement this method. Let's call it row and let's call it column and let's call it step. So first we have choices. So let's take a for loop. This will go till path row dot length. Here inside this for loop, we will take new coordinates where we can place the knight. Let's say new row, oh, new row, and the new row will be row plus path row, and we'll pass the index I. Okay, and same for the column. This will give us the coordinates for the new cell where we are going to place the knight. So column plus path column and we'll pass the index. Now comes constraints. We will check if the current move is valid, then we will move forward. So let's call is valid move and let's pass the details in this method. Pass the board, board, new row, new column. And if this is a valid move according to the constraints, we will increment the step and we will place the knight at the current cell. How we'll place the knight at the current cell? We'll just write the current step number at the current cell. Let's implement this method. And here, what are the constraints? If row must be greater than or equal to 0 and row must be less than 8. So this is the constraint for row. And similarly for column. And for column, let's copy this and do same for the column. because the column also must be within this range. And the final condition is that the cell must be having value 0. So board, new row, new column. The cell must be having value 0. Then we're going to return true. Else we will return false. So let's write it this way. Let's return, and that's it. It will return true if all the conditions are satisfied. Now coming to the next element is recursion. So we're gonna call this night2, this must return boolean. So if, and let's call night2 recursively and pass all the required parameters. So first let's pass the board, and now the new row from where we are going to go forward, and the new column, and the updated step count. If we can go forward, return true, else step back and revert our decision. So now comes the backtracking step. So we're gonna backtrack and we will update the values back. So we'll decrement the step again to the initial value or the previous value, and now the value for the current cell. Let's update it. And this is small n. So after doing all this, let's write the last line to return false. And now comes the base condition. Base condition is when we reach to our goal, which is when the step count reaches 63, because this board is having 64 cells. So the last count we can reach is 63 as we're starting from 0. So when we reach to 63, we'll print this board, the updated board. So let's loop over the rows and now loop over columns. For both row and column, we are taking board.length. We're going till board.length because it's a square matrix. Now let's print the elements. So board ij, this should be print, and after this for loop, let's change the line, add a line, and then return true. So this is the complete solution to the night2 problem. Let's try running it and see what we get. So it prints the matrix having all the steps. It is starting from 0. The night starts from 0 and then it goes to 1. Then this goes here and then here, and finally it reaches this cell with step count 63. So this is how you can code night2 problem. Now let's analyze the complexity of night2 problem. So for this problem, we have maximum 8 choices to make from every cell, right? And there are total n square cells in this board. So we can say that the worst case runtime will be 8 raised to power n square. So it's order of 8 raised to power n square. Now for space complexity, in worst case, the function can get called for n rows and n columns at a time. That means the call stack may have n square recursive calls at a point in time. So the space complexity is order of n square. Hey guys, welcome back. The next problem is Boggle problem. In this problem, we will be given a matrix or a board of characters. Each cell has one character and we will be given a dictionary or a set of words. Now the problem is to find out all the words that can be formed by sequence of adjacent characters and which are present in the given dictionary. In order to look for the words, we can move to any of the 8 adjacent characters except the one which we have already taken in the sequence. Here for A, we cannot move again to F as we've already taken it in the sequence. So that's what the problem is about. Let's see how we can solve this problem using backtracking. To solve it, let's think of the 4 elements again in the context of this problem. The first is choices. At each letter we have 8 choices. Any adjacent cell can be chosen, and these are the coordinates of these 8 adjacent cells, which are the choices for us. So these are the choices we have. Next element is constraints. Now to validate if we made the right choice, we need to think of the constraints we have. One of the constraints is that we cannot go to the letter which we have already taken in the sequence. For example, here we cannot move to letter A and F from C because we have taken them already in the sequence. And also we cannot go outside of the matrix. So these are the constraints we have. To implement it, we will take a matrix with same dimension to keep the track of all the visited cells. Initially it is filled up with zeros, and as soon as we start to take cells in the sequence, we update the corresponding cells with 1. So the cell can get included when it is in the range and when the value of the cell is 0. So the cell can get included when it is in the range and when the value of the cell is 0. Now the third element is recursion. With choices, you make a decision, and holding on to that decision, you go forward and check if you can find the solution or not. So we keep making choices and form the word by including the letters recursively. Now the case when you don't have any choice left to go with. Like from this O, you cannot move forward anywhere. In that case, we need to discard the current move. That is, we have to go back or we have to backtrack and think of other choice. So what we do, we try to find the word starting from every character. We start from the first letter of the vowel and update the corresponding cell in the visited matrix with 1. So we append the first letter to a blank string, then we trade through the choices we have. Now with the updated row columns, we check if the cell is valid or not. If it is valid, we recursively search for the word with these updated cell coordinates. So again, for the next call, it will mark the cell as visited and include the letter in the word. Now if the cell is not valid to go, we will again mark the cell as unvisited. So if we don't find word with current decision, we backtrack by updating the cell with 0 again. Now the last element is goal. What is the goal? Goal is to find words which are present in the given list. So we check if the formed word is present in the given dictionary or not. If it is present, we'll print it. We don't have any specific base condition because we will be doing this job for each letter present in the matrix in a for loop, and also we'll be having more for loops inside the method to make combinations with other adjacent letters. When the work for all the letters will complete, we will be having no more valid places to take letters from, and the program will eventually terminate. So this is how we're gonna solve the problem. We will mark the cell as visited when we will include the letter in the word. We'll loop through the choices and select one if it is satisfying the constraints. We recursively try to find the word. If there is no choice left, we will update the cell again with 0. That is the backtracking step. And on each recursive call, we will check if the formed word is present in the dictionary or not. If it is, we're going to print it. That is the goal. And in order to find other words, we will continue to search and make recursive calls. So let's get started. So we have a dictionary or a set of words that we're going to find out from this boggle. And I've already taken the dimensions as constants. You can also find it from this 2D array or from this matrix boggle. So now to find the words present in this dictionary, we will start from a letter present in the boggle. And starting from that letter, we will try to find out that word. If going forward can make a word present in this dictionary or not. So let's call find words and let's pass this boggle in this find words. And now to keep track of already visited letters, we will take another matrix of same dimensions. So int visited, new int array of dimensions m cross n. And let's pass this visited matrix in this find words. And now as we are going to start from letters present in this boggle one at a time, so we're going to do this stuff inside a for loop. So first for loop will be for rows. So I starts from 0 till m, and then another for loop inside this for columns. J starts from 0 till n, and let's invoke the find words within these loops. So now we're passing boggle and visited to this find words, and now let's pass I and j and the string str. So initially the word will be an empty string, so let's pass the empty string. And then inside the method we will take letters one by one from this boggle. And find words, create this method. So initially for the first word we will set the visited cell to 1 to indicate that we have already traversed or taken this word. So let's set it to 1 and let's include that word. So word, let's change this. This will be word plus string. So the word plus the first letter present in this boggle. So as we've already included the first letter present in the boggle in the string, that's why we are marking the cell as visited. Now we will check if the formed word is present in the dictionary. If the dictionary contains the word, then we will print that word on the console. So sys out word. Now to form a word, we have to keep including the letters to form a word. And to include a letter, we have 8 choices. And these 8 choices are the 8 adjacent cells to that letter. So for this, we're gonna again need loops. First loop is to cover the rows. So we can move one step backward and one step forward row wise. So we can start it from I minus 1 and it will go till I plus 1. I plus 1 equal to I plus 1. And now similarly for columns, we can go one step backward column wise and one step forward column wise. So rows columns start from j minus 1 and goes till j plus 1. So this loop will cover all the adjacent cells to that letter. And now here comes the constraints. So before calling this find words method recursively, first we need to check the letter for which we are calling this find words satisfies the constraints or not. So let's implement this as visited method. Create this method. And here the constraints are the letter, for the letter the row must be equal to or greater than 0 and it must be less than m. And similarly for columns, the column where the letter is placed, it must be greater than or equal to 0 and it must be less than n. Call must be less than n and uh, and the letter must not be already visited. So here pass row and column, this must be equal to 0. So if the letter is inside this 2D array dimensions and is not already visited, then we can call the find words to include this letter recursively. So let's pass boggle, visited, row, column, and the word. Now if this recursion don't work out, we have to backtrack and we have to revert our decision, which is only when the letter does not satisfy the constraints. So in that case, let's revert our decision and mark back the cell with 0. And with this, the solution to this problem completes. In this example, we're not having a specific base case because we're doing everything inside of for loops, as we are running for loops to go through each letter, and we have also taken for loops to traverse through all the choices, and a method which is also working as a terminating method, because when we are left with no choices or when all the cells gets visited, we will eventually get out of the for loops. So this is the implementation. Let's run this. Oh, this must be blank string. So let's run this and see. So these are the words which are present in dictionary that can be formed in this boggle. So this is ray and fake and books. Now it's time to analyze the complexity of word search problem. So in word search problem or in boggle problem, we have maximum 8 choices to make from every cell, right? As we are forming word by including every adjacent character one by one. And these are m cross n characters present in this boggle. So we can say that the worst runtime will be 8 raised to power m cross n. So this will be the time complexity. Now talking about the space complexity. Space complexity will be order of m cross n, which is the max number of recursive calls happening on the call stack at a point in time. Hey guys, welcome back. So let's quickly summarize what we learned in this section. So this section was on backtracking, right? This is the design technique which is an extended form of recursion but with some special properties. The problem that falls under backtracking are the problems where we need to take our design back. It means we can change the decision at runtime and take a step or multiple steps back, right? So these type of algorithm design techniques are very useful if you're into game programming. What we learned? We learned what is backtracking, how we can identify backtracking, how we can approach problems on backtracking, and we tried solving some of the problems on backtracking. I hope after solving some problems, you might have gained better confidence to take on these kind of problems by yourself. Try solving some more problems on internet that can be solved using backtracking, and we will see you in the next section with next design technique. Hey guys, welcome back. So here comes our next algorithm design technique that we are going to cover in this section. It is divide and conquer. A lot of problems can be solved using this technique, and these problems can be solved optimally. We will see how we can identify and approach problems on divide and conquer. In this section, also we'll solve some classical problems to practice divide and conquer. We have handpicked these problems, so please code along with us, and I'm sure by the end of this section you will start feeling quite confident in solving these kind of problems. So let's start learning this technique from next lecture. Hey guys, welcome back. So it's time for another design technique, and this is not a very natural to your brain and may not come to your mind immediately if you don't know the title of the technique. So, as the name suggests, the divide and conquer technique solves the problem by dividing problem into little subproblems and conquering those subproblems by solving them with any approach. So let's try to understand this with a very simple example. Suppose you're given a sorted set of elements and you need to find one particular element in this set. So the first approach that would come into your mind will be start to search elements by going through each element one by one and comparing that to the current element. But the worst case complexity of this approach will be O (n). Now with divide and conquer, we can do it with better performance. What we do, we divide the set into half, and then we compare the middle element with the given element that we need to find. If the given element is greater than the middle element, that means we need to find it in the right subset by again dividing it into the subsets. Similarly, if it is smaller than the middle, we search it in the left subset, and when we get it equal to the middle element, we finally find the position of the element. So with this approach, we reduce the complexity. It gets O log n, as we're eliminating almost half of the elements at every iteration. So to sum up, divide and conquer technique divides the problem into small, easily solvable parts, and then we conquer each of the subproblem, that is, we solve each of the subproblem, and then we combine the results together for a global solution. But some of the problems may not require the combined step. Dividing and conquering may solve the complete problem, but again, that's a problem specific thing. We'll learn more as we'll start solving problems. So time complexity can be improved significantly using this technique. Even if you are working in a multi-threaded or multi-core processing environment, subproblems can be passed on to multiple servers or threads, and then results can be combined. MapReduce algorithm is also a special form of divide and conquer that is used heavily in big data environment. So I think you might have got a decent idea by now about divide and conquer technique, and you will be more comfortable when you will solve some problems along with me in upcoming lectures. Hey guys, welcome back. Before we start solving some of the problems related to divide and conquer, let's discuss some tricks to identify if the problem can be solved using divide and conquer. So for identification, we have these points. Divide and conquer can be applied only when each problem may generate two or more subproblems of same kind. And that can be solved recursively and can be combined back for a global result. Some of the examples are merge sort, where subproblems result can be combined back for the global result. Quicksort, that gets solved by dividing and conquering the subproblems. Binary search, however, this more specifically comes under decrease and conquer because there is only one subproblem. We will implement merge sort and quicksort in upcoming lectures. Now coming to how to approach if you identified that you should apply DC, that is divide and conquer. So how are you going to approach the problem? Approaching divide and conquer can look a little tricky in first shot, but below steps can help. So divide and conquer. Given a problem of size n, divide it into a subproblems of size n divided by b, where a must be greater than 1 and a must be greater than or equal to 1 and b must be greater than 1. And then solve each problem recursively, which we call the conquer step. We are going to do it recursively until it becomes really small or almost constant. This is called multi-branch recursion. Now the third and the last step is combine the solution of subproblems into an overall solution. So these are the three steps, and there is a relation called recurrence associated with divide and conquer that will help us to calculate the complexity for our algorithm. So it is Tn equals to A Tn divided by B plus work done to combine and merge all the subproblems back. So you are dividing a problem having size n into small problems having size n divided by b each, and the number of subproblems are a. So the complexity of the complete solution or the complete algorithm is equal to the addition of complexity of all the subproblems and the work done to combine and merge all the subproblems back. So we will discuss more about recurrence when we will discuss the time complexity in divide and conquer, because defining the time complexity of divide and conquer can be a little tricky. So I think by now you are ready to solve some of the problems related to divide and conquer. So let's move on from the theory and start doing some code from next lecture for some interesting related problems that will actually make you confident about this approach. So see you guys there in the next lecture. Bye-bye. Hey guys, welcome back. In this lecture, we are going to understand how we can sort elements present in an array using the merge sort algorithm. Merge sort is a fundamental example of divide and conquer algorithm. And also, it's a very famous sorting algorithm. In merge sort, what we do, suppose we have an array, we divide it into two halves, we get two individual array, and we do the same to them, that is, we again divide them in halves, and we keep on doing that. So when we are going to stop, we will do it till further division of array can no longer take place, and this happens when you reach single element arrays. So then we cannot divide it further. Let's see exactly how this happens. For the given array, we have a lower bound, which is the index from where the array starts. Obviously, it is 0. And we also have upper bound, which is the last index of the array. Here it is 6. Now to divide this array into two halves, we need a mid value, where we can partition this array. We can calculate this mid value by adding the lower bound and the upper bound, and then dividing the value by 2. This will give us an int value. In this example, it will be 0 plus 6, 6 divided by 2, so we will get 3. So this is the mid index. So the first array will start from the lower bound to the mid index, and the second array starts from mid plus 1 to the upper bound. So for this example, the two array we get are 1 from 0 to 3 and the other one from mid plus 1, which is 4, to the upper bound, which is 6. So this is how we're gonna partition the array. But what if the upper bound is an odd number? Let's say if it is 7, then how are we gonna partition the array? If the upper bound is 7, then the mid index we will get will be 0 plus 7 divided by 2, which will be 3.5, right? So after rounding off, we will get 3. So the first array will start from 0 till 3 and the next array will start from 4 till 7. This is how we will partition the array. So here you can see these are the two calls we are making to partition this array. And after the partition, we are getting two arrays. Both are having their own lower and upper bounds. So further partitioning of these produced subarrays will be done by these recursive calls. We don't have to do it, we just partition them once for the first level. So this was the first step of the divide and conquer algorithm, where we divide the task. And this involves recursion to do that division till we reach a certain base case to stop that division or to stop that recursion. And the base case is when we only have a single element in each array, which is when the lower bound and the upper bound index becomes the same. So we divided the problem into subproblems, and then we did everything recursively for those smaller subproblems to get to the very base values. The smallest subproblems are just single elements, they are just constants. So we covered the divide step and the conquer step. Now the most important step of merge sort algorithm is the combine step, because it's having the core logic that how we actually gonna sort these elements. So when we are solving the divide and conquer algorithm for different problems, then sometimes the division into subtasks might require the core implementation, and some other time it may be the combine step that require the core implementation to solve the problem. And this you can see with this merge sort algorithm, where the combine step requires the core implementation to solve the problem. And the divide and conquer step were really straightforward. So how this combine step is to be done? How we are going to combine all these arrays? If we are merging these two subarrays, then this must be an array having 9 and 17. So 9 will come first and then 17. And then if we are merging these two arrays, then the output will be an array having elements 5 and 33. Similarly for these arrays, so we merged all the list having single elements to a list having two elements. Now merging these lists having two elements into four elements will result to these lists or to these arrays. One having elements 5, 9, 17 and 33, and the other having elements 7, 11, 19 and 25. And this should be the result, and this is how this algorithm should work. So at this point here, let's understand how we can merge these arrays back into a list having all the elements in ascending order. Let's say the first array is named A and the other one is B. And this will be the merged array or our much awaited solution. We're having a pointer I at the first element of array A. We have a pointer J pointing at the first element of array B, and a pointer K using which we're gonna fill up the elements at the correct index in the solution array. So let's start. The element at ith position in array A is 5 and the element at jth position in array B is 7. We're gonna compare both the elements and we will put the smaller one in the solution array. Fair enough? So now the kth position is filled. So let's increment the k and also increment I by 1, as we've already picked 5 from A. At this instant, J is still at 7 and I is on 9. Again, we compare these two and find out that 7 is smaller one. So we pick it and place it at kth position in the solution array. Again, we increment the k, and this time we increment the j. Again, check for the smaller one and proceed. So this is how we're gonna merge two arrays into a single sorted array. So I gonna go all the way up till the middle index m, and j is going to go till the upper bound. And then check for the smaller one from a and b at its ith and jth index respectively. If the element at index I is smaller, then put it in the solution array and go ahead by incrementing the I. Else, put the element at jth index of array b into the solution array and increment the j. And after putting the element in the solution array, increment the k. So I hope you got it. But this solution is not complete yet. Think of the case when the length of these two arrays are not same. One might be smaller than the other one. For example, array A is only having 2 elements and B is having 4 elements. Then what? So we need to cover this case as well. If the pointer I reaches to the middle index or to its limit, then we just need to get the remaining elements of B just by incrementing the J. No comparison, we go straight. And same is true if J reaches to its limit and I is still stuck there with more elements next to it. So if any of these two conditions fails, then check if there are more indexes to be traversed by I. If yes, get all the elements one by one just by incrementing the I and k. And also do the same for J. Now the solution is complete. So let's have a code walkthrough to the solution. Let's start off by creating an array. So int array, call it ARR, and let's insert some values in this array. 11, 6, 3, 9, 14, 66, and let's say 2. So now let's call the merge sort. Merge sort, this method we are going to create. So let's pass array and the lower bound, which is 0, and now the upper bound. So let's create a variable to hold the length of this array. ARR dot length. And now let's pass the upper bound, which will be length minus 1. Let's create this method, and here this I here will be the lower bound. So let's replace it with L, and the J is the upper bound. So let's replace it with U. If the lower bound is less than upper bound, so if L is less than U, then find out the middle element or the middle index. So to calculate the middle index, we will add L and U and then divide the value by 2. And now we will call merge sort to partition this array into 2 halves. So first pass the array. The first array will start from L till M, and the second array, let's call the merge sort for the second one, and pass the array, and it will start from M plus 1 till U. This will keep dividing the arrays until we get single element arrays. And then we will start merging them. So let's create a method merge that will merge 2 arrays into one array, 2 subarrays into another subarray until we get to the final array. So let's pass array and the lower bound, and the mid index and the upper bound. Now let's create this method merge. So in this, we are going to merge two subarrays, right? So let's create two subarrays first. The one having, let's say, length n1 and the other one having length n2. So let's take n1 and this will be m minus l plus 1. So this is the length of the first array and n2 is the length of the second array, which is upper bound minus m. Now let's create these arrays with these sizes. So int l new int of size n1. And now the other one, let's call it int r of size n2. We have already taken L, so let's replace it with left and let's call this one right. So now let's copy the data to these temporary arrays. Let's take for loops. This first one is, let's say, starting from 0 till n1. And let's insert the elements in this array. So li or left I equals to arr l plus I. In the merge sort method, we are calling merge sort twice, but we're not collecting the data actually in two different structures. And here we are doing that. So we are getting all the data that is related to the left part, left partition into the left array, and the data belonging to the right partition into the right array. So right, it will be arr m plus 1 plus j. And now we are going to merge these temp arrays. So let's take the pointers. Int I starting from 0, int j starting from 0, and k starting from the lower bound. So k equals to L. Now a while loop. While I is less than n1, and j is less than n2, just the case. And then we're gonna check which one of the element in these two these two places are smaller. So li is less than right j. So if the left one is smaller, then add this element at ith index to the array k. Increment the I, else we will pick the element from the right subarray. So arr k equals to right j. And then let's increment the j. And finally, after placing the element at the right position, increment the k. Now the two cases when one of the array completes but there are still elements in the other one. So if I is still less than n1, then put all the remaining elements of the left array in arr. So left I, keep incrementing the I, and also keep incrementing the k. And now same for j. If there are still elements left in the right array, if j is less than n2, then get all the elements from the right array and put them in this solution array. So write j, increment the j, and increment the k as well. And with this, we have implemented the merge sort algorithm. Now we just need to print the elements of this array, the solution array. So let's come back to our main method and let's take a for loop that will iterate over this solution array and will print it. So we've already taken it in a variable, and now let's print the elements sys out and arri and give some space. And now let's run this program. Let's have the console view and see we're getting all the elements in sorted order. Now let's analyze the complexity of merge sort. Let's first talk about time complexity. So the operations we have are we keep dividing the array into two halves until we reach to the base case, and we keep merging these halves upwards to construct the complete array or to construct the complete list, right? So how many divide operations it's gonna take to reach to the base case? We are dividing the arrays in halves, right? At each step, we are dividing the arrays in halves. So this is gonna take log n time to reach the base case. For example, if you have 8 elements in the array, then it's gonna take log 8, that is 3 divide operations. After the third operation, you will be on the base case. So if you're having an array or a list of 8 elements, then it will create 2 halves having 4 each, and then it will create 4 arrays having 2 elements each, and then will create 8 arrays having 1 element each, right? And if you are having 16 elements, then number of operations will be log 16, that is 4 operations. You will start with 16, then you'll get arrays having 8 elements each, then 4, then 2, then 1. And here you can see that right after the 4th operation, you are at the base case. So dividing the array till the base case will have log n complexity. Now let's talk about the merge operation. At each level, we are having n number of elements to be merged. However, not all at once each time. Still, as a whole, at each level, it's gonna consume order of n time. If you see here, when you reach to this step, merging all the lists below, here you will be having 4 elements in the first list and 4 elements in the other list to be sorted and merged to generate the original list. So in this list, you have to go through 4 elements, which is actually n divided by 2, and the same is true with this other list. You have to go through 4 elements, that is n by 2. So total of n elements to make the result. Similarly, at all the other levels, you're doing the same. If I talk about the levels just before it, here we are doing the same. We are merging 4 lists of n by 4 length each to make up these 2 lists of n by 2 lengths, thus again making a total of n. So at each level we are doing the same. We're getting a total of n. That's why the complexity will be order of some constant multiplied by n. And after ignoring the constant factor, we will be having complexity, time complexity order of n for this merge operation. We can verify this using the recurrence relation. The recurrence relation for this will be 2t n divided by 2 plus on, which will result to on log n time. Here in this recurrence relation, we are having 2 recursive calls of n by 2 size, and we are having n as the complexity for merging the subarrays. So this will give us O n log n. You can solve the recurrence relation using the substitution method explained in the recurrence relation section to verify this time complexity. Now let's talk about space. So we are creating two temporary arrays to store the numbers of original array in the first call, and then we follow that and we keep creating the arrays to store the elements. We are storing n number of elements at each level, right? So this will be having order of n space. Hey guys, welcome back. Let's get to the next example for divide and conquer algorithm, and it is quicksort algorithm. In this algorithm, we perform sorting by choosing a key element that is called a pivot, and we partition the unsorted array around this pivot such that all the elements which are smaller than the pivot gets in the left, and elements which are greater than the pivot gets in the right side of the pivot element. And if it is equal to the pivot, we can move it either side, left or right. And then we continue to choose pivot and perform partitioning until all elements get sorted. For example, see this is an unsorted array. You choose a pivot element, which can be any of the element, any one element present in this array. It can be first element, it can be last element, or it can be a middle element. You can choose any element. So let's choose 10 as the pivot. Now you perform partitioning around this pivot number, or you can say you rearrange the elements present in this array such that you have one partition having all the elements smaller than this pivot, and a right partition having all the elements which are greater than this pivot. So according to this arrangement, 10 gets the third index. And now we say that this index is the appropriate place for this element. But as you can see, still left partition and right partition are not sorted. So again, we apply this whole thing to these generated partitions. We choose a pivot. For the left partition, the pivot is, let's say, 8, and for the right partition, let's choose 90. And then again rearrange the elements by comparing them to the pivot. But still we're not done yet. We have unsorted partitions, right? So we again do this, and this continues till every element gets placed in array in sorted manner. So this was the whole idea of the solution. Now let's think of the approach to achieve the solution. First, how we actually gonna divide problem into subproblems. This is much different than how we do in merge sort. In merge sort, the divide and conquer both steps are very straightforward. But in quicksort, we need to divide problem bit smartly, as the core logic of entire quicksort resides in this step. So pay attention, this is the most complicated part of the algorithm, so the algorithm will make more sense if you understand this logic. So let's see how technically we do this. So here let's pick 10 as pivot. We're gonna take two pointers, left pointer and right pointer. Left is at the leftmost element and right is at the rightmost element, right? Now we will compare left pointer element with the pivot independently. If it is less than or equal to the pivot, then the current element is already placed at the right cell. And we don't do anything, and we move on by incrementing the left pointer. And then we go to the right pointer and we compare the element present at this place with the pivot. If it is greater than the pivot, then we are good. The element is at its right place. And then this right pointer moves towards the left. So you're getting it? Left pointer goes towards right and the right pointer goes towards left. But for this example, see the value we're having at the right pointer. It's 0. So if we compare it with the pivot, which is 10, we find that this value 0 is smaller than the pivot. So now the right is stuck here. The right pointer is stuck here. We cannot make a move with it, but we can go back to the left pointer and check out the value present at that pointer. So see, the value is 1 and it is smaller than the value 10. So we can make a move. We can increment the left. Now it is at 67 and the right is still stuck at 0. So again, check for the element present at the left. This time the value present at the left pointer is greater than the pivot. 67 is greater than pivot. Now both the pointers cannot make further moves. That is, if the left gets higher element than the pivot and the right gets lower than the pivot, we know elements are out of order. So we need to rearrange them. And that we do by swapping them with each other. So let's swap them. Now the elements get the right place with respect to the current pivot element. And now let's resume with what we were doing. Compare the element with the pivot and make move accordingly. Then there comes a point when the right pointer crosses the left pointer. And this is when we are done with the current pivot. At this point, it's time to perform partitioning. And that we do by replacing the value present at the right pointer with the pivot element. So one iteration is complete. Once this is done, you will see the partitions at either side of this pivot. All the elements at the left to this pivot are smaller than the pivot, and all the elements present at the right to this pivot are greater than this pivot. Now, still this array is not sorted. We have now two more arrays or two arrays from this array. And again, we are going to do the same with these arrays. So we conquer by recursively performing partitioning of the subarrays. Here you can see the first array is from 0 to 2 and the second partition is from 4 to 7. So this is the core partitioning logic. Function will have array, lower bound and upper bound as input parameters, and we will always take first element as the pivot, which is present at the lower bound. Left is the first and the right is the last element. Now we will increment the left pointer if left pointer element is smaller or equal to the pivot and when left pointer is less than length minus 1, because it shouldn't go out of the array bound, right? Now talking about the right pointer, we will decrement the right pointer if element at right is greater than the pivot, and we'll also check right is greater than 0 or not, because we don't want to go out of the array bound. And then if both the pointers get stuck, that is, if we're not able to make pointers move to right and left, then we must swap them because the elements are out of order. But again, before swapping them, we must verify that left pointer should be smaller than the right pointer. And this whole process will be repeated until we go through every element. That is, until when left pointer is smaller than the right. But the moment the right pointer crosses the left pointer, we again have to perform swapping because now the process for current pivot is complete. So we swap the elements present at the right with the pivot element as to get the pivot at its correct index. And then we finally return pivot index for the current iteration. Now next step, we conquer by recursively performing partitioning of the subarrays present at either side of index 3. Like here, 10 gets the place at 3. So the partition function returns index 3. So the next recursive call will be for subarray from 0 to 2 and the subarray from 4 to 7. Again, for these, the same process will be continued. Partition returns 2 as 8 get placed at index 2 and 90 gets placed at index 7. Again, for these, the same process will be continued. This continues till we left up with subarrays of single element or no element at all. And finally, each element will get its correct place in the array. So this is how the algorithm works. See the code snippet. This partition function after the execution returns the index of the pivot for that iteration. So we get the index. Now we know either side of the index we have the partitions. So first partition starts from the lower bound to index minus 1 and the second partition starts from index plus 1 to the upper bound. So this is how we're recursively calling the quicksort function for the partitioned arrays. We're going to recursively perform this implementation till lower bound is less than upper bound. Now the last step, which is combine. As you've already seen, once the conquer step recursively sorts all the subarrays, all elements get sorted at the end. That's because we're not creating different array for partitions. Rather, we are just rearranging elements in the same array considering the partitioning indexes. So let's start writing the code for quicksort. Let's take array with few elements and now let's call a method called quicksort and let's pass the array lower bound which is 0 and the upper bound which will be the length minus 1. Let's create this method and here I and j are lower bound and upper bound respectively, so let's replace them, lower bound and upper bound. Now inside this method, let's take index where we will store the index of the pivot. So if the lower bound is less than upper bound, then we are going to call the partition method partition and we're going to pass the array and the lower bound and upper bound to this partition method. This will give us the index of the current pivot. Let's create this partition method. So here while let's take pivot and we are going to take the first element as a pivot each time, so it is the element present at the lower bound. Left is also the first element at the first element which is the lower bound and right will be at the upper bound. So we have taken the pivot which is the element at the first place and we have taken 2 pointers left and right. So when the left pointer is smaller than right pointer, we will do some stuff. So here while left is element at the left is smaller or equal to the pivot, and also if left is within the array bounds, that is it is less than the array dot length minus 1, that is the last index, then we are going to increment the left pointer. And same if right is greater than the pivot, value at the right is greater than the pivot, and if the right is greater than 0, that is it falls within the array bounds, then we are going to move towards the left, right? So we will do right minus minus. This is upper bound. So now when left and right pointers are stuck, That means the elements are out of order, so we must swap them. So let's swap them. Let's take a temp variable and let's put the left element here in this temp, and at the left place let's put the element present at the right, and at the right place let's put the element present at the left, which we have in temp. But before doing this we must check that left is less than right or not. If it is less than right, then we are going to swap these elements. So after doing this whole thing, the current iteration is complete. The last step is to swap the lower bound with the element present at the right index. So let's swap them. So let's again take a temp and let's put the value present at the lower bound, which is the pivot, and now at lower bound put the value present at the right pointer, and at the right pointer put the current pivot, which is present in temp. Now the current pivot comes to right index, so we are going to return this index from here. So after returning this index, this partition method is complete, and now this is the index where we have to perform the partition. So at either side of this index we will be having two subarrays, and again we are going to do this whole stuff with those arrays. So first array starts from lower bound till index -1, so passing the index -1, and the second array, let's pass array, it starts from index +1, goes till upper bound. So this is the complete implementation of quicksort algorithm. Now the last thing we have to do is to print the elements of the sorted array. So let's take a conventional for loop, and here let's print all the elements, all the sorted elements, by writing ARRI, and let's give some space here. So now the implementation is complete. Let's run this program and see the output. So this is the sorted output we are getting after applying this quicksort algorithm. It was very simple. So now let's talk about the worst case complexity. A worst case can be you're having the largest number as the pivot. So to find out its correct position, you have to make n iteration to put it at the last index. Right. So you go till the last index and then you put the pivot at its correct index. So you had to make n iterations, right? And then after the rearrangement, you again choose a pivot, and again you have the largest element as the pivot. So you again have to make n-1 iterations to reach to the appropriate index. And this goes on, which makes a total complexity the addition of n plus n-1 plus n-2 all the way to 2, because after that we will only be having single element. So this is an arithmetic progression, and we know that the solution of the series till 1 is n plus 1 divided by 2. But here we are going till 2. Still it is approximately equal to n plus 1 divided by 2, and analyzing it asymptotically we will ignore everything other than the term n squared. So the complexity of quicksort algorithm, or the time complexity of quicksort algorithm, is order of n squared. Now let's talk about the space complexity. In quicksort, we're not using extra arrays or space to store elements, but as quicksort involves recursion, we must consider the space that will be taken up by the call stack. So in the worst case, quicksort will be called one time for every element of the list, since the solution could recurse all the way down to single element list. Therefore, we will be having a call stack entry for every function call. This means that at worst there will be n stack entries created at particular instant, and that's why it will be having order of n complexity, linear space complexity. Hey guys, welcome back. Let's move to the next divide and conquer problem, the median of medians. In this problem or in this algorithm, we're given an unsorted array and we need to find the median or the middle element of the array for which half of the elements are smaller than the median and half of the elements are bigger than the median. Suppose this is the array. For this array, the median will be 34, right? Okay. Now the nice solution for this problem would be something like first you sort the array and then get the middle element index. But that approach does more work than required. As you just need to find the median, there's no need to know the sorted position of each element in the array. And the worst time complexity for this solution is O n log n. There's another solution for this problem that has complexity O(n), which is based on quicksort algorithm. So what we do, we choose a pivot element, then we rearrange the numbers exactly like we used to do in the quicksort, and then we return the pivot index. Now we check if the index is the middle index. If it is a middle index, we have found the median, and if pivot index is less than the median index, we recursively search for the median in the right subarray. Else, if the pivot index is greater than the median index, we recursively search in the left subarray. So suppose the pivot is 10. Now you compare every element with this pivot and rearrange the array like this. And we see the 10 will get the third place, right? Is this the median? No, you can tell this by seeing this that median index is 5. So we need to find or we need to search for the median in the right subarray. It is present at the right of this 10. Now we choose a pivot from this right subarray. So let's choose 56. So after the iteration, it comes at the fourth index in this array. But we're looking for the second element, right? So we keep on going to search in the left subarray for this iteration, because now the median is present left to this 56. This continues, and finally we get 34 at the first index, that is at the fifth index of the overall array. So this is how we get the median. Now if we go with the traditional approach to choose pivot element, we will end up having O(n) square complexity, similar to the quicksort. Because if we choose pivot randomly, it is possible that it may end up having position far from the median, like at the first place. Then again you need to search for the pivot and recursively find the median subarray of elements n-1. So in worst case, this approach will go through n-1 multiplied by n-2 multiplied by n-3 and so on, which results in n square complexity. So we need a different approach to find pivot so that we can guarantee that element we choose as pivot is close enough to median. And by choosing pivot close to median, we reduce the number of elements to search by almost half in each iteration. In that way, complexity becomes O(n). Let's see how. Suppose this is the array Now in median of medians algorithm, what we do, we divide the array into sub-arrays, each of length 5, where the last subarray may have length less than 5. Then we find median of each subarray directly. We recursively determine the median of the set of all these medians that we got in the last step. And then we use the final median as pivot. So we found 25 as median. Now use 25 as the pivot, and after one iteration of sorting, we will get this 25 at index number 13. And you can see this array. This is an array starting from 0 to 21. So the median will be present at the index number 11, right? So this 25 is definitely not the median. Now where we have to go to search the median? See the left half of this 25 and the right half. So index 11 is present at the left. So now we're going to do the same thing with this left subarray. So let's take this left subarray. Again, divide into chunks of 5 elements. Again, sort these subarrays and get the median of each. And get the median of these 3 medians and use this value as a pivot again. So when we use 16 as a pivot for this subarray, which is having elements 13, 24, 4, 24 till 1, we will get 16 at index 5, but still this is not the index we're searching for. So again we will take the left subarray and the right subarray to this index 5. And now the element we're searching for is present in the right subarray because it's the 12th element, or you can say it is the element present at the 11th index. So let's take the right subarray and again we're gonna divide it into chunks of 5 elements. Again sort these arrays and find the medians of each, and then the median of these 2 medians. So now 24 is our pivot. Using this pivot, let's take one iteration over this subarray. When we do this, we will get 24 at the 12th index. But still, this is not the index. Index we need is 11. So again, let's take the left subarray and the right subarray. But this time, we won't be having any right subarray as there are no elements to the right of this 24 or to the right of this index 12. So this time we're going to take the left subarray to find out the median. We have to find the 6th element, right? So let's take this array and again let's divide this into chunks of 5. Get the median. So the median of medians we get is 24. Use this as a pivot to have one iteration of sorting using quicksort. So when we do this, we get 24 at 11th index. And this is the index we were searching for. So the element that we need is present right at this index. So this is the median. So let's code median of medians algorithm. So let's create an array, int array, and insert few elements in this array. And now let's call find median method, which will find the median of this array. So here let's pass this array And let's create this method. So here this code is going to be a little long, so in this method again we are going to call another method find median util, which will find the median from this array. And in this method we will pass the array, we will pass the index, the middle index where the median will be present after the completion of this code. So this is the mid element and it is array.length divided by 2 plus 1, right? And now we're gonna pass the lower bound and the upper bound. Lower bound is 0, array starts from 0, and upper bound is array.length minus 1. So here, this is the find median util. Again, in this method, we are going to call another method. But before that, let's rename these parameters. This is, let's say, k, which is the index, middle index, and this is the low, and this is high. So now here we are going to call a method partition, and in this method we are going to pass the array, the lower index, the lower bound, and the upper bound. So now let's create this method partition, and here in this partition again we're going to call a method. This will return us, let's say, m, and here this returns int int. Okay, now here we're gonna call get pivot value, and here we will pass again array low and high. So this pivot value is, let's say, pivot. Okay, now we're gonna write code for getting the pivot value. So main implementation is going to start from here. Here you know that we are going to divide the array in subpartitions having 5 elements each, right? So we need array that will hold the elements present in those partition and another array that will hold all the medians we are getting from that partition. So let's create array. Let's say it is int temp, and let's initialize this array with null. Now we need another array that will hold the medians from each chunk. So let's create this array. This is a new int array, and the size of this array, this will be math.cl, and here high minus low plus 1, we're having chunks of 5, so high minus low plus 1, and this divided by 5. And math.ceil except double, so let's cast it to double. And as this is an int array, cast the whole value as int. So this is the size of medians array, and now let's take median index and initialize it with 0. The next step, we are going to copy the elements into the temp array, and then we are going to sort each chunk. So here, while high is greater than or equal to low, get the size of next element, it can be less than 5. So here we are initializing this temp with new int, and here the size is math.min, It can be 5 or it can be less than 5, because a chunk can be having 5 elements or it can be having fewer elements if there are no more elements. Okay, so now let's fill up this temp array with the elements. So this will start from 0 and it will go till temp.length until the value of low is less than high. And then we're going to increment the I. So here let's put the value in this array. So temp I, and let's put the value present at the low index, and then we will increment the low. So after getting this chunk, we're gonna sort this chunk. So let's sort this using the sort method from arrays utility class. So arrays dot sort, and let's pass the, oh my goodness, this must be sort, and here let's pass temp array. And now we are going to find the mean and we are going to store it in the median array. Now let's put the median from this temp into this medians array. So median in this chunk will be present at the middle index after the sorting. So it will be temp, and the index will be temp dot length divided by 2. Now let's increment the median index. Now we are going to do this stuff recursively to get all the medians into this medians array, and then to finally return the median of these medians. So pass the medians array, the lower bound for this array, and the upper bound for this array, which is medians dot length minus 1. But see this method, we're not having any base condition that will return the median of medians. So let's write the base condition. If high minus low plus 1 is less than equal to 9, then we are going to sort this array. This is the median array having all the medians from those chunks. So let's sort this array. ARR. This is sort here. And then return the median of these medians, which will be present at the middle index of this medians array, right? So ARR dot length divided by 2. This is, we are doing this when the index is, when the length is smaller than or equal to 9, because if it is greater than 9, then we are going to again break it into chunks. So this is how we are getting the pivot, and now the next step is the same what we do when we sort the elements using quick sort. So we take a low pointer and we take a high pointer, or you can say we take 2 pointers at both the ends, and we increment the left pointer, the low pointer, if the value present at that low pointer is less than the pivot value. So increment the low, we go towards right. Otherwise, if high pointer is having value greater than the pivot value, then we go towards the left. That is, we decrement the high, right? And when both pointers are stuck, then the elements are out of order and we must swap them. So to swap them, we must check that low is less than high or not. If low is less than high, then only we can swap these elements. So let's swap them. Take a temp and put the value present at the low pointer in this temp, and put the value at high pointer in this at this low index, and finally put the value present at the low index which we have stored in temp in at high index. So now this is the high index which we are going to return here, but see, if low and high both pointers are having the same value, then we don't have to swap those values. So if both the values are equal, then we're gonna go with incrementing the low pointer. So let's increment the low. And finally, return the index of the pivot, which now the pivot is present at the high index, right? So let's return high. So this will be the value which is returned by this partition method m. So after getting this value, what we're gonna do, we have to check for the length. If length equals to m minus low plus 1, this is the length. And now if this length is equals to k, that is it is at the same index where we are searching for it, then we will return the element at this index, because it is the index where we were searching for, where the median is present, because it is the middle of that array. Else if the length is greater than k, that means that the value we're searching for, or the median, is present at the left to this index. So here we'll pass array k low and m minus 1. Else it is present at the right. So else return find median util pass the array, and the index for it we have to search for is k minus length, m plus 1 is the lower and high is the higher. So now the find median util implementation is complete, and this will give us the median. So int median equals to find median util, and now let's print this median. Median is median. Now let's try running this code and see if it gets us the right median or not. So median for this array must be 24. Let's see. Oh, we are getting the exception here. Median temp low plus plus. Oh, here it must be less than or equal to high. Now let's try running it again. So yes, we get 24, which is the median. Hey guys, so let's sum up our learning on divide and conquer. I always sum up what I learned because this connects all the dots in my brain and I'm able to remember the stuff for a longer period. So let's see what we learned in this section. So we started with understanding what is divide and conquer. We understood how we can identify and approach divide and conquer problems. We saw a lot of problems and we solved those problems using divide and conquer. Now I hope you're feeling more and more interested in next technique we are going to learn. So let's quickly move to the next section. Hey guys, welcome again with another design algorithm, greedy algorithm. Name itself gives a lot of clues and brings so many thoughts in mind. If you think without even watching a single lecture, as greedy people do, they pick up the best without thinking much of the future, right? So does this technique. In this lecture, we opt the local best, or you can say the next best, without thinking much about what is best as a global solution. So we will understand this technique, how we can identify if a problem can be solved using greedy. We will learn how to approach problems on greedy, and we will have some problems to apply this greedy algorithms on. So let's start this exciting stuff from next lecture. Hey guys, welcome back. So we are discussing greedy technique in this section. Let's try to understand what this approach is about. This is the simplest and most natural approach of solving the problems. Believe me, you will find it very natural to think about, and our brain most of the time uses this approach to solve the problem at first place. Very natural way of thinking. Formally, a greedy algorithm, as the name suggests, always makes the choice that seems to be the best at that moment. This means that it makes a locally optimal choice in the hope that this choice will lead to globally optimal solution. If I give you a few things to choose from a bag with price tags but absolutely free for you, what will you do? You might become greedy and choose the items with highest prices, right? But what about if I ask you to choose few items within a maximum capacity? You can start choosing the highest tag item first, as the human nature of being greedy. Here comes the optimality problem. How do you decide which choice is optimal? So let's define this formally again. Assume that you have an objective function that needs to be optimized, either maximized or minimized at a given point. A greedy algorithm makes greedy choices at each step to ensure that the objective function is optimized. The greedy algorithm has only one shot to complete the optimal solution so that it never goes back and reverses the decision. So if we take a pause and think, sometimes being greedy at each step may lose the overall optimality, because in greedy technique there is one shot and then you can't change the decisions. So greedy algorithms have some advantages and disadvantages. It is quite easy to come up with a greedy algorithm for a problem. Also, analyzing the runtime for greedy algorithms will generally be much easier than for other techniques. For example, divide and conquer. For the divide and conquer technique, it is not clear whether the technique is fast or slow. This is because at each level of recursion, the size of problem gets smaller and the number of subproblems increases. The difficult part is that for greedy algorithms, you have to work much harder to understand correctness issues. Even with the correct algorithm, it is hard to prove why it is correct. Proving that a greedy algorithm is correct is more of an art than a science. It involves a lot of creativity. So let's try understanding with this an example. This is called a coin change problem. Here you are having $1 coin, $2, $5, and $6 coin. You are asked to draw $11 from ATM machine where the logic runs on greedy. And you want the minimum bills. ATM machine, being greedy, tries to find the next local choice without being worried about global solution much. So first it chooses $6 bill then $5 bill, it becomes $11. So the greedy approach works fine here. But what if the ATM machine is asked to withdraw $10? It first chooses $6. Now for next local choice, it can't choose $5 because it will exceed the requirement of $10. So it will go for $2 and $2 again. Whoops, this is not the optimal solution. Solution could be $5 plus $5, only 2 bills of $5, but our greedy algo solved it in 3 bills. Now you might be able to understand that how greedy can go wrong, but it can be very fast in terms of time complexity. Now to extend our discussion further, if we apply greedy, there are some problems. For example, fractional knapsack, load balancing, independent sets guarantees the optimal solution, but some problems struggles and fail to guarantee the optimal solutions. For example, these are 0-1 knapsack and coin change problem. However, coin change depends upon input currencies, but greedy cannot cover all the cases there. So hope you might got a decent idea about greedy approach. Let's discuss identifying and approaching the solution using greedy in upcoming lectures. So see you guys there in the next lecture. Hey guys, welcome back. So let's discuss in this lecture the most general approach that we can use in most of the cases to find how to identify and approach the greedy solution. It's difficult to identify if the problem can be solved using greedy. That's why a proof should be written to establish that the solution is optimal and correct. But writing proofs is kind of out of scope of this course because we are more focusing on how to approach the problem. But to identify if a problem can be solved using greedy, there is a mathematical structure which is called matroid. If you're interested more and if you are from mathematical background, you can research more on it. But in general, it says if the subproblem sets of a problem are very independent from each other, then it can be optimally solved using greedy. One more thing to note and not to get confused with is solution of a problem may be correct but not optimal. And our problem, suppose coin change problem, demands for optimal solution. So coming back to identification, if the subproblem sets of a problem is very independent from each other, then it can be optimally solved using greedy. So here are two ways. First is hit and trial and then prove if the solution is correct. And this other way is go with mathematical definition. But for our purpose, we can just have a look and most of the time we will be able to recognize which problem can be solved using greedy. For example, in this section we will study fractional knapsack, which can be solved optimally and correctly using greedy. But 0-1 knapsack can't be solved correctly using greedy. Just to give a clue, the problems which can't be solved using greedy will be certainly solved using dynamic programming, also called DP. We will study that in upcoming lectures in this course because dynamic programming is based on exhaustive search and using memoization for all the solutions of subproblems. Now let's come to how to approach the solution. So when you're sure that problem can be solved using greedy, it's very easy to approach the solution. Just look for the next best choice locally, and if the choice does not fit into the solution, don't choose that. And then keep building the global solution. That's it. Still, with so much of explanation and everything, you just need to solve a couple of problems to understand it clearly. So from next lecture, let's solve few problems to build our basics very strong. So stay tuned. See you guys in next lecture. Hey guys, welcome back. In this lecture, we are going to solve the knapsack problem. This is a very famous problem. What is a knapsack problem? You are given a set of some items and you're told that you can pick items from this set, but you're also given a max weight. The total weight of all the items you are dropping into your knapsack or bag must not exceed this maximum weight. This is the only constraint. So you'll be having weight of each item, you'll be having maximum weight, and you'll also be having value of each item. Then, are you going to pick random items from the set? No, you're not. You'll pick items that give you the most profit. So this is the knapsack problem. Then you fill up the knapsack with the items such that it maximizes the profit without exceeding the weight limit. Now there are two famous types of knapsack: 0-1 knapsack and the other one is fractional knapsack. The greedy approach is well suited for fractional knapsack, but it is not a choice for 0-1 knapsack. Let's know these types better. 0-1 knapsack means that you must pick either the complete item from the selection set or you will not pick that item. Taking a fraction of item is not possible. So either one, the complete item, or 0, no item. So now you must have got what fractional knapsack means. In fractional knapsack, you can also pick a fraction of the item into your knapsack. For example, let's say you're having a bunch of flowers as an item. In 0-1 knapsack, you have to pick the complete bunch, whereas in fractional knapsack, you can pick any number of flowers from that bunch. So point here is that we cannot solve 0-1 knapsack with greedy. Because you know the greedy approach, the greedy algorithm has only one shot to complete the optimal solution so that it never goes back and reverses the decision. So we have to go with what we are left at the last selection. We have to make it from that anyhow. That's only when we are allowed to take a fraction from the item. We can't change the previous decisions. So that's why greedy is a good choice for fractional knapsack. And 0-1 knapsack is solved with dynamic programming. Got it? Now let's go ahead and see how we are going to solve the fractional knapsack problem. You're having some items here, and these are the values of those items. And these are the respective weights of these items. The capacity of this knapsack is 50. Let's go ahead and start putting the items in knapsack. We must have maximum profit, remember? So the item with highest profit is the second one, 480. Is it? It's maximum among all, but it's the profit on 12 units of that item. Now see the sixth element. Its value is 405, but its weight is only 5 units. So if we calculate the value per kg or per unit, for the second element it is 480 divided by 12, which is equals to 40. And for the sixth element it is 405 divided by 5, which is 81. So the sixth element is giving us more profit than the second element because we have saved space for other valuable items. So we have to carefully choose items as we have weight limit. Similarly, let's calculate the profit per weight ratio for each item. So these are the values we get. So we are going to pick items according to these values per unit. So the very first item that we are going to add into our knapsack is the item number 6. Its price is 405 and weight is 5. Now let's calculate the remaining weight. 50 minus 5, which gives us 45. Now next most valuable item is item number 2 because the profit per weight ratio is 40 for it. So let's pick it. Price is 480 and weight is 12. Now the remaining weight is 33. Now next item with profit per weight ratio 17, it's item number 3, price is 336, and its weight is 16. Now the remaining weight is 17. Okay, now the next item is fifth item, for which the price is 238 and the weight is 14. Now the remaining weight is 3. Now the next largest profit by weight ratio is of item 7. Its ratio is 11 and its price is 121. But its weight is 11 and we can only fit item of 3 units into the knapsack. So we have to go for a fraction this time. So let's get only 3 units of this item 7. This is the fraction we need. Now the weight is 3 units, which gives us 33, and now the remaining weight is 0. So this is how we can solve fractional knapsack problem. So let's say we are having 4 items and these are the weights and these are the values of those items, and the capacity of the knapsack is 50. Now we're gonna get the maximum profit. Let's call get max value and let's pass these parameters in this method. So we're gonna pass this weight array, the value array, and the capacity of the knapsack. And this is gonna return us the maximum value. So double max value. Now let's create this method. Create method. So we'll create an item type array that will store every item with its value, weight, and calculated cost. So items, new item. This will be of the same length of these arrays. So let's say weight.length. We haven't created this item type here. So let's create a static class item. So this will be having double cost that we're going to calculate here, and having weight, value, and the index of that item. Now let's create a constructor for this class. So public item and in this constructor we will pass weight, value, and the index of the current item. Let's initialize these values. This dot weight is weight, this dot value is value, int dot index is index. Oh, this dot index. And now we will calculate the cost. How do we calculate the cost? Cost is the value of that item divided by the weight of that item. So here we will pass the value divided by the weight. This constructor is deprecated. Let's change it to double dot value of. Okay. So this item is having all the data about that item along with the index. Now we're gonna insert all those items in this items array. So let's take a for loop. And at the ith index in this items array, let's put the item with weight I, value I, and the current index. Now we will sort these items by the cost, because first we want to add the items that can give us more profit into our knapsack. So let's sort the array, import arrays, and now sort the items array in descending order of the cost. So we have to provide the sorting here, the comparison. So for that we are going to pass a comparator, and we are going to implement its compare method here. So let's import the comparator and let's add the compare method to compare the items. As we want to sort in the descending order, so we're gonna first take the cost of o2.cost, and on this cost we're gonna invoke the compare to method, and we're gonna pass the cost of oven. So this will do the sorting. Now in the sorted array, let's start picking items with maximum cost ratio to minimum cost ratio. So let's take a variable total value that will hold the result for us. Initially it is, let's say, 0. And now let's run a loop, a for each loop, for each item present in the items array. Let's get the current weight and current value. So the item for which we are performing this, we're gonna get the weight of that item dot get dot weight, and let's cast it to int. And also we're gonna need the current value. This is item dot value. The item can be added completely in the knapsack if there is space in the knapsack. Okay, so we will check if the capacity minus the current weight is greater than or equal to 0 or not. If it is greater than or equal to 0, that means the complete item can be added into the knapsack. So we will update the capacity and add the value to the total value. So let's add the current value to the total value, because we have added the complete object into the knapsack. Let's make it total val. The other case is when the capacity is not sufficient to get the complete object into the knapsack. So what we will do, we will calculate the fraction that can be added into the knapsack. So let's calculate the fraction, and this fraction can also be calculated by calculating the ratio of capacity by the current weight. So weight of the item is current weight. This will give us the ratio of the value that can be added into the knapsack. So we're gonna add this fraction of the current value into the total value. Double, and now current value the total value becomes current value multiplied by fraction plus the previous total value. So this is the new total value, and now we're gonna break this loop to come out of this loop because the knapsack is completely filled, there is no space left. So now we will return this total value, and we're gonna print this value here in this main method. So let's print it. The maximum profit possible is this max value. Okay, now let's run this program and see the result. So this is the maximum profit that we can get if we go greedy, and this is the optimal one. Now let's analyze the complexity of fractional knapsack. So the main step that takes time is the sorting of all items by their value by weight ratio in decreasing order, right? So the running time will be time taken in sorting these items. So whatever technique you have used for sorting, that will be the complexity of the algorithm. And the most general and efficient one is n log n. Even if you use built-in functions for sorting, it's gonna take order of n log n time, where n is the total number of items you're sorting. Now, space complexity. We're just having temporary variables to solve the problem. So the complexity will be constant as it's not affected by input size. Hey guys, welcome back. In this video, we are going to solve interval scheduling maximization problem. Interval scheduling is a class of problems where we are given data sets representing time intervals. Now there are a lot of variants of this problem, but we will be working on interval scheduling maximization. So here we are given set of intervals, and in this problem we need to find a set of non-overlapping intervals of maximum size. That is, we need to choose as many intervals as possible from the set that don't conflict with each other. The goal here is to execute as many tasks as possible. So your result set must be having maximum number of intervals which are non-conflicting. Here we can see non-overlapping intervals are A and D. As first we will pick the interval A, which is from 0 to 6, so we cannot pick B and C as they are overlapping intervals. A finishes at 6, so any interval that starts after 6 can be picked, which is D here. Let's see how we can find optimal solution with greedy algorithm. The steps are, we're gonna sort intervals by their finish time and choose the earliest finish time interval, as the goal is to choose the maximum number of intervals. If we choose interval that is finishing earlier, we will be able to include more intervals in the set, right? And with that, we need to check the next interval should not conflict with the one we just chose. For instance, these are the intervals. Remember the finish time of interval that we just took and compare it with the start time of the next interval. So last finish time is 3, and then we have C, it's not overlapping, it starts after 3, so we can have it. So we choose the next interval only if it starts after the last finish time. If it overlaps, we won't pick it. This overlaps, we cannot pick it. And now this also overlaps, but this can be included. It starts right after E. So this is the output we get. And this is how this algorithm works. So see here, we are having a 2D array intervals having start time and end time of intervals. Now let's create the method schedule and let's pass this intervals array. This method will return maximum set of intervals that has no overlaps. So we will collect the data in list of integer arrays. So let's call it optimal schedule. Now let's create this method schedule. And here let's initialize a list that will hold the result to be returned by the schedule method. So it's a list of integer arrays, optimal interval set, it's a new array list, and it's a list having integer arrays in it. Let's import array list. So after initializing this list, the first thing that we are going to do is sorting the interval according to their finish time, as we want to have the maximum number of intervals. So sort, let's import arrays and let's pass the intervals and let's pass an implementation to the comparator as we want our own implementation. So here let's implement the compare method for the comparison. So let's first import the comparator and then let's override the method. So we want to sort according to the finish time. So O1, and the finish time is present at 1th index, at 0th we are having start time, at first index we are having the finish time. So it is O1 1 minus O2 1. So this will sort in ascending order. And how the sorting is going to get us maximum number of intervals. See the studio array intervals. The first interval is having n time 3, the second is having n time 15, and the third is having n time 10. Now ignore the start time and see the n times. If we don't do this sorting, then it might pick the second interval, which is covering more space. That means we would be able to have less number of intervals in the solution. So the sorting is important. Now after sorting the intervals according to n times, now let's take a variable last finish time and set it to the minimum value of integer. So we are initializing it with the minimum value. And then we're gonna take a for loop to iterate through each and every interval. So for each interval array present in intervals, this is interval array present in the intervals list, initialize a variable start with interval 0, that is the start time for that interval. So this is the start time for that interval, and now we're gonna check if this is the start time. Now we're gonna check if the star is greater than the last finish time. That means it must not overlap the previous included interval, right? So that's why we're checking if the start is greater than last finish time. Then we're gonna get the end, which is present at the 1th index, at the first index. So let's, after taking this end, we are going to add this interval to our optimal interval set because we are going to pick it. interval. Now, as we're including this interval, I have pronounced it wrong, I guess. Okay. Now, as we are going to include this interval set. So as we're going to include this interval, we are going to update the last finish time. So last finish time is this end. So again, it is going to go in this loop and again going to check if the next start is greater than the last finish time or not. And in this order, it will get us all the intervals in this optimal interval set. And finally, we will return the set. Not, let's copy this and paste this. Okay. Oh. So the implementation is now complete, and now we are going to go back to the main method, and here we're going to print the result. So let's take a for each integer array present in this optimal schedule. Let's print out the result, the start and end intervals. So this is dot length sys out is I so it is going to print the start and the end of that interval, and after each interval let's give a line. So now the implementation is complete. Let's run this and see the intervals we get. So these are the 4 intervals that we got using this greedy technique. So it is ending at 3, next is starting at 5, and 10, 12, 14, 16. So no one is overlapping. Now let's analyze the time complexity for this problem. In this, we will be sorting the intervals by their end times, and then we iterate through the sorted set for finding the non-overlapping time intervals. So sorting gonna take n log n running time, plus there will be n iterations. So total complexity will be order of n log n plus order of n. We can ignore the term O(n) here, hence the time complexity for this problem will be order of n log n. Now the space complexity. So to solve this problem, we are creating n size array for storing the optimized intervals one by one. So the space complexity will be order of n. And this is when we are including the output array in this analysis. If we do not include the output structure in this analysis, then it will be constant space, because your algorithm is not using up that space to calculate something or to process something or to perform any kind of operation. It is using that space only to store the result. That's why if you don't consider that output array, then it will be constant space. So space complexity most of the time is dependent on what you're going to include in your complexity analysis. Hey guys, welcome back. The next example of greedy algorithm that we're going to discuss in this lecture is Huffman coding. Huffman code is a data compression algorithm which uses the greedy technique for its implementation. The algorithm is based on frequency of characters appearing in a file or in data. We know that our files are stored as binary code in a computer, and each character of the file is assigned a binary character code, and normally these character codes are fixed length for different characters. For example, this is the data we have. How are we going to send this data over a network? First, each character is converted into the ASCII value, and then binary of that value gets calculated, and then finally we can send those zeros and ones over the network, right? See here, the ASCII value of A is 65, and after converting it to binary it is 01000001. So 8 bits are being used to convert each character into its binary when you use ASCII. So here the total number of characters used in this string are 26. So the total number of bits required to send this message is 26 multiplied by 8, which is 208. This much bits are needed to send this data over the network, and this is when we're not using any compression technique. This is actually called fixed length coding, because for each character used, it takes up 8 bits. That is a fixed number of bits no matter what. Now think about compressing this so that it takes less bits. There can be various ways. One of them is Huffman coding. But before that, let's talk about the compression a bit more. Think of number of characters that you can represent using 2 bits. We can represent a character with 00, we can represent a character with 01, we can represent a character with 10, and with 11. Let's say these 4 combinations are taken for A, B, C, D. Now what about the remaining characters that we have in our message? So definitely we can't go with it. Now think of the number of combinations with 3 bits. There will be 2 raised to power 3 combinations, that is 8 combinations, right? Similarly, if we use 4 bits, then we would be having 2 raised to power 4 combinations, that is 16, right? So we can represent 16 characters with these bits. And here see how many different characters we have. We only have 7 distinct characters. So we can use 3 bits to send this data over the network, right? And in ASCII, they use 8 bits. The number of characters we can represent is 2 raised to power 8, that is 256. We don't have this much different characters in our message. 3 bits are sufficient for us because we're having 7 distinct characters in this message, and 3 bits can help us represent 8 distinct characters. So okay, let's go with 3 bits. The possible combinations with 3 bits are these. Alright, let's assign characters to these combinations. So message sent over the network is A000 because 000 represents A, and then B001, and so on. So see, the total number of bits we are sending are now just 26 multiplied by 3, 78. Surely this technique made a good choice. The bits are reduced from 208 to 78. But how the receiver will decode this message? Think about it. How it gonna know which combination represent which character? There's no other way than sending this information along with the message. So we send the character along with its bit value we're choosing for it. So 3 bits and A. And to send A, we have to use the ASCII code here. ASCII of A is 65, which converts to this binary. And if we calculate for all the characters we are having in this message, 3-bit representation for each, 7 multiplied by 3, and 8 bits of ASCII for each, so 7 multiplied by 8, so it becomes 77. So we need 77 extra bits. So the total message length over the network will be 78 plus 77, which becomes 196. which is not so far from 208. Now let's see how much difference the greedy approach can make. The greedy approach for compression is Huffman coding. Huffman code doesn't use fixed length code word for each character and assigns code words according to the frequency of character appearing in the file. Huffman code assigns a shorter length code word for a character which is used more number of times and a longer length code word for a character which is used less number of times. So Huffman coding demands knowing frequency of each letter present in the message. Let's find out the frequency of each character present in this message. A appears 5 times, B also appears 5 times, C appears 4 times, D 3 times, E 2 times, F 1 times, and G 6 times. Now it's time to know the Huffman algorithm. In Huffman algorithm, we first sort the unique characters in ascending order of their frequency. So F is having least frequency, so it comes first, then E, D, C, A, B, and then G. So we store these characters in a priority queue in which the character with lower frequency is at higher priority. So these are the respective frequencies of these characters. Now we're going to draw a tree based on these frequencies. How we are going to draw this tree? Each time we're going to take the first 2 frequencies and then we're going to merge them into a single frequency. And then again we will rearrange all these frequencies and we'll do the same until we get a complete tree. The first 2 frequencies are 1 and 2. Let's merge them. 1 plus 2 gives 3, so we get 3. Now again sort them including 3, so the new arrangement is 3, 3, 4, 5, 5, 6. Again take the first 2. First 2 are 3 and 3. Merge them into a single one. It gives us 6. Again rearrange all the frequencies in sorted order of the frequency and look for the smallest 2. These are 5 and 4, so let's merge them into a single one. So it gives 9. Now again rearranging the frequencies 5, 6, 6 and 9. This time this 6 node in green is the same we are having here below, which is having subnodes 3, 3. We are not having space there, so we have taken it like this. Now again merging the smallest 2 frequencies, it gives 11. Now there is no free frequency left. The frequencies we have are 11, 6 and 9. So again we have to rearrange these frequencies. Let's rearrange them. First comes 6, then 9 and then 11. The first 2 are 6 and 9. Merge them, it becomes 15. And now we are left with only 2 frequencies, 15 and 11. 11 is smaller than 15, so it comes first and then comes 15. Let's again merge these 2 frequencies. 11 plus 15, it becomes 26. So this is the final tree. See the leaves of this tree. These are the frequencies of the distinct characters. So F is having 1, E is having 2, D is having 3, C, A, B and G. Now the next and the last step is marking each left edge with 0 and each right edge with 1. So at the left of 26 we have 11. We will mark this edge as 0, and at right we are having 15. We'll mark this edge as 1. Similarly here, all the left edges as 0 and all the right edges as 1. And now this is a complete and final tree. Now using this tree we are going to find out the binary code for each character. So for A, see the path. It is 26, 15, 9 and 5. So the code for A is 111. And now see the B. B is present here after 11. So the path it traverses is 26.11.5. So the code for it is 00. And similarly, we have all the other codes. So along with the message bits, we send this information so that the receiver knows which code belongs to which character while decoding. So here we have all 7 characters. To send each character, we need the ASCII code, which consumes 8 bits. So 7 multiplied by 8, and then their corresponding bits. These are total 21 bits, and all the bits that will replace the characters in the original message, that is the bits required to form the coded message. These will be the bits for that character multiplied by the frequency of that character, right? These add up to 70. This makes a total of 147, which is quite smaller than both of the previous results. So when we were using 8 bits, the number of bits required were 208, and when we were using 3 bits, the number of bits required to send the message were 196. But using this greedy approach, we just need 147 bits. The first two approaches are having fixed number of bits to send each character in the data. But this Huffman coding approach is based on variable length. It is also called variable length coding. So in Huffman coding, if the frequency of character is high, the code that will be generated for that character will be having less number of bits, which makes it better than the fixed length coding approaches. So this gives us the optimal solution. So see, this is the data that we are going to send over network, and let's encode it using Huffman coding, and let's pass the string in this encode method, and this is going to return an equivalent string code for this string, binary code for this string. So this is the method encode. Here we're going to create a map that will hold the frequencies corresponding to each character present in this string. Let's call it f new hash map. So as key we will be having the character, and as value we will be having the frequency of that character in this data. So now let's take a for loop. It will start from I and will go till length of this string, str.length. This is length method. And now inside this for loop, if the character is not present as key in the map, then we'll add that along with value 0. So if f contains the key, the character, string.char at I, then we're gonna put this character as the key and 0 as a value. Dot char at I, and the value is 0. And when the character repeats, we will increase the frequency of that character. So here we're gonna put the character as a key. So char at I, if it is already present, then increase it by 1 each time. So f.get the value present for that character, that means the previous frequency, char at I, so add 1 to the previous frequency count. So this is how it will calculate the frequency corresponding to each character and will put it in this map. Now the next step is to generate the tree, the Huffman tree. So for that, let's create a method, generate tree, and let's pass this map f in this method. And this method will return the root node of the tree that we are building, having all the nodes attached to it. So let's create this class. Let's call it Huffman node. Let's create this class right here, class Huffman node. And this class will be having the frequency, it will be having data, and it will be having the left node, Huffman left, and right. Oh, Huffman node. So now other than these data members, we are going to implement the compare to method for this Huffman node class because we need the sorting of frequency. So here we are going to implement the comparable, and we will implement the compare to method here. So let's add the compare to method and let's sort these nodes according to the frequency. So here frequency minus O dot frequency. Coming back to encode method, and let's generate tree. Let's create this method. In this method, we are going to first take a priority queue that will store the nodes. Priority queue, Huffman node. Now let's fetch all the characters from this F map. So set of characters, character, F, let's import set F dot key set. Now we're gonna take a for each loop to create Huffman nodes for each character. Here we are going to create the leaf nodes. Leaf nodes will be having character as the data. So for each character present in this key set, we're gonna create a separate node. Let's call it node. New Huffman node. And now as data to this node, we will set the character. Hope you remember that all the leaf nodes are going to have the character as data. So here we are working for the leaf nodes, so we are setting the character as the data to these nodes. Now we're gonna set the frequency that we are going to get from this map F. So for this character, for that character, we will get the frequency by passing that character. And leaf nodes are not gonna have left and right attached to them, so the left and right both will be null for them. And finally, let's add these nodes in the priority queue. We implemented the comparable for these nodes, so priority queue is going to have them in sorting order. So the node having the least frequency will come first, so they will be inserted in ascending order of their frequency. Now the next step is we're gonna take first two nodes and we're gonna merge them into one having single frequency. So let's peek to get the first element. So let's call it first, and let's remove this from this priority queue. Priority queue dot pull, and let's also get the second node and remove it from the queue. So priority queue dot pull, and now get the sum of both first and second. So Huffman node, this will be the new merge node, so let's call it merge node, new Huffman node. Now we will make the first node the left node of this merge node. So at left of this merge node, left, we will be having first, and at the right we will be having the second node. So merge node dot right is the second node, and this merge node itself will become the root. So merge node is now the root, and as we will only be having one root for a complete tree, so let's make this root a static one. So Huffman node root. So now this merge becomes the root. Now what will be the frequency of this merge node? The frequency of this merge node will be the sum of the frequency of the left node and the right node. So merge node dot frequency, first dot frequency, and second dot frequency. And the data for this merge node will be nothing because it is not the leaf node, so it won't be having the character as the data. And then finally we are going to add this node into the priority queue. So we will keep on adding these nodes until we're left with the single node in the queue. So here, while priority queue dot size is greater than 1, we will do this. And then finally we will return the root from this priority queue that will be having all the nodes attached to it, the final tree. So dot pull. So here we will get the complete tree, the root of the tree that we generated, and now we have to generate the binary code for each character. So characters are present at the leaves. Now let's call the set binary code method to generate binary code for each character. So here we are going to pass the root, and we are going to pass a string builder object. using which we are going to create the binary code. So let's create this method. So now here we need zeros for left edges and we need ones for right edges, right? So let's start with the left edge. We're gonna use the string builder. Let's call it str, and here str.append. For left edge, we're gonna append it with 0, right? So let's append it with 0, append, and let's pass 0 here. And after appending it with 0, we're gonna call the set binary code recursively because 0 means we have selected the left node, right? So here we will pass left of this root. Let's call it root, or let's simply call it node. So here we're gonna pass the left of this node. That means we are going left to this node, and let's pass the string str, so that till it gets to the base case it will be having the complete string that we need at that character. And then finally, after passing the string, we have to again delete the last character. So we will delete the last character str.length, so that we can call it for the right edge with value 1. So now let's, if we are going right, if we are selecting the right edge, then we need to append the string with 1, right? So here let's append it with 1, and let's go to the right node and let's pass the string and then again delete the character. Now coming to the base case, and this whole we are going to do if the node is not null, right? So let's include this case. And now coming to the base case is when we reach to the leaf node, right? So if leaf node means there are no nodes attached to the left and right. So if node.left is null and node.right is also null, then here I'm going to take one hash map to store the result. So static map, this will be having the character as the key and string of zeros and 1 as the value. Let's call it char binary map, and or let's call it char binary mapping and initialize it. So again, coming to this base case, here let's add the data to this map. So dot put. So first we're gonna put the data. Data is a character, so we have already set the data for the leaf nodes as the character, and the value is the string that we're getting when we reach to this base case. Else we will do these recursive calls. Oh, I forgot to write put here. So now this implementation to the set binary code method is complete. So now this char binary mapping hash map will be having characters as the keys and the binary code for those characters as the value. Now coming back to this encode method, let's print the complete hash map here. So sys out binary codes, and here this char binary mapping. Now that we have all the codes, we can generate the complete binary for this message. So let's take a for loop, and here this is str.length, and let's take a string builder to store that binary. String builder is new string builder. And here first get the character. So character C is str.char at I, And for this character, we're gonna fetch the binary from the map. So s.append, and here there's char binary mapping dot get the value present for that character. So we're getting the value and we're appending it to s. And finally, we will have complete string, and here we will return that string. So now in this main method, let's print that string. So the final coded string is plus the code. So now let's run this and see the binary we get. So you can see the mapping and you can also see the complete binary. Now let's analyze the complexity for this problem. So solving Huffman coding problem includes storing frequencies of characters. It includes generation of tree and then setting zeros and ones to the nodes. So the running time will include order of n for all the traversals while storing frequencies in a map object. And then generating tree will take n log n running time as we're using priority queue, which involves sorting of nodes. Basically adding nodes in a sorted manner, which is gonna take n log n. And while setting the binary code for one node, it will take log k for traversing through the tree where k is the number of nodes in the generated tree. And this we are going to do for n number of leaf nodes. So it will take n log k. Here we are analyzing complexity in asymptotic way. So we can ignore n and n log n as well because order of n log k will be larger than these two. So here the complexity will be order of n log k. Now the space complexity. Our algorithm or our solution for Huffman coding is going to require order of k space for generated tree. The other containers that we are having to store key values need only order of n space individually, which is smaller than order of k. So we will ignore it and we will take order of k as the space complexity for this problem. Hey guys, welcome back. In this lecture, we are going to understand Dijkstra algorithm. Dijkstra algorithm basically operates on graphs where we find shortest distance to reach to each node. In this problem, we will be given a graph. Every edge will be having some weight. We need to find the shortest path for each vertex from the given source node. For instance, in this graph, A is the source node, so we need to find minimum distance to reach to every node from A. For that, we will be having a table or a matrix of shortest distance for every single vertex, and will update or improve them continuously. Initially, we give start node 0 as minimum distance, and to all other nodes, shortest distance will be infinity, as we don't know the distance to these nodes yet. So we start to explore node A. 4 edges are coming out of A, which are B, D, F, C. So we check for every vertex. If the distance from the current source to vertex is smaller as compared to the current upper bound, for example, to go from A to B, the current upper bound is 0 because at A we are having 0. So A to B distance is 3. And in the table, distance is infinity. So we check if 3 is smaller than infinity. If it is, we say that the best way to go to B is A. So we update the distance as smallest distance for B. Next edge is C. A to C distance is 5 and upper bound is 0, which is less than infinity, so we update the distance for C as well. Similarly for D, distance from A to D is 6, which is less than infinity, so we update it in the table. And then for F, it is 8, it's less than infinity, we update it in the table. So now we are done with A because we have traversed all the adjacent nodes. So the next we choose the unexplored vertex, which has minimum distance. So see the table, the vertex with minimum distance is B. So let's process B. Now B is having value 3, so the upper bound is 3. So if we visit any node after visiting B from A, can we improve the distance to get to these adjacent vertex from A? If we can, we will update the distance with the new value. So the neighboring vertices of B are A, D, E, G, right? A is already visited, or if you even try to go to A through B, then the path will be A, B, A, which will be 3 plus 3. The upper bound at B is 3, so it will be 6. So that we don't prefer anyways because it is having value 3 already and A is having value 0. Next is D. The current distance to get to D is 6 from A, right? You can see this on the table. And if we go through B, it will be 3 plus 4. That will be 7, which is not less than the current one. So going through this path is not a good choice. We need not to improve it. Now we're going to look at E. If we choose B to get to E, the distance will be 3 plus 2, which is less than infinity, so we will update 5. Next is G, which is less than infinity. Here we are having 5 distance and the upper bound is 3, so the distance becomes 8. So let's update it here. Now B is also visited. The minimum distance in this table is for C and E, right? So next we're gonna start with C. So here adjacent vertices are A and F. A is already visited, so we have only F. So for F, if we go through C, the distance is 4 plus 6. But F is already on 8 if we go directly from A. So we are not going to take that. Now C is also visited. Next we will process E. Here the adjacent vertices are B and G, and you know that B is already visited, so we have G. So for G, the upper bound here on E is 5 and the distance is 10, so it becomes 15, which is greater than 8. So we won't update it because we have a better path when we go through B. Now E is also visited. Next minimum is D, so we're gonna process D. So see, if we can improve the distance to reach to F, it will be 6 plus 1, which is 7, which is actually less than the current one. Current one is 8. So we update 7 as the minimum distance for F. Now we start processing F. So here the adjacent vertices are A, C, D, G, right? Where A and C are already visited, and for D, it is 8 plus 1, which is greater than 6, so we won't update. For G, it is 8 plus 8, 16. Again, it is greater than 8, so we won't change it. So basically, we are minimizing the path from the very start and we repeat the process for the whole tree. We will get the best path to reach to destination as every time we go to a vertex, we know we are on the best way to reach to this vertex. So if we apply this rule throughout the graph, we will generate the optimal solution. Now, before jumping into the code, let's talk a bit about how we're going to have this data. So see here, we will be having a matrix where the rows and columns of this matrix will represent the vertices. You can see A, B, C, D, E, F, G. These are the vertices, and the values in this matrix are the respective distances from one vertex to another vertex. As you can see here, in this table, the A to A distance is 0, the A to B distance is 3, the A to C distance is 5, the A to F distance is 8, the B to A distance is 3, and so on. So this matrix is having all the distances. So this is one array or one matrix that we will be having, and we will be having another array that will store the shortest distance that we are finding using this algorithm for each vertex. So the index of this array will represent the vertex. As you can see, we are having 0, 1, 2, 3, 4, 5, 6. These can be A, B, C, D, E, F, G, and the shortest distance will be the values in this array. And one more array to keep the track of already visited vertices. So it will store Boolean, true if the node is already visited, and false if it is not visited previously. So here I've already created this matrix having all the distances, and now let's call Dijkstra and let's pass this adjacency matrix in this method. Let's create this method. Here in this method, let's take a variable v. V is number of vertices, so v will be equal to adjacency matrix dot length, right? Now we create Boolean array of length v to mark the node visited. So Boolean visited, new Boolean array of length v. So it will keep track of all the visited nodes. Now we create another array to hold distance for each vertex. So it is also of length v, and now we set the distance for source as 0 because we start from here. So this is the source and it must be having distance 0. So distance 0 equals to 0. And now we're gonna mark every other vertex as maximum value of integer because we want to assign infinity to all the remaining values. So we'll take a for loop which will start from 1. We are excluding the source because we have already set 0 for source, and now for all the other vertices this will be till v. So for all the other vertices we will set the maximum value of integer. So distance I is integer dot max value. Now we will find out the vertex with minimum distance, and then from there we are going to traverse the adjacent vertices. So to find the minimum for the adjacent vertices, so this loop will start from 0 till v minus 1, and now let's find out the minimum vertex here. So let's call find minimum vertex and let's pass the distance array and the visited array in this method. This will return the vertex with minimum distance. min vertex. So now let's create this method find min vertex, and here we are going to initialize a variable min vertex with -1, and then we'll take a for loop to find out the one with minimum value of distance from the array distance. So it will start from I and will go till distance dot length. I is less than distance dot length, and will increment the I. Now inside this loop, what we're going to check for each vertex is that it must not be visited earlier, and there can be two cases. One, when it is the source node. For the source node, the value for min vertex will be -1 because we are initializing it with -1. So if this is source node, then anyways we are going to go in this if. As if it is some other node other than the source node, then we're gonna check if the distance at this index is less than the distance at the previous minimum vertex or not. So if it is the minimum distance, then we are going to update it into this min vertex variable. Okay, now we are going to return this minimum vertex. Now after getting this minimum vertex, we have to go to adjacent cells from here, adjacent vertices from here. So, oh, there must be one more. So now let's come back to this Dijkstra method, and here let's take a for loop again to go to the adjacent cells. Before that, we will mark this minimum vertex as visited, because we are going to do all the work for this vertex. So from here we will go to all the adjacent cells, all the adjacent vertices from this minimum vertex. So let's take a loop starting from 0, and it must be less than, it must go till it is less than v, and then let's increment it. Now the condition that we are going to check is the value at the cell must not be 0. That means it must be the adjacent to that node. If it is not adjacent to that vertex, then it will be having value 0. Otherwise, it will be having some other valid value. So we are going to take min vertex as row and j as column. It must not be visited earlier, and the distance at minimum vertex must not be the max value of integer. That is, it must not be infinity. So if the value is present, we calculate the distance by adding distance for the source vertex and the distance for the adjacent vertex. So let's get the new distance, and new distance at minimum vertex, which is the upper bound for us, plus the distance present for that column in adjacency matrix. So this is the new distance. Now we want to check if it is less than the distance which is already present in distance array at that position. We will update the new distance as distance in that array, because we want the minimum of these two. So if it's smaller than the previous distance, let's update it in this array. Otherwise, we won't do anything. We won't change it. This is And when we get done with going through every vertex, each vertex, we will print the distance array. So let's print it here. I is less than v and I plus plus, and let's print the distance at each index. This is the index and this is the distance at that index. Now the implementation to this Dijkstra algorithm is complete. Now let's see the output. So these are the distances at each of the index or at each of the vertex. Now let's find out the time complexity for this problem. First of all, we're going to go through each vertex to find the shortest path for them. And while doing so, we are finding the adjacent vertex with minimum distance from the source node. So in worst case scenario, there might be n minus 1 vertices connected to any node, right? So total iterations in worst case will be n multiplied by n minus 1. We can take that as n squared. Hence, the total complexity will be order of n squared for both traversals to the vertices. Now, space complexity. For keeping track of visited nodes and to hold distances for each vertex from source, we are creating arrays of size n. So the space complexity will be order of n. Hey guys, welcome back. It's time to sum up. So, we saw one more technique of problem solving in this section. It is greedy algorithm, and we tried understanding what it is, how we can identify if a problem can be solved using greedy, how we can approach the solution to the problem, and then we tried some of the hand-picked problem using greedy algorithm. I'm sure now you have one more technique in your kit to tackle real-world problems. At the same time, I'm excited to start the next section, and I'm sure you also want to check that. So let's study our next technique in the next section. I see you there. Until then, bye-bye. Hey guys, welcome back. Dynamic programming. I know this name does not seem familiar, and also there is no clue in the name, right? When I was a kid, I learned multiplication tables, at least up to 20. Like 5 sevens are 35. I'm sure you might have also learned these in your elementary school. Why we still remember those tables? Because we use them so frequently in our life, almost daily, and we may not want to waste our time every time adding 5 7 times to get to know 5 sevens are, right? Just by remembering tables, can you guess how much time we saved in our life? Until you do that calculation, let me tell you, this is the basic idea behind this technique. While our code is going through some calculation, we can remember some of the stuff in between or some of the stuff from past so that we can save our time to recalculate. Thrilled? I know you are. This is a very famous technique that can solve most of the problems optimally. We will know more about dynamic programming. We will see how we can identify the problems for dynamic programming, and we will compare dynamic programming with few other approaches. We will know how we can approach the problems using dynamic programming. There are basically two approaches, top down and bottom up. And then we will solve some of the classical problems. This is very important section from interview perspective, so we will solve some extra problems in this. So in real life, if you're coding real systems, I'm sure you will be able to save some of your CPU time. Save the earth by writing better and less CPU consuming code. Ultimately, if you will write better code, less CPU will be consumed and less hardware will be required. So I'm sure this has been created some excitement to learn this technique. So let's start the real stuff from next lecture. See you there in the next lecture. Bye bye. Hey guys, welcome back. Let's look at dynamic programming. Dynamic programming is a very famous algorithm to solve recursive problems. In fact, it is an optimization over recursion. We all know recursion, right? In recursion, we divide the problem in smaller subproblems and we solve these subproblems and use their solutions to compose the result of original problem, right? Then how dynamic programming optimizes this process? What exactly is the idea behind dynamic programming? Dynamic programming is basically about storing the results of subproblems into memory so that we don't need to calculate them repeatedly. In many recursive problems, when we break them up into smaller subproblems, we may find some overlapping or repeating subproblems. For example, think about getting the nth Fibonacci number. What is a Fibonacci number? Or what is a Fibonacci series? It is a series of numbers such that each number is the sum of two preceding ones. It always starts from 0 and 1. So the first two numbers are always 0 and 1, and then all the numbers are sum of two preceding numbers, right? So if we are going to get the series till fifth Fibonacci number, it will be 0, 1, 1, 2, 3, 5. It starts from 0 till the nth number. So when we solve this recursively, what is the formula? It is fib of n equals to fib of n minus 1 plus fib of n minus 2. So it will start from 5. N is 5, right? Then we have two recursive calls, one for n minus 1 which is 4 and other for n minus 2 which is 3. But here as we're calling n minus 1 first, the left chain completes first. So for this n minus 1 call, it again calls for n minus 1 and n minus 2, that is for 3 and 2. At left we have 3, so continuing with this recursive call again for 2 and 1, continuing with 2, and then for 1 and 0. 1 and 0 are base cases, they return 1 and 0 respectively. So after adding 1 and 0, we get the value for fib of 2, which is 1. Now it is sent to the previous call. That's how fib of 3 gets the return value from the left call. Now it's time to calculate the value for the right call, which is for fib of n minus 2. So fib of n minus 2 is for fib of 1 because 3 minus 2 is 1, right? So at 1, 1 is the base case, so it returns 1. So again at fib of 3, we calculate the sum, which becomes 2, and it's passed on to the previous call. Previous call gets its return value from the left call for n minus 1, which is 2, and now it calculates the value for the right call for n minus 2. So n minus 2 is 4 minus 2, 2. And now, okay, again it have to go recursively till the base case and have to calculate the value for this node. But we have already calculated the value for 2. But still we have to do the complete process. So it calculates the value for 1 and it calculates the value for 0 and then finally calculates the value for 2. And then this is passed on to the previous call as the result for fib of n minus 2. Now we calculate the value for fib of 4, which is 2 plus 1, 3, and it is passed on as the result of the left call to fib of 5. Now again it has to go to right to calculate the value for fib of n minus 2, which is 5 minus 2, 3. So we have to calculate the value for 3 again. So the point is, when we are solving such problems using recursion, We are calculating the results of exactly same problem more than once. We have already solved a subproblem, we calculated result for it at some point in time, and then we are calculating the result of the same problem at some other instance. Then why not storing the result into memory along with calculating it, so that we don't need to calculate it again for the overlapping problems? We would just be able to get the result for that subproblem from the memory. This is exactly what dynamic programming is for. So this was all about this lecture. See you guys in next lecture. Hey guys, welcome back. In last lecture, we got together a little information about dynamic programming. In this lecture, we're going to discuss how we can identify if a problem is a candidate for dynamic programming. So let's jump straight to the test points. First is, if you're given a problem which can be broken down into smaller subproblems, and these smaller subproblems can still be broken into smaller ones, and if you find that there are some overlapping subproblems. Next point is if it is an optimization problem, or you can say if problem demands for optimal solution. With optimal problems or solutions, you see terms like shortest, longest, minimized, maximized, least, most, fewest, greatest, biggest, smallest, etc. And the optimal solution of subproblems can be used to form the optimal solution of original problem. So these are the main points to identify if a problem can be solved using dynamic programming. So always judge the problem on these points to find out if it is a candidate for dynamic programming. So this was all for this lecture. See you guys in next lecture. Hey guys, welcome back. In last lecture, we talked about how we identify if a problem can be solved using dynamic programming. You may find all or any of those points to be same as the identification points to some other famous strategies. And that's why you may find yourself stuck between choosing one of those strategies in middle of your interview. That's why, to make things more clear, in this lecture we're gonna do some differentiation between these techniques. So let's see how DP is different from recursion, how it is different from divide and conquer, and how it is different from greedy. So first let's talk about recursion. We've already discussed how DP is different from recursion, as it's simply an optimization over recursion. Same problems can be solved with recursion, but if problems have overlapping subproblems, then definitely the recursive solution is going to take more time, as it's gonna be calculating same subproblems repeatedly. Now, let's talk about divide and conquer. In divide and conquer, we divide the problem and then we solve those subproblems to construct the solution of original problem by combining results of those subproblems, right? But the subproblems in divide and conquer are not overlapping. They are independent from each other, but in case of dynamic programming, the subproblems are overlapping in nature. If you think of any divide and conquer algorithm, let's say merge sort, you divide the array in two halves and both the subarrays are independent from each other. At no point they're gonna repeat. Now if you think of dynamic programming, you know the example of Fibonacci sequence where the subproblems may be overlapping. Now let's differentiate between dynamic programming and greedy. Greedy and dynamic programming both are used when we are asked for optimal solution. But greedy approach does not guarantee the optimality. We have to test it with different cases to check if the greedy is providing the optimal result, but dynamic programming will generate an optimal solution using principle of optimality. The next difference is that in dynamic programming we choose at each step, but the choice may depend on the solution to subproblems. Whereas in greedy algorithm, we make whatever choice seems best at the moment, and then we solve the subproblems arising after the choice is made. So most of the time, it is easy to implement the solution with greedy. So these were the difference between greedy and DP. For example, we have the coin change problem. The coin change problem with greedy does not always guarantee optimal solution. Hey guys, welcome back. After knowing how to identify if a problem can be solved using dynamic programming, now in this lecture we're going to talk about how to approach the problems using dynamic programming. There are two ways to solve a problem using DP. First, using top-down approach, and second, using bottom-up approach. Top-down approach is combination of recursion and memoization. What is memoization? Memoization is storing the result of subproblems in memory so that we do not have to solve overlapping subproblems again. This way, using memoization, we speed up the program. So top-down approach is memoization on the top of recursion. And as you can guess from the name, it starts from the top. The way we solved the Fibonacci series was top-down approach. We started from n and we went up to the smallest value of n. So now how we avoid making the repetitive calculations? We store the result for each subproblem in memory, right? For example, in an array. So let's say we are initializing this array cells with -1 and then see this piece of code. First we check if the array is already having solution for the subproblem. If yes, then we directly return it from here. Else we need to solve the subproblem. If the value of n is 0 or 1, then it is the base case, so we fill 0th and first cell with 0 and 1 respectively, and along with that we return the values. Else we make the multi-branch recursive calls. And after getting results from those recursive calls, we combine them and add them, put them in the nth cell, and then we return the result. So this was the top-down approach to solve this problem, where we are starting from the top, that is from n, and then we go downwards. Now let's talk about the other approach to solve dynamic programming problems, the bottom-up approach, where we start from the bottom and go upwards toward the top. Unlike the top-down approach, which is recursion plus memoization, the bottom-up approach is simply an iterative approach. So we start from the smallest value. See here, we insert the bottom values 0 and 1, and then we start iterating from 2 to n and keep calculating and inserting the values into the solution array. At each point, the solution is sum of previous two values. That is what we do here directly inside the for loop. So the base case in top-down is generally the assignment in bottom-up. These were the two approaches for solving problems using dynamic programming. Now let's talk about the general approach to adopt when we solve a problem using DP. First, we find out the recursion in the problem, and then we pick between top-down and bottom-up. If we're picking top-down, then we store the answer for each subproblem in a table to avoid having to recompute them. And if we're choosing bottom up, we find the right order to evaluate the results so that the partial results are available when needed. That's all about approaching a problem using DP. Hey guys, welcome back. We have discussed a lot about dynamic programming and how we can achieve the solution using dynamic programming, right? Now let's start working on some problems. In this lecture, we're going to solve staircase problem with help of dynamic programming. So let's see what this problem is about. In this, you're given n stairs and step size. For example, step size can be 1 or 2. That means either you can take one step or two steps at a time. Now, objective is to find total number of ways to reach to the top. That is, to reach to the nth stair. So there are multiple ways to reach to the top, as you can either take one or two steps at each stair, right? For instance, if there are 4 stairs, you can reach to the top by taking one step at each stair. So one way is 1 1 1 1, so one at each step, right? Or you can take two step at first, then one step, and again one step. Or you can take one, then two step, and then one step. Or one step, and two steps. Or you can take two steps and again two steps. So there are total 5 ways to reach to the top. Now let's think of the solution. Let's say we have reached to the nth stair. If we have reached to the nth stair, obviously we have came from either n minus 1 step or from n minus 2 step, because step size is 1 and 2, right? So total number of ways to reach to the nth stair will be the summation of ways to reach to n minus 1 stair and ways to reach to n minus 2 stair. And that's the case when you're having step size 1 and 2 only. So if you have k step sizes, then what? Then you need to add ways to reach to n minus 1, n minus 2, going on to n minus kth step sizes. So that gonna be an arithmetic series. We can write it as summation of ways to reach to n minus jth step, where j is in range from 1 to k. And if you're given random step sizes like 2, 3, 5, etc., then j would be every step size. Let's say we have to reach to the fourth stair and the number of step sizes we have is 3. Either we can take 1 or 2 or 3 steps at a time. So let's calculate the number of ways to reach to the fourth stair. Let's create a method and let's pass n and the number of step sizes here. Let's create this method. This method is going to return the number of ways. Create this method, and here we gonna return number of ways, right? So let's return ways. Let's take a variable ways. Let's initialize it with 0, and now we're gonna take a for loop. This for loop is going to start from I equals to 1 and will go to I less than equal to k, because at the nth stair either we have came from the last stair, that is the n minus 1th stair, or from n minus 2th stair, or from n minus 3rd stair, right? So that is why we are running this loop, and here we are calling number of ways recursively by eliminating I from n. So this will become one call for n minus 1, one call for n minus 2, and one call for n minus 3. So that is how we get the ways. And now talking about the base case is when the n is 0, and in this case we're gonna return 1 as it will contribute one step, right? And if the value of n becomes negative, then we have nothing to do with it, so we're gonna return 0. Return 0. This is not possible that the step size is the value of n is less than 0. So this is the complete solution. Now this will return us the number of ways. Let's print it. So let's print ways and let's run this and see the number of ways are 7 to reach to the fourth stair. So how this recursive solution is working? We have 4 stairs and we can take either 1 or 2 or 3 steps, right? So to calculate ways to reach to the 4th stair, we need to calculate ways to reach to 3rd and 2nd and 1st step, right? Again, to calculate ways for 3rd stair, we will recursively calculate ways to reach to 2nd, 1st and 0th stair. And this continues. When we have negative values as n, take it as 0, and when we left up with n equals to 0, that's our base condition. So there we will return 1, as there will be always one way to reach to any stair from stair 0. So ways 1 will be 1, and then you have ways 0 which will return 1, and that's how ways to reach to second stair will become 2. Then you again have ways 1. To calculate it, you need to go down and get the result for the base condition, which will return 1, and again you have ways 0 that gonna return 1. So total ways to reach to the third stair will be 4. Then you have ways 2. you calculate it again by dividing into subproblems, and you calculate recursively. Same with the subproblem ways 1. Ways 2 gonna return 2 and ways 1 returns 1. So total ways to reach to the fourth stair will be 4 plus 2 plus 1, which is 7. So you can see we need to calculate ways 1, ways 2 more than once. We have overlapping subproblems in order to get the solution recursively. So to avoid that, let's implement memoization with this recursion, which is our first solution using dynamic programming, as this is the top-down approach. So what we do in top-down approach, we take an array to store result of each and every recursive call, right? So we're taking an array of n plus 1 size because we need to handle the base case when the value of n is 0, right? So we calculate ways to reach fourth stair by adding the ways at third step, at second step, and at the first step. But in order to calculate the ways at fourth step, we need to calculate the ways at third step, and to calculate the ways at third step, we have to calculate the ways at second step, then at the first step, and then at the 0th step, which is the base condition for us. So base condition will return 1. So we do update cell 0 with 1 in the array. So ways 1 will be 1 plus 0, that is 1. So we update 1 at index 1. Then for 0, we pick up the value present at index 0 and return this one. For negative values, it's gonna be always 0. So ways for 2 will be 1 plus 1, 2. That we fill at index 2. Now we have ways 1. This time we don't need to calculate it again. We will just pick the value from index 1 and will directly return it. Similarly, when we'll be having subproblem ways 2, we don't need to calculate it. We'll just pick the result that we've already calculated and store in the array. So this will continue and we get total 7 number of ways as the result. So let's implement this in the code. Here we've already returned the recursive code, right? Now to make it top down, we just have to memoize it. So let's memoize it. For that, let's take an array. Here I'm gonna take int array new int of size n plus 1, as we're gonna consider the case when the value of n is 0, right? So that's why its size is n plus 1, and now we're gonna pass this array here. Let's do this here, int array arr. And now before passing this array here, we have to initialize each cell with some initial value, and we're gonna put -1 at each cell. So let's take a for loop and at arri we're gonna put -1. Okay, now here we don't need this variable. Here we're gonna do everything using array, right? First we need to check if the array is already having that value, then directly return it from there. So if arrn is not equal to -1, then return this value. Now we don't need this variable. We are going to do everything in terms of this array. So here this is arrn and arrn, where we're gonna store this result for the nth cell, and here we're gonna call it recursively, and here we pass the array. But before performing the summation, we must put 0 at the nth cell because we are having -1 at the cell, so this calculation is gonna go wrong. So now let's store the result in the array for the case when the value of n is 0, and let's put it after these two cases, and finally let's return arrn, which is the value we wanted, And let's run this code. So we get seven number of ways. Now let's implement the bottom-up approach. So what we do in this approach will be having an array to store result exactly how we did in the previous approach, right? Difference is that we will start filling it with smaller subproblems first. We have the base case, which is when n is 0, and we will update the cell as 1 there. And then we iterate through this array, and at each step we add last k values from the array to get the ways to reach the current step. But consider a case when n is 1 and we need to add last 3 values from the array, as we have k as 3. So array 0 will be 1, but if you try to access minus first position or minus second position index, you're gonna get exception. So we put a condition: if the step minus j is greater than or equal to 0, we pick that value and add it to the result. Otherwise, we won't. Similarly, for n equals to 0, it will update 1 plus 1, which is 2. For 3, it will add all last 3 values, 1 plus 1 plus 2, which is 4. And 4, it will add last 3 values. These are 1, 2, and 4, which will be 7. So that's the total number of ways to reach to the top. Simple, right? Let's implement this in code. Let's start writing the code for bottom up. Let's call a method that's gonna return the number of ways using bottom up approach. So let's call it ways bottom up, and let's pass the value of n and k here. Now let's create this method. This is the implementation for bottom up. Let's tag it with this. And now here, similar to the top down, we're gonna create an array to store the results at each step. Starting from the base case, let's put 1 at the 0th cell for n equals to 0, and then we're gonna take a for loop to reach to the nth step. So it will start from 1 and it will go till I is less than equal to n. We've already taken the 0th case, we have already put the value of 1 there, so we are taking this loop from 1. And now at ARRI we're gonna put 0 so that we can do the calculation. Here we're gonna take another for loop for the number of steps that we can take at each stair. These are 1, 2, and 3. So this loop will start from 1 and will go till 3, which is the value of k. And now here inside this loop, we will calculate the value to be put at the ith index, which is equal to ARI plus ARR I minus j, right? And this I minus j may become negative sometime. So to avoid all the negative scenarios, we have to put a check here that I minus j must not be negative. So it must be greater than or equal to 0. And then finally we will return the value of ARR n. So here let's return ARR n. So this is the bottom up implementation. Let's test this implementation. Let's try printing the ways we are getting from this number of ways method. Let's run this and see there are 7 ways to reach to the 4th stair, which is indeed correct. Now let's observe the complexities. First, the time complexity for the recursive solution. So in this problem, we are making k number of recursive calls inside each call. As we have taken the for loop starting from 1, to step size k, right? We have taken 3 as step size for our example, so there will be 3 recursive calls at each step until we reach to the nth step or until we reach the last step. So the time complexity will be 3 raised to power n in this case. Now let's analyze what would be the space complexity for recursive solution. We are not storing values in any container, right? But we do have call stack. The maximum depth of the recursion tree will be n, so the space complexity will be order of n. Now talking about top-down and bottom-up approaches. In top-down approach, we are taking an array of size n to store the result at each step. So all the repeating recursive calls are going to cancel out and we will only be calculating the result at each step only once. We're not repeating calculations of any value. For example, if you want to find out the total number of ways to reach to the second stair, we don't have to recalculate the total number of ways to reach to the 0th or first stair. The recursive calls will find these values already stored in the array and will get these value from there, and after adding up these values we can get the value for stair 2. So that's why the time complexity will be order of n. Now let's see the space complexity for top-down. The space complexity for top-down will be order of n because we are having an array of size n, and we will also be having n entries in the stack at maximum, so it will be order of n. Now let's analyze the time complexity for bottom-up. In bottom-up, we have taken 2 for loops. Outer for loop to go through each step, and total steps are n, so complexity for outer loop is n and the inner loop is for step sizes. It starts from 1 and goes till k. So the total time complexity will be order of nk, but we can ignore k here as we're analyzing it asymptotically. So this will be order of n time. Now space complexity for bottom up. Space consumed is order of n as we have taken an array of size n to store the values at each step. Hey guys, welcome back. Let's get to the next problem, which is 0, 1 knapsack. I hope you're familiar with this problem now, as we have already solved fractional knapsack with greedy approach in greedy algorithm section. In knapsack problem, we are given a knapsack with capacity W and weights and prices of n items. So we need to put these items in knapsack such that it won't exceed knapsack's capacity and we get the maximum profit. Now the difference between these two is that with fractional knapsack, we're allowed to put fraction of items in the bag, right? But with 0, 1 knapsack, we have to put the complete item. So there are just 2 choices. You can add the item or you cannot add the item. For example, you have knapsack of capacity 10 and items are of weight 7, 4 and 5 and prices 15, 8 and 8 respectively. Now if we solve it with greedy approach, we will sort items as per their cost ratio, so it will pick the item that give us maximum profit with minimum weight, right? And that is the item 1. So the value will be 15. Now further you can't put any other item in knapsack as knapsack don't have enough space and you can't put fractions of item. So profit remains 15. Now think, is this the maximum profit that we may get? Nope. The optimized solution would add item 2 and item 3 so that the profit will be 16. So clearly this time greedy fails. Therefore, we need to take different approach and that approach is dynamic programming. Let's go with it. Let's first try to solve it with recursion. We have n items and we have 2 choices. Either we can include the item in the solution or we can exclude it. We do calculate profit in both the cases and go with the choice that's having maximum profit. So you include item 1 and calculate profit. How? You take the price of item chosen and check for the rest of the items. Can you include them in the solution after including one? Clearly you cannot. So capacity of knapsack is reduced to 3. So profit becomes 15. Now what if you exclude item 1? Then you just check for the rest of the items. Clearly, if you don't include 7, you can add these two items and get the maximum profit, which is 16. So there you got your sub problem. For n items, if you include the last n minus 1th item in the knapsack, you calculate profit by taking price of that item and the profit of remaining items with remaining capacity. That is price of n minus 1 plus recursively you're calling the same function for the remaining items with the remaining capacity. That is your first subproblem. And if you don't include the item, profit will be the profit for remaining items with the same capacity, right? So this is our another subproblem. But we have to choose the maximum and we check with which approach we are getting maximum profit, so the recurrence will be maximum of price of current item plus profit for remaining items with capacity W minus current item's weight, where the weight of the item must be less than or equal to the capacity. This is the first case. And the second one is the profit of remaining items with the current capacity. And then we're gonna choose one which is maximum of both. Let's see the complete recursive solution. So either we include the item or we exclude the item, right? So here see, if the weight of the current item is equal to or less than the capacity, then we can include it, right? So we are including the price of the current item and then we are recursively calling get max profit by eliminating the weight of the current item for the remaining elements or for the remaining items. So this is the case when we are including the current item. But what if we exclude the current item? So we have to calculate that profit as well. So here we are calculating get max profit for the remaining elements or for the remaining items with the current capacity. And then we find out the maximum among these two. And then we return it. So what is the base case for this recursion? It is either when the capacity of knapsack becomes 0 or we are left with no items. In that case, we will simply return 0. So with this approach or with this recursive approach, the time complexity will be exponential. Why? Because there might be overlapping subproblems. That function will compute again and again. Let's see how we can solve it using dynamic programming. So first approach is top to bottom, or we can say recursion plus memoization. Instead of solving overlapping subproblems again and again, we may create an array to store the profit that we calculate. Let's move forward to top to down. Now let's see how we can memoize it. So we need to take an array that can store result at each step, right? And as you know, there are two parameters, n, which is number of items, and w, which is capacity of knapsack, which are changing at every iteration. So we need to take a 2D array to store result of every recursive call. Like here, we have n equals to 3 and w equals to 10. To keep all results stored, we take a 2D array of n plus 1 multiplied by w plus 1 dimension, and we initialize it with minus 1. And as we made recursive calls in our naive recursion approach, we'll do the same. To fill the knapsack of capacity 10 with 3 items, we check values for n equals to 3 and capacity equals to 5. And now we check if the value is already calculated. we can see it's not, as there's -1 placed there. So in that case, we make recursive call and calculate profit for it. This continues till when we reach to our base case, which is if we are left up with 0 items or 0 capacity of knapsack. So we update that cell as 0. So now the recursive call F11 has its value 0 stored in the array. And in order to calculate profit for F25, we add price of second element, which is 8, right? And since F15 will also be 0, so we take 8 as the maximum profit among both for the subproblem F25. And then we update the cell to 5 as 8. So this is how we store result of every cell in this array. So that if similar subproblem ever occur, then that can be picked up from the array as it's already calculated. So let's code the top-down approach. These are the weights and prices of the items, and this is the capacity of the knapsack. Now we're gonna take an array of size n. So size will be weight dot length, right? So we're gonna create this array to store all the intermediate results, including the final result. So this is an array. Let's initialize it. Length of this array will be 1 plus n because these are the weights of 3 items, and we're gonna include the case when there are no items present. So that's why the size is of n plus 1, capacity plus 1. Now let's take a for loop to initialize all the cells with -1. So let's take for start from I equals to 0 till n plus 1 less than equal to, we can directly take less than equal to n and increment the I. And now one more for loop for j. So this will go to capacity less than capacity. And now at each cell, let's less than equal to capacity. Now let's put -1 at each cell. So ij equals to -1. And now let's create a method or call a method get max profit that will return us the result, the maximum profit from these items. So let's pass a weight array, the price array, n, the capacity of knapsack, and the values array. Let's create this method, and this method is going to return int. So now first we are going to check if the values array is already having the asked item or not. If it is already having that item, we're going to directly return that item from that cell. So values n-1, capacity n-1, capacity -1. So if this cell is having value other than -1, not equal to -1, then we will return this value. So return values n-1, capacity -1. As if the value is not present in the values array, we have to calculate it, right? So either we can include the current item or we can exclude it. The case when we're gonna include this item is when the weight of the current item is less than or equal to capacity. That is, if we can fit it into the knapsack. So in that case, we will include its price, and then we will recursively call get max profit for the remaining items. So here we're gonna pass the weight array, get max profit, and here we're gonna pass the weight array, the price array, and the first call was for n, so now we're gonna call for the remaining, so n-1, and the capacity is also reduced to capacity minus weight of the current item. So we're gonna pass capacity minus the weight of the current item that we've already included, and minus 1 and the values array. So this is the case when we are including the item. So let's take a variable int lines here, including. This is 0, initialize it with 0, and one more variable if we are excluding the element. So now the case when we are excluding the element, in that case we are not going to add the price of the current item. We are just going to call the get max profit recursively for the remaining items, and this time the capacity is not going to change as we are not including that item. So this is the case when we are excluding the current item. So we have implemented both the logics, and now we have to get the max of both among both. So whatever is the maximum, we have to return that. So first is int here and second is ex here. So let's put it into the current cell in the values array, so that if this is going to repeat, then it will fetch the value directly from that cell, and then finally return this value. Let's copy this and let's return it here. So now coming to the base case, we haven't implemented the base case here yet. So let's write the base case. Base case is when either we have no elements, no items present, or the capacity becomes 0. That is, now we cannot fit more items into the knapsack. So in this case, let's override the value at that cell. So values and capacity, this must have value 0 and return 0. So this is the complete implementation. Now it will return us the int value, the maximum profit that we can get using this dynamic programming approach or using this top-down approach. Let's print this value. Now let's try running this code and see if we get the maximum profit. So here we are getting 16, which is indeed the maximum profit which we can get by adding these two elements into the knapsack, right? So this is how, using memorization over recursion, we can implement the top-down approach. Now let's see how we implement the bottom-up approach to solve this knapsack problem. So we create a 2D array with similar dimensions. Difference is, in bottom-up approach, we start filling the array from the smallest problem. So we iterate through the array when items are 0, or when the capacity of knapsack is 0, which was the base case when we implemented the top-down approach, right? So here we update 0 in the array. So initially when item is equals to 0, we update 0, and similarly for item 1, when capacity is 0, we update 0. Now for I equals to 1 and j equals to 1, which is when the capacity of the knapsack is 1 and we have to fill the bag with exactly one item. So to fill this, we check if the first item can be added to knapsack. We can see it is having weight 7, so it cannot be added as the capacity is 1. So we exclude it and check, fill this cell with profit for remaining items, that is for I minus 1 comma j, which is the value for 0, 1, which is equals to 0. So we fill it with 0. Next, for capacity 2, again we cannot add I minus 1th element, that is the first item. So we exclude and update the profit of 0 second cell. This will continue till j is equal to 6. Now when j becomes 7, we have knapsack of capacity 7, right? So this time we can put one item 1, with weight 7. So we check profit when we include this item. To do that, we add the price of this I minus 1th item to the profit of remaining items with the remaining capacity. That is for I minus 1 items. with capacity, that is current capacity minus weight of chosen item. So we take price for 0th index, value for 0, 0 that we have already calculated, which is 0. So we add 15 and 0. This is the profit when we include this item. Now when we exclude this item, the profit will be the profit for remaining items, that's value 0, 7, which is having value 0. So max profit for this subproblem will be 15. Hence we update this 15 at the current cell. Similarly, we check for capacity 8, 9, 10 for item 1. The max profit for all these subproblems will be 15. Now next iteration. When we check for second item in the knapsack, first for the capacity 0, that will be 0. Next check if I minus 1th element can be added in the knapsack. We can see item second is having weight 4, so it cannot be added in the knapsack. Hence we exclude it and then we check for the profit for the remaining items with capacity 1, that is 0. So we update it with 0. Similarly, till j equals to 3, we update 0 as we cannot put the second item in the knapsack of capacity less than 4. And for capacity 4, capacity equal to 4, we check if we can include the second item. Yes, we can. So we calculate profit by adding price of this item to the profit for the remaining items of capacity 4 minus 4, which is 0. So hence profit gets 8. And if we exclude this item, we get profit 0. So clearly for this problem, profit 8 is maximum. So we update it with 8. So this continues for capacity 5, 6, the profit will be 8. And for j equals to 7, it checks for the profit. When we include second item, it is 8. And when we exclude it, we check for the profit for the remaining items with capacity 7, and that profit for 1, 7 is 15. So clearly here the profit 15 is maximum. That means in bag of capacity 7, if we exclude this item and go with previous profit, we get maximum profit. So we update 15 here. And again, same will happen for capacity 8, 9 and 10. Maximum profit will be 15. We continue this to fill for item 3 when capacity is 0, 1. We cannot include item as it is of weight 5. So we exclude it and take the profit for 2 items, which is 0. So we fill 0 here. Similarly, profit 0 will be updated for capacity 2 and 3. And for capacity 4, we still cannot add the item with weight 5. So we exclude it and update the profit for remaining items, which is 8. So this continues. Now let's try it in code. So bottom up, and here I'm going to invoke a method get max profit using bottom up. So in this we're gonna pass the weight array, the price array, price array, n, and the capacity. Let's create this method. Now here in this method, this is the bottom up code. Bottom up, and this is the code using top down approach. So now coming back to this bottom up code, here we're gonna take the values array to store the results. So let's take this array int. It's a 2D array of size and +1, capacity +1. So now we're gonna fill up this array with appropriate value for that cell. So we're gonna take 2 for loops similar to the loops we have taken while initializing all the cells of this values array in case of top-down approach. But this time we are not going to initialize this array. We are directly going to put the right value for the cells. So the first case is when the value of I is 0 and the value of j is also 0. That is, we have no items and the capacity of knapsack is 0. So in that case, that cell must be having value 0, right? So we're gonna fill all these cells with 0. So j is capacity, right? So now here, if this is not true, then we have to calculate the value at the cell, the price, the maximum price for that cell, right? So we're gonna take two variables, one when we are going to include the current cell and the other when we are not going to include the cell. So the case when we are going to include the cell is when the weight at that cell is less than equal to the current j, that is the capacity for that cell. So in this case we can include the item, right? So price of the item, price I minus 1 plus the price that we've already calculated at values I minus 1 and j minus this weight at the cell. So j is the capacity at that cell and the weight is the current item, is the weight of current item that we are eliminating from the current capacity. So the other case is when we are excluding the current item, that is we are not including the price of this item, and that's why we will be having j. And now we will calculate, or we will get the maximum out of this 2, and we will put it at the current cell. So math.max, and let's pass these variables, right? And now we're gonna fill the values I and jth cell with this value. So this is the implementation, and finally we can return the last cell, the value at the last cell, which is the result for us, right? So return value present at values n and capacity. Return. So this was very simple implementation to bottom up, right? So it's very easy to implement bottom up. This must return int. Let's print this maximum profit that we're getting in our main method. So let's sys out it. And now let's run this code. So see, it gets 16, which is the correct result for this knapsack 01 problem. Now if we want to print the complete table, we can take these two for loops and we can print each item, each element of this 2D array. So let's print sys out here values ij, give some space between the elements and change the line after each row. Now let's run this and let's see the table. So this is the complete table that we are getting, and at the last cell of this table where we are having our result. So this is how we can code the top-down and bottom-up approaches. Now let's analyze the complexities. First, for the recursive solution. So in recursive solution, at each element or at each index, either we are going to choose that item or we are going to exclude that item. And in both the cases, we are performing recursion, right? Either until we reach the knapsack weight limit or until we have included all the items. The worst case would be when we include all the n items in the knapsack. if we look to this time complexity thing. So as we're having two recursive calls to make inside each call, that's why time complexity is 2 raised to power n. We keep performing recursion twice inside each call until we reach to the nth item. So it is having exponential complexity. Now let's see the space complexity. At maximum, there will be n entries inside the stack. Other than that, we're not having anything, right? So the space complexity is order of n. Now let's analyze complexities we will get with a top-down approach. The time complexity will be order of nw, as we will be doing nw number of operations, where n is the number of items and w is the capacity of knapsack. We won't be solving the problems repeatedly, and we know that the total number of unique problems is nw, whose results we are storing in n cross w matrix, right? So the time complexity is order of nw. Now the space complexity. The top-down space complexity will also be order of nw, because we have taken an n cross w matrix to store the values. Now let's analyze the complexity when we choose to go with bottom up. Bottom up will also be having same complexities as top down. In bottom up, we're gonna take nested for loops for n and w. The outer one we are having is for number of items, and then inside this loop we are having a loop for capacities. So the time complexity is order of nw. Now the space complexity. The space complexity in case of bottom up will also be order of nw, because we're gonna take n cross w matrix to store the values. Hey guys, welcome back. In this lecture, we are going to understand coin change problem with its solution. So what is the coin change problem? We will be given a set of coin denominations and target amount for which we are going to make change using the given denominations. It is also given that the supply of given denominations is infinite. To make the target amount, you can use any number of given coin denominations. Let's say the target amount for which we are going to make change is 7 and the given denominations are 1, 3, 5, 2. So let's first see the recursive solution. So I think you know the subproblem. The original problem is for amount 7. Then from here we have to go with all the denominations we have. If here we are going for 1, then now the next subproblem is to make the change for 6. The target amount for the subproblem is 6. And if we go with 3, the next subproblem will be having the target amount 4. And if we go with 5, target amount will be 2. And with 2, the target amount will be 5. So with 1, the next subproblem is 6, right? Here again, we have 4 paths. Again, we're gonna go for all. Let's have a complete path when we keep on taking 1. So this is how it's gonna go. This is how the problem is going to get divided. Each path gonna stop either when it reaches 0. That means we have got all the coins needed to make that change, or when the denomination becomes greater than the target amount. As in that case, we won't be able to make the change using that denomination. See this call where we have target amount 4. Here we first go for 1, then we're gonna go for 3, and then for 5, and then for 2. But see here, the target amount for this call is 4, and using 5, we cannot make the change for 4 because it is greater than 4. So this recursion having this 5 is going to stop right here. This is how it works. Now shown is the complete path when we choose 1 as the denomination each time. So if we are taking only 1 rupee coins to make change for 7, then we're gonna end up having 7 coins to make change for 7. Too many coins, right? So at each level, we are going to try all the options that can contribute to make the change. And then we select the minimum among these options. Here, if we first choose 5, then the next target will be 2. And from here, if we choose 2, it becomes 0. In this case, only 2 coins are needed to make the change for 7, which is indeed the minimum number of coins to make the change for 7. So let's see the pseudocode. We're going to include the coin and we're going to calculate the coins required for remaining amount or for the subproblem, right? So let's call the function minimum coins recursively to get the minimum number of coins for the subproblem. And now in this result, we will add 1 for the coin we have already selected. But before this, we must check that the coin or the denomination must be greater than the target amount for that call. And this whole thing we're going to do for all the denominations available. So we will be writing this inside the for loop. Now this result is going to get overridden each time for each new denomination as we are having this stuff inside the for loop. So the last result we will be having here is the one for the last denomination. But what we want is we want to get the one having minimum number of coins, right? So we're going to put a check here that if the new result, which is subresult plus 1, is less than the previous one or not. If it is less than the previous one, then we're going to overwrite the result. So at the end of this for loop, we will be having minimum number of coins as the result. So this is the final result that we are going to return from here. Now talking about the base case is when the amount or the target amount becomes 0. So in that case, we're going to return 0. Now let's jump right into the code and see the actual implementation. So these are all the denominations and this is the length of this coins array having all the denominations and this is the total or target amount. Now let's create and call minimum coins method and let's pass this information. The coins array having all the denominations, the length of this array and the total or the target amount. So this call is going to return us the minimum number of coins needed to make change for 7. So let's create this method. So here inside this method, so what we're going to do, we have to call this minimum coins recursively to get the result for the subproblem. So here we're going to again pass this coins array, the length and the remaining amount for which we're going to get the minimum number of coins recursively. So here we're going to subtract the coins I, that is the current denomination. So let's take a for loop starting from I going all the way to n. And here we gonna increment it and then here we're gonna pass total minus coins I, that is the current denomination, which is the total or target amount for the next subproblem. And after that, this is let's call it subresult. And now when let's take it as int. So now when we add 1 to the subresult, we're gonna get the result, right? So result equals to subresult plus 1. Let's initialize the result variable. Let's initialize it with the maximum number of maximum integer value. So integer dot max value, as we want to select the minimum, so this will be helpful for us if we take it as a maximum value. So here before assigning it to result, we need to check this new result must be smaller than the previous result, right? So this new result is subresult plus 1, result plus 1, and this should be smaller than the result. And one more check here, we're going to insert one more check here, that the sub result must not be equal to the max value. Sub result must not equal to integer dot max value. It should not overflow. So now see, this everything, the stuff we're gonna do if the current denomination is either smaller than the target amount or equal to the target amount. So here total, and let's enclose this in this if block. And finally we're going to return this result here. Now the base case is when the total or the target amount becomes 0. So if the total is 0, then return 0. So this is the final implementation. Now let's see this main. Here we are getting the minimum number of coins needed. Let's print this value. Minimum coins needed, this number, this much number of coins. So let's run this program and see. So minimum coins needed, 2 coins. So we just solved the recursive solution, and this recursive solution is having loop inside the recursion. So the time complexity of this recursive solution is exponential, and this is obviously going to have overlapping subproblems. It definitely gonna consume much more time than time taken by other approaches. Now let's solve the same problem using dynamic programming. So first we have a top-down approach, which is recursion plus memoization. So we solve the recursion. Now we just need to memorize it to avoid recalculating the overlapping subproblems. So this is the recursive code, and we just need to memorize it to convert it to top-down code, right? So to memorize it, we're gonna take a map. That map will store target amount or the total amount as the key, and the minimum number of coins needed to make that target or total amount as the value. So let's create this method, minimum coins top down, and here we're gonna pass a map, new hash map, integer, it is the target amount or the total amount, and the minimum number of coins needed to make that total. Let's import hash map, and now let's create this method. Let's copy this implementation and paste it. And first we will check if the map is already having the minimum number of coins for that target amount, then we directly gonna return that minimum number of coins from here without calculating it again. So here, if hash map dot contains key total, then return hash map dot get the minimum number of coins for that total. Else it's gonna do this stuff, and here in this recursive call we have to pass this hash map. And finally, let's change it to minimum coins top down. And finally, when we're done calculating the number of coins, the minimum number of coins for that total, along with returning it as a result, we have to put it in the hash map. Hash map dot put total as the key and result as a value. So now this implementation is complete, and here we're just gonna replace this minimum number with min to see the result we are getting from this minimum coins top down. So let's run this program and see if we get 2. So yes, it returns true. So we saw the top-down approach, and using this approach we can avoid recalculating the overlapping subproblems. Here it is showing only 2 overlapping subproblems, but there will be so many overlapping subproblems, right, which we can avoid recalculating using top-down approach. So we saw the recursive solution and we saw the top-down solution for the coin change problem. Now let's see the solution using bottom-up approach. So in bottom up, we start from bottom right. So here we're going to divide the complex problem into simpler subproblems, and then we start solving them from bottom to reach to the top. And this is how we're going to get the solution. We keep on storing the results of subproblems, and then we use these results to calculate the solution of bigger subproblems, and finally we reach to the original problem with the final solution. So here we have divided the problem into subproblem. The original problem is of making the change for amount 7, and here the smallest subproblem is of making a change of amount 0. Then we have making a change for a total of 1, and then 2, then 3, 4, 5, 6, and then we have the original problem of making the change for amount 7. Now see the options we have. We can choose any of these denominations at the left to calculate the solution of these problems. We must take them in ascending order. So let's start solving these subproblems. The first subproblem that we have is for amount 0, right? And see the first row. For first row, we are only having the availability of coin 1. So what is the minimum number of 1 rupee coin that are required to make a total of 0? We literally need no coin. 0 1 rupee coins are needed to make a sum of 0. So let's fill the cell with 0. Let's go ahead for the next subproblem having the same single choice, which is of 1 rupee coin. We have infinite supply of 1 rupee coin. We can use as much coins as we need, but we cannot use 2 rupee coin, 3 rupee coin, and 5 rupee coin because this row is dedicated for the 1 rupee coin. So what are the minimum number of ways to make 1 rupee coin or 1 rupee target amount using 1 rupee coins? Obviously, the minimum number of coins is 1. We can use 1 rupee coin as the change. So now the next subproblem is 2. We need 2 1 rupee coins to make a target amount of 2. And similarly for 3, for 4, for 5, for 6, and for 7. Now coming to the next row. At this row we have the availability of 2 rupee coins as well as 1 rupee coins. So using how many 2 rupee or 1 rupee coins we can make a sum of 0? 0. We don't need any coin to make a sum of 0. Now next is 1. We just need 1 1 rupee coin to make a sum of 1. See here, these values are same as the values in the previous row. That means until we get the subproblem with amount equal to the current denomination, we don't have that denomination as an option in the answer. So here we're just copying these two values and putting it here because we're only using 1 rupee coins to form these targets. So while filling the rows, we don't change the results till we reach to the target equal to the denomination. The next target is 2. To make this target, we can either use 2 1 rupee coins or we can use 1 2 rupee coin. And the one which takes the minimum number of coins to make the change for 2 is when we use 1 2 rupee coin. So let's fill the cell with 1. Next, for 3 rupee coin or for target of 3, we can take 1 2 rupee coin and 1 rupee coin. Total of 2 coins, which is less than the coins needed when we use only 1 rupee coins. So minimum number of coins is 2, so we put 2 right here. But how we are actually getting this value? So to get this value, we go 2 steps back in the same row because this is the row for the denomination 2. That's why we go 2 steps back, and then from here we get this value, we add 1 to this value to get this value 2. Now we compare this value with the value in the previous row at the same column. The minimum one, we choose the minimum one and put that value right here. So the formula to get this value is, we get the value, first we calculate amount minus denomination. We subtract the denomination from the amount. The amount is 3 and the denomination is 2. We get 1. So now we see the value present at the index 1 at this row. And after getting this value, we add 1 to this value. Now we have to choose the minimum among these two values, the one we calculated and the value that we calculated at the same column in the previous row. Now the next target is 4. We follow the same process. 4 minus 2 gives us 2. At the index 2 we have 1. We add 1 to it and then we get the minimum among 2 and 4, which is 2. Same for 5, 6, 7. And our next row is for the denomination 3. Till we reach 3, we have to just copy the values from the previous row and we're gonna put them at these respective cells. Now at 3, we have to repeat this process. This is the formula to calculate the value at the cell. So this is how all the cells gets filled, and finally at the last cell, which is for the original problem, we get the final solution. So this is how we fill this table. Now we're going to implement the solution in code, but here it seems that we have taken a 2D array, but we don't need a 2D array to solve this problem. Because each time we calculate the value for the current cell, the dependency is only on the previously calculated values in the same row and on the value already present at the current cell. For instance, if we are calculating the value to be placed here at this cell, then all the cells before this are already having the updated values, and all the cells after this, including this cell itself, let's say, are having these previous values. Now the dependency of this new value is only on the previously calculated value at the same cell and on the previously calculated value in the same row. So we don't need a 2D array. So let's see the solution in code. So now let's create a method for bottom up. So let's call it mincoins bottom up. And here we don't need this hash map, so let's remove this. And let's create this method. So let's take the array in which we are going to store the results. Int array. The length of this array will be total plus 1. Total is the amount for which we have to calculate the minimum number of coins. So as we are going to start from 0, so this will be total plus 1. And at the 0th index, we're going to place 0. We're going to initialize the cell with 0 because for 0, we don't need any coins, right? So now this first for loop we're going to take is to initialize all the other cells other than the first cell in this array, and we're going to initialize these cells with maximum value of integer minus 1. Minus 1 because at multiple places we're going to increment this value by 1, so that's why. Now we're going to take the for loop for denominations, or you can say for the coins array. So it is going to start from 0 and it will keep running till value of I is less than coins dot length. We have already taken this value in len variable, so we can write len here. Now the inner for loop is for the array ARR, and this is for the total amount or the target amount, or you can say for the subproblems. So for subproblem is having the target amount 0. For that we need 0 at that cell, right? So we have already placed 0 at the 0th cell, so we're going to start this loop from 1 till arr dot length, and now here we're going to put the result at this current cell, that is at the jth cell of this array arr, and this result is, it is 1 plus the value present at the current subproblem minus the denomination value at that index. So it is j minus coins I. That's it. But before this, we need to check if this new value is smaller than the previous one or not. So here we're going to check if this value is smaller than the already placed value at the jth cell, then update this value. Else we don't need to update the value present at the jth cell. And before this check, we need another check to check that the current denomination must be smaller than or equal to the target or total amount. So it should be less than or equal to j. Let's enclose the stuff inside this if. And finally, after the completion of this implementation, return the value for the original problem, which is present in this array at total, because we need to return the minimum number of coins required to make change for this total. Now the implementation is complete. Let's go to the main, and here let's change this to min coins and let's run this program. So minimum coins needed 2 coins. Now let's analyze the complexities for coin change problem. In our recursive solution, we are performing recursion inside a for loop. And this for loop goes till the length of the coins array. Inside each call, we're making this many recursive calls, which is specifically 4 in our example, which we call branching factor. And the maximum depth of recursion tree is equal to the target. So here we're having 7 as the target amount, so the depth of recursion tree will be 7, which is when we keep choosing the denomination 1. So the time complexity will be the length of the coins array, which is the branching factor here, raised to the power target amount, which is the depth of the recursion tree. So if you have length of the coins array as m and the target amount as a, then the time complexity for the recursive approach of coin change problem that we implemented is m raised to power a. Now the space complexity. Space complexity is order of a for the recursion call stack, where a is the target amount, which is the depth of the recursion tree, right? Now comes the analysis for dynamic programming approaches. First, let's analyze the top-down approach. In top-down approach, we eliminate the repetitive operations that we had in the recursive approach. So we are only going to solve each problem only once, but we're still going to go a deep into the recursion. So the time complexity will be order of MA, where M is number of coins and A is the target amount. So we only be having this many unique problems. Now the space complexity. We've taken a map or dictionary kind of object to store key value result for each target, where we have taken target amount as key and the minimum coin needed to make the target as corresponding value, right? So we are starting this map from 0, or the starting the target amounts from 0 up to A, which is the original target amount of our problem. So the total space it gonna require is order of A. And also we're going to get a maximum A number of entries for recursive calls on the stack at a point in time. So still it is order of A. Now comes bottom up approach. So in bottom up, we took two nested for loops. First loop is iterating from 1 to m, that is for the denominations, and the second is iterating from 1 to a, which is for target amount. So the time complexity is order of ma, where m is the number of coins and a is the target amount. Now the space complexity for bottom up approach. The space complexity of bottom up is order of A, as we have taken an array of size A plus 1 to store minimum number of coins at each target starting from 0 up to A.
Hey friends, welcome back. The next DP problem that we're gonna discuss is longest decreasing subsequence. Subsequence is a subset of any sequence where elements are in same sequence and can be non-contagious. In longest decreasing subsequence, we need to find the length of that longest subsequence from the given sequence in which elements are in decreasing sorted order, that is from highest to lowest, and yes, elements need not to be contagious or unique. For example, you have an array, and to find decreasing subsequence, you check it like the first element is 20, then you check if next element is smaller than 20. Yes, then find the next element which is smaller than 8, which is 7. So first decreasing subsequence will be 28, 7, which is of length 3. Similarly, we need to find the other possible decreasing subsequence for this, which would be 20, then 12, then 10, then 9, then 7. So this subsequence will be of length 5. Similarly, next, 20, 16, 10, 9, 7, which is of length 5 again. In this way, you may find other sequences like 20, 10, 9, 7, 20, 9, 7, 20, 18, 7, and many more. But the longest subsequence will be these two, which are of length 5. So the LDS length for this sequence will be 5. Now when we understood the problem, let's see how can we solve it. If you see here, we are looking for every possible combination of sequence. For example, for 20, first you go with 28, 7, then you check for remaining array from 12 to 7. Then you again check for the remaining array. Once you are done with calculating the length for every subsequence for it, you choose the max value and return. So clearly this problem can be divided into sub-problems. We will calculate LDS for every possible subsequence that are contagious. And in order to calculate LDS length for subsequences, we have two choices. Either we include the particular element or we don't include the element in decreasing subsequence. If the element is smaller than previous element that is included in LDS, then we can include the element. Then we calculate LDS obtained by including the element, and we also calculate LDS obtained by not including the element. and we figure out with which choice we can maximize the LDS length. Like if you are at position 4, then you check if you can include the fourth element by comparing it to the previous element. Suppose that is 16. 10 is less than 16, so we may include this element and proceed further to calculate LDS. We will compare 9 with 10. It can be included. Then we compare 18 with 9. It cannot be included. So we exclude 18 and compare the next element 7 with previous element 9 in decreasing subsequence. Proceeding further, now we have no elements left to compute on. That's the base condition. We return 0 as array having no elements will have 0 length of LDS, right? So we compute LDS by including and excluding elements like this. 7 can be included, so we add 1 with remaining elements LDS, which is 0, and if we exclude 7, then LDS will be 0. So 1 is the max length, so we return 1 here. 18 cannot be included, so LDS remains 1 here. 9 can be included, so we add 1 with the LDS length of remaining elements, which is 1, so it becomes 2. And if we exclude the element 9, then it remains 1. So we return 2 here. Similarly, for 10, it will be 3. In this way, we get max LDS length at the end, which is 5. So what is the recurrence relation here? Max LDS length at any position I is the maximum value of LDS calculated when we include the ith element and exclude the ith element. Where we can include the ith element only when it is less than previous most element in decreasing subsequence. So let's implement this in code and understand the execution. This is array nums for which we need to calculate LDS length. We will create a recursive function that will get us the LDS length for given array starting from 0th index, and initially to compare 0th element we pass some max value as previous element. So we create function. Your return type would be int and it will be having arguments array and the current index and the previous element. First we write the base case when no element left to compute, that is the index of current element gets equal to the length. In that case, what we do, we return 0. So we return 0. Yeah. Then for each element, we have two choices. First, including the element. So we take a variable include, we initialize it with 0, and we check if the ith element is less than previous element. If yes, then we include and add 1 to the LDS length for remaining elements. So we recursively call this function. We put nums and the current element would be I plus 1 and the previous element would be the ith element. And as the second choice, we calculate LDS when we exclude ith element, which will be equal to the LDS length for remaining elements. So that's gonna be with current previous element. So we pass nums and I plus 1 and the current previous element, that is previous. Yeah. So at last, what we do, we return the maximum value among these two variables. So this will be the max LDS length for the given array. So we return max of include and exclude variables. So we are done. This is our first choice and this is the second one. What we are doing, we are calculating LDS in both the cases and returning the max value among them. So let's run this program. Let's print the result that we are getting from this method. Let's put some, so length of the LDS would be this. So let's run this program. So we get the length 5. So well, that's the brute force approach where we go through every possible subsequence and calculate length of LDS and then return the maximum. If we draw a recursion tree for this solution, we find there are overlapping subproblems which we are computing again and again. When problem has optimal substructure and overlapping subproblems, then we know we can solve them with dynamic programming. So let's see the first approach to solve this. Instead of computing the subproblems again and again, what we do, we can store the results obtained for a particular call in a 2D array, which is of size n plus 1 by n. Because we need previous to compare with 0th element and to store result of the complete array. So what we do, we initially fill the array with -1 and store the result of every recursive call at position previous index plus 1 and current. Like recursive call for previous index 1 and current index 7, it will store the result at position 2 and 7. So in this way, for all those overlapping subproblems, we won't need to make recursive call to compute them again. As now we have all the results stored in array. So we check in each iteration. If result is already computed for that iteration, we simply return that value. So let's do this in code. For this, we need to create a 2D array, right? So we create a 2D array and name it as dp, and this array would be of length plus 1, length of array plus 1, and the length of array. Now we need to fill this array with -1. So for array in this dp, we run this for loop and we fill this array with -1. So fill, put array here, pass array and -1. Now let's create method. Let me just copy this. So this method would be having arguments, this array and -1 as initially -1 as the previous index and 0 as current index and this dp array. So create method. This will return int, and let me just change the variables names. This would be previous index and this is the current index. So we have base case as if current element gets equal to length of nums, we return 0. So let's write this case and return 0. Then we calculate LDS for two possible choices. We include element include 0. We include element when current element is less than the element present at previous index. So we compare the current element with the previous element, and in this case we add 1 to the LDS length for remaining elements. So 1 plus get LDS for nums. Previous index will be the current index, and current will be current plus 1 for the next method call, and we pass dp. And initially we have taken previous index as -1, so we add a condition here. If previous index is less than 0, we can include the element. And next choice, we exclude element and calculate LDS with current previous element for remaining elements. So we pass nums and current previous index as previous index, and the current plus 1 as current index, and the dp array. Now we get the max value from these two choices. So we get max value from include and exclude, and we need to store it in dp array at the position previous index plus 1 and the current column. So we store at previous index plus 1 and current column. So we have stored the result in this at this position. Now we return this value. So we are done. Now we have stored the value that we have calculated. Now we put a check here that if for current iteration the result is already calculated, that is value at this position, if it is greater than or equals to 0, or sorry, greater than 0, then we simply return this value. So we are done. This is the memoization step where we are storing the result that we are calculating in this array. So we are good to run this code now. This is the top-down approach. This is the top-down, yes. So let's run this code, and we are getting the LDS length of 5. So difference is we now need not to calculate the LDS for similar subproblems more than once. What we are doing, we just pick the result which is already calculated from this array. So this is how we implement this approach. Now let's look at the bottom-up approach to solve this. What we do in this approach, we divide this into subproblems. We find the longest decreasing subsequence for subarrays like 0 to 1, 0 to 2, 0 to 3, and so on. And we store the result in 1D array. So if we have these results, we check at any position, can we increase the value of LDS by adding current element to the sequence. For instance, if we are at position 3 and we already have LDS for subarrays 0 to 1, 0 to 2, then we will check can we increase the LDS by including this element in the LDS. If we can, we will add 1 to the LDS, which is larger among the values that we have already stored in LDS array, and get the LDS for the subarray 0 to 3. So the logic is pretty much same. Let's see how we actually implement this. So what we do, we will take an array that will store the LDS values for all the subarrays, like at index 0 we store LDS for array 0 to 0, at 1 for subarray 0 to 1, and at 2 for subarray 0 to 2, and so on. So we will store them instead of calculating it again and again. So what we do, we initialize the LDS array with 1 and then we will try to maximize it. We will start comparing the values. We take I and j pointers. J gonna point the position for which we will calculate LDS and I for going through every element present before j. So let's start. For subarray 0 to 0, the longest decreasing subsequence will obviously be 1. So we start looking for position 1. So j is 1. We check if 8 is less than 20. Yes, so we can increase the value of LDS by including 8. So we add the LDS for element 0 to LDS for element 1. So it becomes 2. That's the LDS value for subarray 0 to 1. Now we increment j and we check if we can increase the LDS for subarray 0 to 2. If we compare 12 with 20, it is less than 20, so we can include it. So we add the LDS for 20 to this one, which is 1 again. So we update 1 plus 1, 2 at index 2. Now we increment I. Why? Because we need to check if we can increase the LDS even more. Now we check if 12 is less than 8. Nope, it's not. So we cannot include the 12 with the LDS sequence for subarray 0 to 1. So we don't update it. So the LDS for subarray 0 to 2 is 2. So increment j again and start comparing it with every element present before it. So 16 is less than 20. Yes. So we add 1. So it becomes 2. Then we check if 16 is less than 8. Nope. So do nothing. If 16 is less than 12. Nope. Again do nothing. So that's the LDS value for subarray 0 to 3. Let's move forward. Increment j. We check if 10 is less than 20. Yes. So we add 1 to LDS for 20 and increment I. If 10 is less than 8, nope. So we do nothing and increment I. If 10 is less than 12, yes. So what we do, we add 1 to LDS for subarray 0 to 2, which is 2. So it becomes 3, which is greater than current one, which is 2. And our goal is to maximize LDS, so we pick 3 and update it. Then we again increment I. Again we check if 10 is less than 16. Yes, so we add 1 to LDS for subarray 0 to 3, it will be 3. We compare if it is greater than current one, which is not, so we do nothing. So by this point, we have LDS for subarray 0 to 1, 0 to 2, 0 to 3, 0 to 4. So we keep on moving, we increment j and we compare 9 with all these previous elements and we maximize the LDS for subarray 0 to 5 and we get 4 here. And we continue, we increment j and we maximize the LDS for 18 and we get 2 here. Again we increment j and we now compare 7 with all these elements and we try to maximize the LDS length for the element 7. So at the end we get 5 here because we can include 7 in the decreasing subsequence. So at the end we can see the max value among these is 5, so the final result would be 5. That is the bottom-up approach. Let's see how can we implement this in code. We again create a method and this will be the approach bottom up. So we write bottom up here And this time we would be just needing the array nums, nothing else. So let's create this method. This will return int, and we start with the condition: if length is 0, that is array is empty, then LDS length will obviously be 0. So in this case we return 0. Now we create array max LDS, we name it max LDS, to store maximum LDS lengths for all these subarrays. So this array will be of length of given array, and we initially fill this array with 1. So let's fill it with 1. Now we need to take a variable to store the max LDS from all the calculated LDS. So we name it like max so far, and by default this variable would be 1. Now we need to go through every element and test every possible AND index of decreasing subsequence. So we take j to point every element. We increment the j, and for every j we again go through elements till index before this j. So we take I, and I will be pointing every element before j. So condition is I will be less than j, and we increment the I. Inside this, we check if the jth element is less than the ith element. If it is less than the ith element, then we update the maximum value among the current LDS length and length that we get by adding 1 to ith LDS value. So this would be the max value from the current max LDS that is updated at the jth position, and the max LDS value present at I plus 1. Once we finish going through every ith element, what we do, we will choose the maximum element from the last element and the current element. So basically what we are doing, we are keeping track of maximum LDS value with every iteration. And after going through all the elements, we get our maximum LDS length, so we return this value. So we are good to run this code now, and we get the max LDS length 5. So that is how we calculate maximum LDS length with the bottom-up approach. Now if we talk about time complexity for all these approaches, for the approach bottom-up, it would be O(n) square. As you can see, there are 2 loops running here, and similarly for the top-down approach it will be O(n) square. But with recursive approach we get exponential time complexity as we come across overlapping subproblems in this approach. However, there is another approach with which we can achieve complexity O(n) log n, that is using binary search with dynamic programming. So yes, there might be various techniques to solve a particular problem, but key is to get basic concepts of algorithm design techniques. Once you get that, you can identify and solve the given problem accordingly. Now let's quickly go through complexities of these approaches. With recursion, the complexity will be exponential. As for any given element in the array, there might be 2 possible states. Either it would be in the subsequence or it would not. So we do need to visit 2 to the power n possible subsequences. Now, space complexity. The algorithm is not taking any extra space apart from internal stack space, which would be n, as there will be max n recursive calls. So it's gonna be on if we count that. Otherwise, the complexity will be constant. With top-down approach, we do eliminate all the duplicate recursive calls, so the time complexity will left to be on square. And as we are using n 2D array for memoization, space complexity will also be n square. That's the extra space used by algorithm. Next, the bottom-up approach. In this, we are finding LDS for each of the elements, so we go through each n times. And again, we are doing linear work. We are going through the array for comparing elements with each other. So the time complexity would be n square. And space complexity would be on, as we are storing LDS length for n subproblems in the array. Welcome back. In this lecture, we are going to solve another dynamic programming problem called Levenshtein distance. In this problem, we will be given two strings and we have to calculate the added distance between them. That is, we need to find the number of minimum operations required to transform one string into other. There are three operations that we can perform. We can insert a character, we can remove or delete a character, and we can substitute or replace the character. For example, we have two strings, base and basic. We can convert base to basic by substituting E with I and then inserting character C. Though there might be other ways, but the minimum added distance will be 2 here. And if strings are Thursday and Tuesday, it will take two operations, as we need to delete letter H and replace the letter R with E. If we think of subproblems, we need to process all the characters of these strings. Suppose we traverse from the right side and we compare the last characters. If they are same, we don't need to do anything. We ignore them and check for the remaining characters. And if they are not equal, we have three choices. Either to insert the character of string 2, or to remove character, or replace the character with the character that we are comparing. So the subproblems here are, if the length of first string is m and the second string is n, then in the case when the characters are same, we ignore them and we check further for length m-1 and n-1. In other case, if we insert character, length for string 1 gets m+1 and string 2 gets n-1. So if we go with this choice, we need to further check for remaining lengths, which will be m and n-1. Similarly, if we remove last character, we will check for length m-1 and n. And if we substitute character, we further check for length m-1 and n-1. So we calculate number of operations in all three choices. Whichever is minimum, we go with the choice and add 1 for the current operation to it. We keep on doing this till we end up traversing one of these strings. In that case, the number of operations will be the length of the other string, as the only option will be to insert the remaining characters. So if the length of string 1 gets 0, then the minimum added operations will be the length of other string, which is n. Or if the length of other string, the string 2 gets 0, then the minimum added operations will be the length of string 1, which is m. Let's see the recurrence relation. Levenshtein distance for strings having length m and n will either be the distance for m-1 and n-1 lengths, that is the case when last characters are equal, or 1 plus the minimum among the distances that we calculate for all the possible choices, that are when we insert the character, when we delete the character, or when we replace the character. Or it would be the max of m and n, that is the base case where one of the string is of length 0. Now to optimize it a bit, we can merge these duplicate recursive calls. So what we do, we put k here, where k will be 1 when we replace character and 0 when last characters are same. Now let's implement this approach. So these are the strings and m and n are their lengths respectively. So we need to create method get distance with the arguments string 1, string 2 and length m and n. Let's create this method. The return type would be int here. So now let's implement the base case, that is if length of any of these string is 0, we return the length of other string. So what we do, we return max value among m and n here. Max from m and n. Now we need to implement choices. Let's say we have choice 1, that is insertion. So what we do, we add 1 for current operation and recursively compute the minimum operations for remaining strings. So we recursively call this method with arguments string 1, string 2, and the lengths will be m and n-1. Similarly with the next choice, for the deletion, here we pass length m-1 and n. Now the last recursive call. Before this we need to compute k. So what we do, we check if character at m-1 and character at n-1 index are equal. So we check character at m-1 and character at n-1 are equal. If they are equal, then we need not to do anything. So the value of k will be here 0 and otherwise it will be 1. So with choice 3 we make recursive call for m-1 and n-1 and we add k to the result. So let's write k here. Now what we need to do, we take minimum from these three choices. So we get minimum with this method min. We pass choice 1 and we again call math.min and we pass choice 2 and choice 3 here. And we simply return the minimum value among these three choices. Now let's print it out and just run this program. So this returns 2. So it takes 2 minimum operations to transform string Thursday to Tuesday or Tuesday to Thursday. Yeah. If we draw recursion tree for this, for each recursive call, we need to make 3 recursive calls. with lengths m n minus 1, m minus 1 n, and m minus 1 n minus 1 respectively. So clearly we can see there will be many recursive calls with similar arguments. That is, with this approach we are solving similar subproblems again and again. So to avoid solving the overlapping subproblems, we can go with dynamic programming where we solve smaller subproblems and use those solutions to build the final one. So first approach is memoization or top-down approach. So we will store results of subproblems in an array. As here are two varying arguments, we build a 2D array of size m and n, and that is initially filled with -1. Then we solve the problem and store the result of each subproblem at the position m-1 and n-1, so that whenever this function is called to solve for the similar subproblem, we just return the result. So at every call, we put a check if the problem is already solved or result is already present. So if it is present, we take that result instead of calculating it. Now let's quickly go through this in code. Now for top-down approach, we need to create a 2D array of the length m and n, and we need to fill it up with -1 initially. So we iterate through each array from this TP and just fill it up with this method. With -1. Now we need to create a method. This method gonna have arguments string 1. So we pass string 1, string 2, m and n, and with this array for memoization. So we create the method. Now for implementing the memoization with recursion, let's take the recursive code from here and just paste it. So now for every recursive call, what we need to do, we will store the result in the array that we have created for memoization. So just remove this and just store this result that we are calculating at each recursive call at the position m-1 and n-1, and simply return this result. Let's change the method arguments here. Pass TP. And now finally we need to put a check here if the result is already calculated, that is, if value at this position is greater than or equals to 0, we do nothing, just return the value present at index m-1 and n-1. So here we are done. Let's check if this code for top-down approach is working fine. Let's print it out. This is the top-down approach. Let's try top-down and just run the program. So yes, the added operations are 2 for these strings. So now with this approach, we are calculating just unique subproblems. Let's see the final approach, which is bottom-up to solve Levenshtein distance problem. As we did in previous approach, we create a 2D array to store result of all the subproblems. But this time we create array of size m plus 1 and n plus 1. Why? To handle the base case. That is, for 0th row and 0th column, we initially update the length of other string. As to convert a blank string to BAS, what we need to do, we will need to perform 3 added operations. So we update 0, 1, 2, 3, 4, 5 at 0th row and 0, 1, 2, 3, 4 at 0th column. Basically, at each index of this array, we will store the minimum number of added operations that we can perform on a substring of string 1 to turn it into another substring of string 2. How are we going to do that? Let's understand. We start from 1 and 1. So letters are B and B. These are equal. We need not to perform anything here. So we check for remaining string, as the number of added operation will be the one for the remaining string. So we can see here there's nothing. B is the first character in both the strings. So we update the added distance for 0, 0, which is 0. Now for 1, 2, B is not equal to A. So what can we do here? We look back here, B and B are same. So we just need to insert A. Or we delete B and insert B and A. So minimum of these all possible operations is inserting the character A, so it becomes 1. So we update 1 here. Next is letter S. B is not equal to S, so we look back to convert B to BA. It took one operation, so here we can add 1 to this and update 2. Similarly, for I, it will be 3, and for C, it will be 4. That means to convert B to BASI, it takes 3 operations, and to basic, it takes 4 operations. Now next is letter A and B, or we say we need to convert BA to B. In that case, we have choices. We remove A, we remove B, that are the 2 operations, and we add B, so it becomes 3. Or we substitute B with A, that is the 1 operation, and then we remove A, so it becomes 2. Or we just say B is already there, we don't need to do anything, so we just remove A, so that will happen in just 1 operation. So here 1 is the minimum, so we update 1 here. So what is the pattern here? At every index, we are looking for these 3 neighboring indices, and we are choosing the one which is minimum, and then adding 1 to get task performed. And that's the case when characters are not equal. If they are equal, we go diagonally and update the added distance for the remaining strings. So the formula is we compare the I-1th and J-1th character, as we are starting from 1, 1 to fill up this array here. So for iteration I and J, we're gonna check if I-1th and J-1th character are equal. We fill up the added distance for I-1 and J-1 position. If not, we look up at the 3 neighboring indices that are at J-1, I-1 and J-1, and I-1 and J. So we pick up the minimum one and add 1 to it. Now let's quickly implement it in code. Let's start. Let's create another method for the approach bottom up. And this method will have just string 1 and string 2 as arguments. We don't need anything else. Let's create this method, and this will return int. So first what we do, we will create a 2D array. Let's say ltest, that will be of size m plus 1 and n plus 1, that is string 1 dot length plus 1. and string 2 dot length plus 1. And then to handle the base cases, what we will do, we will update the first row with 0, 1, 2, 3 and so on. So we will just put the values for 0th row and for every column I, the value I. Similarly, to fill up the first column, that is 0th column, we will update 0th column for every row with value I. Now next, we will start iterating through rest of the indices. We will start from I equals to 1 and it will be less than or equals to string 1 dot length, and then j will do start from 1 and we will iterate till string 2 dot length. So now for every character at I minus 1 and j minus 1 in string 1 and string 2 and string 2, what we will do, we will check if these characters are equal. If they are equal, we will update the value present at I minus 1 and j minus 1 to the current cell. So the current cell will be ij and we will take the value present at I minus 1th row and j minus 1th column. Else what we will do, we will look for the neighboring indices and get the minimum value among them. So we will update the value at current cell and the value will be minimum from all those cells. First it will be the value at I and j minus 1. Second, the minimum value among the value present at I minus 1 and j and the value present at I minus 1 and j minus 1. And then we will add 1 for the current operation. So let's add 1 with it. Now finally, we will return the last value calculated that will be present at position string dot length, string 1 dot length and string 2 dot length, that is present at the indices m and n. So this is how at the last index we will be having the minimum added distance to convert the given string 1 to given string 2. So let's run this program and we got the number. So what we have done here, we checked for the every character present at string 1 and string 2. If the characters are equal, we looked up diagonally and updated the minimum added distance for remaining string to the current cell. And if they are not equal, we looked for the minimum added distance for the remaining strings, that those are the 3 neighboring indices for the current cell, and added 1 to the minimum value among them. So this is how we do calculate the minimum added distance with the bottom up approach. So hope you got the whole idea about Levenshtein distance and how do we solve this problem with all the 3 approaches. So this is all for this lecture. See you in the next. Let's analyze the complexity for Levenshtein distance problem for all these approaches one by one. In recursion, there are three available choices to perform at every recursive call. So the time complexity will be exponential, that's the 3 to the power m, where m is the length of the first string. Now, space complexity. The algorithm is not taking any extra space apart from internal stack space, so counting that, it would be mn, as there are m cross n recursive call possible at a time. Now with top-down approach, we do eliminate all the duplicate recursive calls, so the recursion tree will left to be just of m cross n size, so the running time will be mn. And as we are using n2d array for memoization, the space complexity will also be m cross n. That's the extra space used by algorithm. Next, the bottom-up approach. In this approach, we are going through both of the given string to find the edit distance for all the smaller subproblems. So running time will be mn, and space complexity will also be m cross n, as we are storing LDS length for all the subproblems in the array. But this can be further optimized by observing that we only need the value of 3 adjacent cells in the table to find the value of the current cell, right? So you may try that solution.
Welcome back. By now, I'm sure you have got the pattern and the basic idea what we do in dynamic programming and what kind of problems generally are solved using this approach. As we promised, we're gonna cover a bit more problems that falls under this design technique, as generally people do struggle a lot understanding these optimization problems. So in this lecture, we're gonna understand the very classical optimization problem, that's a rod cutting problem. In this problem, we are given a rod of some size n, let's say n is 4, and we can cut it into smaller parts, that is any number of smaller pieces, where every piece would be of some specific price. Now the task is to sell this rod in such a way that it gives us the maximum revenue. So every piece of rod is of different price. We choose that bunch of pieces by selling which we get the maximum price. It can be rod of size 4 itself if selling bigger piece is giving max revenue, or even 4 smaller pieces of size 1 if they are making the revenue maximum. Suppose these are the prices for pieces of length 1, 2, 3 and 4. In this case, if we divide the rod into two parts of length 2 and 2, we will achieve max revenue, which will be 10. So how we solve this? We look for all the possible combinations and see where the first cut will be. If it is at length 1, we check max profit for remaining length base, which is 3. That's basically our subproblem. We recursively find the maximum revenue for a rod of length 3 and add it to the price of the first piece of rod. That will be the max revenue where at least one piece of rod is of length 1. Similarly, we calculate the revenue when a cut is at length 2. If one piece of length 2, we check for rod of remaining n-2 length and we add the max to the price of second rod. Same goes with piece of rod of size 3 and 4. This will cover all possible combinations in which the rod can be cut, as we are dividing the given rod in two pieces at every recursive call, which are I and n-I. So for a rod of size n, we check combination starting from every I length piece till the length n, where the next piece can be of length 1 to n-I. So we do calculate obtainable revenue for each combination and choose the one which is maximum. So we create a function that will calculate the max revenue that we can achieve by cutting the rod of length n, and we calculate for every iteration I by adding the price of current length with the revenue for remaining length n minus I. Here I is in a range 1 to n, so we recursively check the total obtainable price in each case and return the maximum. Now the base case is when length of rod is 0. In that case, the price will be 0. Let's code this recurrence relation. We will be having a price array that's gonna have all the prices for all those lengths, and we need to get its size. Now we need to create a method rod cut that gonna have price and size as its arguments. Let's create this method. The return type will be int. Let's change it to n. Now we need to implement the base case first. That is, if rod is of length 0, the revenue gonna be 0. Now we take minimum integer as the max revenue initially. So we assign the minimum integer, min value to max revenue. And now we need to divide a rod of length n into I and n minus I pieces. So what we do, we take a for loop and we start from length 1 to length. Now we calculate the revenue for each length. We take price of the I length piece, which is at position I minus 1. And for remaining n minus I length, we recursively find the max revenue. So we choose the max revenue, which will be the max from the current max or the one that we have calculated. So we pass max revenue here and this calculated revenue as the second argument to this. Now we simply return this max revenue. So we are done. Let's print the result. This will be the max obtainable revenue for the given prices. So yes, we are done. Let's run this program. And here we get the result. The maximum revenue that we can obtain is 10. Now, if we change the price for the rod of length 1 to 4, the max revenue will be 16, as it will choose 4 pieces of length 1 to maximize the revenue. So this was the recursive approach. With this approach, the solution has the exponential time complexity. Now, considering this approach, if we draw a recursion tree, we can see there are overlapping subproblems. So this problem clearly has optimal substructure and overlapping subproblems, so we can solve it with dynamic programming. First approach is top-down approach. With this approach, we memorize all the results of recursive call in an array. So we take an array of size n and store result of every nth call at n-1th index. For instance, here first recursive call will be for n equals to 3. then 2, and then 1. And finally, we reach to the base case. It gets value for n equals to 1 and store at index 0 in this array. Then we calculate for n equals to 2 and we go through every possible combination and get the max among these values and store here in this array at index 1. Now for n equals to 3, we calculate other possible combinations here. Here when we come across the problem that is already solved, which is for n equals to 1, we don't calculate it further, we just pick the value from the array and again choose the maximum among these values and store it to index 2. Same continues, we don't again calculate similar subproblems. Rather, we take the result directly from the array and finally calculate the max revenue, which will be at n-1th index. Let's quickly code this. We need to create another method for the approach top-down. Let's try top-down here. And this method will have an additional argument that is an array of the same size to store the every result. So let's create this method. This will return int and let's write this n. Now just simply convert the recursive code to this top-down approach. This is having the base case and here we are calculating the max revenue for each length. Now what we need to do, we just need to store the result in this array at position n-1 before returning this. And it's done. Now we check if the result is already calculated. So we check if there is already a value present at the index n-1. If it is, we will return the value present at n-1 index. So in the case of any subproblems, this won't compute the revenue again. Now let's run this program and see if we are having correct result. So revenue is 16. Next, the bottom-up approach. In this approach, we take an array of size n+1 where at 0, we store the value for rod of length 0, which is the base case. So we store the maximum revenue generated by each length I. For example, for rod of length 3, we use results stored at 0, 1, 2 indices for these subproblems. Let's understand. We take I and j pointers, I for pointing rod of every length till n and j to go through results of subproblems, as we need to calculate maximum among all n-I pieces. Here I ranges in 1 to n and j in 1 to I. Now we start from rod of length 1. For length 1, we cannot cut it into further pieces, so the max revenue will be price of 0th index, that's 1. So we store it at ith index, so we store 1 at the index 1. Next, for the rod of length 2, we look for combinations. First, not cutting it into any pieces, so we add the price of first index with 0. Next, we decrement j and look for next combination, which are of length 1 and 1. Or in other words, first piece of length 1 and for next we take the result present at I minus j position, which is 1. We add these values and choose the maximum, that is 5. So we store 5 at the index 2. Now for I equals to 3, first possibility to not to cut it, so we add price for that piece which is at j minus 1 index. That's P2. Or we can cut this rod into the length 2 and 1. So for the first piece, we just take the price of that piece, and for the second one, we take the max revenue that we have already stored at I minus j index, that is 1. Or the next combination, that can be first piece can be of length 1 and the second piece can be of length 2. For the length 1, we just take the price of it, and for the length 2, we take the position, we take the max revenue that we are having at the index 2. So we will take these values, and we can see among these values the max is 8, so we just fill this max revenue at the position I. So this continues. For every combination, we are taking the price for the first piece, and for the remaining n minus ith piece, we are taking the max revenue that we are having in this array. So what we are doing, to calculate maximum revenue at each length, we need to calculate the maximum of price for chosen j length rod plus the revenue for remaining I minus j length. So here I is ranging from 1 to n, and we need to iterate again for the different values of I, which we do with the pointer j. So j is in range 1 to n minus I. Let's implement the same. So we create another method for the approach bottom up. Let's write bottom up here. And this method won't need to have any other arguments, as it is an iterative approach. So we create this method, this will return int. Now inside this, we need to create an array to store revenue generated by each length. This will be of size n plus 1, that is of price dot length plus 1, yeah. And we assign 0 at 0th index for the rod of length 0. Now we take max revenue, initially the minimum value. Now we need to fill up the array. We start from length 1 and we go till n. And for every length, we take j starting from 1 to the length I. So max revenue for current j and I minus j length of rod will be math.max, and we choose from the max revenue and the revenue that we are calculating by adding price for jth piece and the max revenue for remaining I minus j length. And then store this result in this array at index I. And at last, simply return the max revenue that will be present at the last index in this array. Now let's run this program, and we get the appropriate output. So this is how we implement dynamic programming in both these approaches. The complexity will be O(n) squared in the bottom-up approach, and as well as with the top-down approach, which is much better than recursive, with which we have exponential time complexity. I hope you are getting more familiar with these problems, though each of them has different way to get solved, but you can think for the solutions in these different approaches starting from the naive recursive solution. So this is all for this lecture. See you in the next. Let's quickly go through complexities of these approaches. First, for recursion, here first think how many cuts we can make on a rod of length n. Starting from 0, we can make up to n minus 1 cuts in the rod, right? So if we sum up overall possibilities starting from k equals to 0 to k equals to n minus 1 number of cuts, we will get 2 to the power n minus 1. So the time complexity is exponential here. And space complexity will be constant if you just count auxiliary space taken by algorithm. Otherwise, there will be n recursive calls on the stack frame at a time. So in that context, complexity will be On. Now for top-down approach, we are making recursive calls for each length for every possibility to make a cut. So the complexity will be On square, as it won't have any duplicate recursive calls as we had in recursion. Space complexity will be On because we are using an array for memoization. Similarly, with bottom-up approach, we are going through each possible choice of cut for every length, right? So that's why time complexity will be On square. And we are having one-dimensional array of size n to store the profits for each length. So space complexity will be order of n. Welcome back. Let's move forward to our next problem, which is matrix chain multiplication. In this problem, we are given a sequence of matrices or a chain, for example 4, 3, 2, 5. That means matrices are of size 4 by 3, 3 by 2 and 2 by 5. The problem is to find out the most efficient way for multiplying matrices of these dimensions. So we don't perform the actual multiplication, we just figure out how many operations it will take to multiply matrices. Now the first way to perform multiplication could be multiplying first two matrices that will take the multiplication of 4, 3 and 2 operations, that are 24, and then multiplying the result matrix to third matrix. That will take multiplication of 4, 2 and 5, that is 40 more operations. So parenthesizing first two matrices will take total 64 operations. Another way is to multiply these two matrices first, that takes 30 operations, and then multiplying the result with the first matrix. So overall this will take total 90 operations. Though multiplication is associative, that means either way we will have the resultant matrix of size 4 by 5. Yet in which order we parenthesize the product affects the total number of operations required to perform the multiplication. Clearly, if we go with this way, we need to perform less number of operations, so this is the most efficient way. So in problem, we will have some sequence of suppose n numbers. That means we will be having n minus 1 matrices. Here the size of every ith matrix is the value present at I minus 1th index and ith index. Like for matrix A1, the size will be 40 by 30. For A2, it will be 30 by 10 and so on. So we need to find minimum operations to multiply all these matrices. Now let's think of the solution. Suppose we have 4 matrices. Now first way to put parentheses after matrix A1, that is multiplying result of A2, A3, A4 with A1. Now for multiplying A2, A3, A4, there are two ways: multiplying A2 with A3, A4, or first multiplying A2, A3 and then to A4. And to multiply A3, A4, there is just one way, as well as for A2, A3 we have one way. So that's the first way for multiplying A1, A2, A3, A4, we can also put parentheses here and multiply A1, A2 and A3, A4 first, then multiply their resultant matrices. Or we can multiply first 3 matrices first and then multiply it with A4. Here again, we check every possible order in which we can perform multiplication. That's how we're gonna divide this problem into subproblems. We start from I and go till j and check for each position k where we can place the bar. We compute operations in every case and go with the one which is minimum. Like first, we place the bar at 1 and we check for both the sides. In left, that is whereas I is equals to k, there's just one matrix, and in right side we start from k plus 1 and check till j. In the same way, we place the bar at 2 and divide it into two subproblems where first starts from I to k and second from k plus 1 to j. Similarly, the third one, where we place the bar after third matrix, that means we multiply first 3 matrices first and then the last A4. Now we compute the number of operations for each subproblem. If at any side there is just one matrix, then no operation will be required for that subproblem. And for other subproblems, we need to recur and compute operations for left side of the bar, that is from I to k, and for right side of the bar, that is from k plus 1 to j, and then the number of operations required to multiply the resulting matrices, and we take dimensions for them from the given sequence, which will be present at index I minus 1, k and j. For instance, for this sequence, we have 3 matrices. Here k is at index 2, I at 1 and j at 3. So the number of operations in combining the resulting matrix and this third matrix would be the value present at I minus 1 index multiplied by value at k and value at j index. As this first resulting matrix will be of size 4 by 2, that are the value present at I minus 1 index and kth index, and the second matrix is of 2 by 5, which are the value present at k index and j index. So let's see the recurrence relation. To compute minimum number of operation for sequences of matrix starting from I to j, we divide it into two sequences with k and recursively compute minimum operations for sequence I to k and from k plus 1 to j. And we calculate operation required to multiply the resulting matrices. The total number of operation will be the addition of all these operations, and we choose the minimum among all possible ways. Here k, from where we split the sequence, is in range from I to j, and the base case is when there is a single matrix. That means if I is equals to j, then number of operations will be 0. Now let's implement this in code. We have a sequence of numbers, let's say 4, 3, 2, 1, 5. That means we have 4 matrices of size 4 by 3, 3 by 2, 2 by 1 and 1 by 5, and will be the length. Now we create a function MCM. We will pass the sequence and the starting ending indices initially, which will be 1 to n minus 1. This method will return int. Now implementing the base case, where we say if I is equals to j, that means we are having just one matrix, so the number of operations of this will be 0. Now let us say number of operations are very large for now. We take max int initially and try to minimize this number. We'll place a bar at every place starting from I to j, and we calculate operations for the current order. What we do, we divide the current sequence into I to k and k plus 1 to j, and recursively find number of operations for them. Plus we add the operations to multiplying the resulting matrices. And among all possible values, we need to pick the minimum one. So this will be the number of operations, and we pick the minimum from these two values. Finally, we return the result. So we return the min ops. Let's print it out and invoke this method. This returns the minimum number of operations to perform multiplications. Let's stick it inside. And run this, and we get our answer. Now if we talk about the time complexity, like other DP problems, this recursive approach has exponential time complexity. This is the recursion tree for matrix chain 4. You can say this is having similar subproblems. MCM34 is called twice, MCM23, MCM12 and many more subproblems are computed more than once. So this problem can be solved with dynamic programming, where we use array to store the result of all subproblems. Let's do that. First way to memoizing the results in top-down approach, we build a two-dimensional array as we have two variants in recurrence, which were I and j. Now this matrix will be of size n by n, where each cell represents a subproblem. Like cell 2, 3, this cell will have result of the subproblem 2, 3. That means when we compute number of operations for a to a3 multiplication, we will store it to this cell. We fill this array with -1 initially, and for the base case, when I is equals to j, we put 0 at these diagonal indices. And we continue to fill array while solving every problem recursively. The final result, which will be for multiplication for all 4 matrices, will be stored at location 1, 4. As I is 1 and j is 4 here. So we return value present at this index. Let's implement this. So we create a two-dimensional array for this approach. It will be of size n by n. And initially, we will fill this array with -1. So just fill with -1 here. Now we need to create a method for this. We'll pass this array along with those arguments to store each subproblem result. So this approach is top down, and we invoke the method passing the sequence and the starting ending indices along with this array. Now simply we just need to convert the recursive code in this top-down DP code. Let's take it here. Now we just need to store values which are getting computed. In base case, store 0 at index ij before returning, and similarly after computing minimum operations for each k, put the value of minimum operations at index ij. Now let's change the method signature of all these recursive calls. Let me just make it more precise. All right. Oops. Yeah. Now, at each recursive call, we check if the subproblem is already solved. If it is, the value present at ij will be greater than or equals to 0. In this case, we simply return that value rather than calculating it again. So we check if it is available, then we just pick that value and return. So this is done. Let's run this. And the minimum number of operations is 38. Let's try the bottom-up approach where we start filling the table from smaller subproblems first. We create an array of n by n to store minimum number of operations for each subproblem. We know if we want to get minimum number of operations for these four matrices A1, A2, A3, A4, we have to know the result for all these smaller subproblems, which are of chain length 3, 2, and 1. So the main focus would be length while we implement this approach. We start filling the table for smaller length of sequences. We know if there's single matrix, the number of operations will be 0. So in this array, we put 0 at cells 1, 1, 2, 2, 3, 3, and 4, 4. Now to solve other subproblems, logic is same. We will put k at different indices between I to j and calculate minimum number of operations for every sequence. Now to get those different length sequences, how do we locate ij pointers? Let's understand that. Starting from two length sequence, if I is at index 1, our j should be at index 2. So that will be a two length sequence. Similarly, if I is 2, then j should be 3. So 1, 2, 2, 3 and 3, 4, these will be all two length sequences. We put k and split them into 1, 1 matrix and we know their answers. We add 0, 0 and the number of operation to multiply a1, a2, that will be multiplication of 4, 3 and 2, which is 24. So at index 1, 2, we place 24. In the same way, we fill values for 2, 3 and 3, 4. Next, we move three length sequences. Again, I starts from 1, j will be at 3. We start to place k from I. K at 1, we split it into a1 and a2, a3. We have answers for these two. For a1, it's 0 and for a2, a3, it's at index 2, 3, which is 6. And we add number of operations to perform multiplication of the resulting matrices of size 3, 1. So logic is same. We multiply value at I minus 1, k and j. So it will be multiplication of 4, 3 and 1, which will be 12. So total operations in this case will be 18. Now we change k to check if with the next option we can get operations less than 18. So left sequence is a1, a2. For a1, a2, value is at 1, 2 position, which is 24, and for a3 it's 0 and number of operations to multiply these will be multiplication of 4, 2 and 1, that's 8. So total operations in this case will be 32. So among these 18 is the minimum, so at index 1, 3 we update 18. That simply indicates for matrix chain 1 to 3, the minimum number of operations will be 18. So we are having result of smaller subproblems with us to compute the bigger one. So next sequence would be A to A3, A4 when I is at 2 and J will be at 4. And we calculate operations when K is at 2 and 3. And update the minimum value at index 24, that is 21. Now the last problem is of length 4. We just have one problem of length 4. So when K is at 1, we need to perform 81 operations. And when K is 2, that's when we multiply result of A1, A2 and A3, A4, we need to perform 74 operations. And when K is 3, we just need to perform 38 operations, which is the answer. So while implementing this approach, we solve smaller length sequences first. We go through every length and set our ij pointers. For each length, pointer I will start from 1 and go till n minus length. Like if length is 3, I can move till index 2 only. As if it goes beyond 2, it won't find sequence of length 3. And if we need to fix j as well, when I is 1 for length 3, j would be I plus length minus 1, that's 1 plus 3 minus 1, that will be 3. Or for length 2, if I is at 2, then j will be at 2 plus 2 minus 1, that's 3. And then we simply put k in range from I to j to compute minimum number of operations for multiplying matrices. At last, we get minimum number of operations at nth column of the first row. Hope you got the logic. Let's code it now. So we need to create another method. This will be for bottom-up approach and pass here sequence, and let's create this. This will return int. Now firstly, we create two-dimensional array. This will be two-dimensional. And this will be of size n. Let me take n. So we have created this array. Now we start filling it with smaller length of subproblems for I equals to 1 till n. We fill diagonal indices with 0. And then we start from length 2 and go till n. It's 2 and we will go till n for solving the subproblems of every chain length. Now inside this, we're gonna take I. That I will be in range 1 to n minus length. As we saw, I cannot move beyond n minus length. So it will be less than and equals to this value, and we increment this. Now for j will be at I plus length minus 1. So this will create a sequence frame of current length. Now if j becomes equal to n, in that case we have to end that iteration as there will be n minus 1 matrices. N is the length, so we will be having n minus 1 matrices. So we don't need to go to nth iteration. Now with ij, we have our sequences. Let's take min ops and initialize it with max value. Now we just need to split the array with k and then compute the minimum number of operations. So we take a k loop that is starting from I and go till j. Now we will take min ops and the value will be minimum among the values calculated before, and to calculate it we take the values present at cell I and k, plus we're gonna add k plus 1 and j index value, and then the result of multiplying the both matrices that will become by this multiplication. And now we need to store this value in the array at the position I and j. So we store this min ops in this array at location array I and j. At last, we return the value at index 1n. Eventually, we will get the minimum distance, the minimum number of operations at this location. We are good to run this code now, and we get the result. Now with these approaches, if we check the time complexity, so in the worst case scenario with bottom-up approach, it will be O(n) to the power 3. As there are 3 running loops, as you can see, and even with the approach bottom-up, with top-down, we will have the same complexity, as we are computing n square subproblems and that we are computing n times. So it will be O(n) to the power 3, which is not actually great, but better than exponential that we were having with recursion. So that's how we solve matrix chain multiplication with these different approaches. This is all for this lecture. See you in the next.
Let's check complexity for matrix chain multiplication for all the 3 approaches. In recursion, what we are doing, we are dividing given sequence into 2 parts. That is from I to k and k plus 1 to j, right? And recursively finding the number of operations. So we can say branching factor is 2, and we are doing this till j, that's basically number of total given matrices, and that is n. So the complexity would be 2 to the power n. That's exponential. Now, space complexity. Space complexity is the depth of recursion tree if we consider recursive call on the stack, that is n. So space complexity will be O(n). Now, moving forward, top-down approach. In this, we are optimizing recursive approach with memoization. So the size of recursion tree gets reduced and it will compute just the unique subproblems. And if we check for unique subproblems, we are calculating number of operations by making 2 recursive calls in every iteration, right? That is for calculating minimum number of operations from I to k and k plus 1 to j sequence matrices. So that makes runtime order of n square. Now for each subproblem there might be n splits possible, right? So we can place the bar at place 0 up to n in the worst case. So that makes complexity O(n) to the power 3. And space complexity, it will be O(n) square, as algorithm is consuming n squared space for storing result for each subproblem.
Similarly, with bottom-up approach, for getting final result starting from sequence 0 to n, we need all I to k and k plus 1 to j results before. So we are solving smaller subproblems first. So here the first loop takes O n running time and rest is n square in the worst case. Therefore, total time complexity will be polynomial, that is n to the power 3, and space complexity would be n squared for the array that we are using.
Hey guys, welcome back. It's time to summarize this section. So here we got to know what is dynamic programming, how we can identify, how we can approach the solution using top-down and bottom-up approaches. We compared dynamic programming with few other techniques, and then we tried out some of the problems using dynamic programming. I'm sure you might have solved those problems, and now you're ready to apply them into your next coding assignment. Great. Here comes end of the section. Let's move to next technique in next section. So see you there. Bye-bye. Hey guys, welcome back. In this video, we are going to discuss maximum contiguous subarray sum problem. And the optimal solution of this problem is given by Cadane's algorithm. So this video is about how to solve maximum sum subarray problem using Cadane's algorithm. So let's go ahead and understand what this problem is. So we will be given an array having negative and positive integers, and we need to find the subarray in this array having maximum sum. So if this is the array, then in this array, the subarray having max sum is the one with elements 2 and 5, right? There can be so many subarrays. You can have this as the subarray, you can have this, you can have this, you can have this. So there can be many subarrays, but remember the elements must be contiguous. You cannot have this as the subarray because it is not contiguous. There are two elements between them. So I hope you got the problem. So how we can approach this problem? The naive solution that first come to mind is that you start from 0th index. You get the sum at here. In this case, it is 5 as we're only having one element. And then you move forward and include the next element. If the sum is greater than the previous sum, you update the result. You see the previous sum was 5 and now it becomes 2, as 5 minus 3 is 2. So the previous sum was greater than this new sum, so we don't update the value here. And then you move forward to include the next element. So this time we are covering 3 elements. This time the sum is 0, still 5 is maximum, so we won't update the result. And this is how we cover all the elements till n. And this is the way we get all the subarrays starting from 0. And then we do the same for the next index and for all the other indices. This is how we get all the possible subarrays and their sum, and we find the one with maximum sum. But for this solution, we will be needing 3 for loops. One to fix the starting index, next 2 inner loops, one for deciding the coverage and another as a pointer till that coverage. So as you can see, this solution gonna take cubic time to complete. There can be many solutions to this problem. There can be a recursive solution. Recursive solution takes exponential time. There can also be a quadratic time solution to this problem. But the most optimal one, the linear time solution of this problem, is the one using dynamic programming. And it is given by Cadane's algorithm. So how Cadane's algorithm solves it in linear time? In Cadane's algorithm, we get the max sum ending at each index. See here, the max sum ending at index 0 is minus 2. Now the max sum ending at the next index can either be minus 2 plus 3, that is 1, or it can be 3. As 3 is greater than 1, so the max sum at index 1 is 3. Now see at minus 1, that is at index 2. Here the sum is either the max sum at the previous index, which is 3, plus the current value, or it can be the current value. So you can see the max one is 2. Now the max sum ending at index 2 is 2. So the idea of Cadane's algorithm is that the local maximum subarray sum is either the sum of previous maximum and current element, or it is the current element. Whatever is the maximum, it becomes the new local max. So we get all the local max at each index, and then we find max out of them. And this is the solution. And this is much faster approach as it only takes O(n) time. So in this approach, you don't have to keep left and right pointers at indices to get the sum of elements between those indices, because at each index we are holding on to the max till that place. We're not interested in knowing anything about the subarrays not having the max, so we're not keeping track of that. So see this. At index 2, either we can take -1 or we can sum it with the previous result. That makes it -1 plus 3, that is 2. So 2 is greater than -1. So the chain is going on. And then comes -3. If we sum it with the previous value, it becomes -1. -1 is still greater than -3. So we include it, and then we have -2 at the index 4. So this time if we add -2 to previous result, which is -1, it becomes -3, which is smaller than -2. And we keep -2 this time. And this is the point where the chain breaks. So if you see here, this chain was going from index 1 to index 3. We were taking the previous sums and then we were adding the current values. Now at index 4, we were taking the value itself, and here a new subarray starts. However, we don't need to focus on the indices at which the subarray or the chain is starting or ending. We just need to know the maximum sum each index is ending up with. Alright, let's move ahead now. Here at index 4, we won't be including the previous result, as this value itself is larger than the previous max, right? And now here at index 5, we have 2. We will take the current, as the local max, the previous local max plus current is smaller than this current. And then at index 6, we include the element 5, or we include the current in the previous maximum. So max sum till index 6 now becomes 7. And then we have -3. We include it again in the previous local max to get the new local max, as this sum -3 plus 7, which is equals to 4, is greater than -3. And then at the last index, index 8, we add 5 to previous maximum to get this 9. So here we have all the local max. Now we get the max out of these local max, which is 9, and this is the final solution. Let's try this in IDE. So this is the array, and now we're going to create the method max sum subarray, and we're going to pass this array in this method. So let's pass the array, and it's going to return an integer. So let's take int max sum, and now let's create this method. Now inside this max sum subarray method, we're gonna take a for loop, and this for loop is going to start from 1. So int I equals to 1, and I is less than arr.length and I plus plus. And the max sum ending at 0th index will be the value of the element itself, right? So we're gonna initialize the global max and the local max initially with this element. So global max initially is the first element of the array. And similarly, the local max and local max ARR0. Now we're going to calculate the local max for each I inside this for loop. So local max is either the sum of previous local max and the current value, local max plus ARRI, or it is simply ARRI, the current value, right? So we need to get the max among these two values, and that will be the new local max. So math.max. And now when we get the local max, each time we're gonna see if this local max is greater than the previous global max or not. If it is greater than the previous global max, we can update it as the new global max. And this is how we will get the final maximum global max. So here again, we're gonna use math.max to get the maximum of these two, local max and global max. So let's pass them global max and local max. And this is the global max. And let's return this global max here. Now let's print this max sum, sys out max sum, and let's run this. So it gives 10, which is the sum of this subarray. So this is how you can implement this problem. You can implement the solution of this problem using Cadence algorithm in a very few lines of code, which can execute in linear time. Now let's analyze the complexity of Cadence algorithm. The time complexity of Cadence algorithm is order of n, that is linear time, because there is only one for loop which scans through the entire array exactly once. Now the space complexity for Cadence algorithm will be constant as it uses up constant space. We're not using any structure to store anything, right? Hey guys, welcome back. In this video, we are going to discuss Bellman-Ford algorithm to find out single source shortest path. Bellman-Ford algorithm help us find the shortest path from a source vertex to all other vertices of a weighted graph. Let's say this is the weighted graph we have been given, and each edge in this graph is having a weight. And this weight is the length of the path. Now we have to find out the shortest path from the source vertex to all the other vertices. We can also use Dijkstra algorithm to deal with such a problem, but Dijkstra algorithm cannot work well with graphs having negative weights. And here see we are having negative weights. So we should go for Bellman-Ford. And Bellman-Ford uses dynamic programming, unlike Dijkstra that uses greedy algorithm. Alright, let's go ahead and see how it works. So we apply this algorithm when we have single source. So let's say that the source where we're going to start from is A. So first we overestimate the length of paths from starting vertex to all the other vertices. And let's say all the other vertices are infinity distance apart from starting vertex A. And obviously the distance of source from itself is 0. And now we're gonna iteratively relax these estimates by finding new paths that are shorter than the previous estimations. And how are we gonna do this? So we're gonna pick two connected vertices let's say u and v having distance du and v having distance dv, and the cost to reach from u to v is cost uv, then if the addition of distance of u and the cost of uv is smaller than dv, that is smaller than the distance of v, then distance of v can be relaxed or updated as the sum. So this we're going to do for all the pairs. And we're not going to do this just once, we're going to do this for all the pairs repeatedly. So if we have n vertices, then we have to do it exactly for n minus 1 times. And by doing this repeatedly for all the vertices, we can guarantee that the result is optimized. So let's have all the pairs here. So we have AB, we have AF, we have AD, we have BC, CE, DE, FB, FC, and FE. So now let's start the iteration. First pair is AB. See the value at B, it is infinity, and at A we are having 0 and the cost is 8. So when we add 0 and 8, the sum is smaller than infinity. So the distance of B can be updated as 0 plus 8, that is 8. Next pair is AF. Again, see the distance at A is 0 and the distance at F is infinity. And the cost is 5. So when we add 0 to 5, it is smaller than infinity. So we can update DF. Next pair is AD. Again, 0 plus 3 is smaller than infinity. We're going to update DF as 3. Now next pair we have is BC. B is having value 8 and the cost is 6, which is 14, and it is smaller than infinity. So let's update DC. The same we're gonna do for all the other pairs. The next pair is CE. So at E we are having infinity and 14 plus 4 is 18. So we're gonna replace this infinity with 18. Now next pair is DE. At E we are having 18. Now we're gonna relax this edge as 3 minus 1 is 2. So we're gonna update it to 2. Next is FB. At B we are having 8 and the value of F is 5 and the weight is minus 4. So 5 minus 4 is 1. So we're gonna replace 8 with 1. Next is FC. At C we are having 14 and 5 minus 1 is 4. So again we're gonna replace it with 4. Now the next FE. Here at E we are having 2 and 5 minus 3 is also 2. So we're gonna keep this 2. So at the end of this iteration, we're gonna have these values. But this was the first iteration. We have to make n minus 1, 6 minus 1, that is 5 iteration. So again, we're gonna do the same with these sequence of pairs. Again, we have to start from the first pair AB and then we have to go till FE. So this will be the second iteration and then the third, fourth, and then the last iteration, fifth one. So we're going to do this for a total of 5 times and then finally we're going to get the solution at the end of 5th iteration. In many cases, you may get the solution in initial iterations as we got the solution in the first iteration, but there can be cases that may give you the solution in the last iteration. So we always have to go for n minus 1 times because the optimal solution is guaranteed only when we iterate n minus 1 times. So this is how this algorithm works, and there is one drawback of Bellman-Ford, that it cannot work with negative cycles. What is a negative cycle? See this, these vertices are forming a cycle, right? So when you sum all the weights for these vertices, you get a negative number. And that's why it is called a negative cycle. So if there is any negative cycle in the graph, then Bellman-Ford algorithm will not work for that. So let's start writing the solution to this problem. We will be needing a graph. So I've taken this class as graph, and in this graph we will be needing number of vertices and number of edges. So V for number of vertices and E for number of edges. Now we're gonna be needing array that can store all the edges along with the information, and this edge itself is a class. So let's create this class edge, and here we will be having the source vertex of this edge, the destination vertex of this edge, and the weight of this edge. Let's say W. Now let's create the constructor for this edge class to define these variables. So let's create this constructor, and we're going to initialize all these variables with 0. D0. So we have created the edge class, which will be holding the complete information about the edge. Now we have to construct the graph, right? So let's create the constructor. This constructor will be having V and E as the input parameters. V is the number of vertices and E is the number of edges, right? So let's take int V and int E, and now let's define these. This dot V is V and this dot E is E. Oh, let's change this to E. Now let's initialize the edge array, and the length of this edge array will be equal to the number of edges in this graph, right? So now let's, after creating this edge array, we need to initialize each cell with a new edge object. So it is going to go till E, and here inside this for loop we're going to initialize each cell with a new edge object. So new edge. Now going to the main method, here we're gonna create a graph G equals to new graph, and in this constructor we will pass V and E, that is number of vertices and number of edges. So number of vertices is 6 and number of edges is, let's say, 9. Now let's say A is the 0th vertex, A equals to 0, and B is the first, to 1, C is second, D is third, E is fourth, and F is fifth. So now for the first edge AB, we're gonna set up the values of source vertex, destination vertex, and the weight. So A is 0, B is 1, so the source vertex is 0, edge 0, as this edge is present at the 0th index. So the source vertex is 0 and the destination vertex for this edge is 1, and the weight of this vertex we have taken, or we've been given, is 8. So weight equals to 8. Now the next vertex is AF, which is present at the first cell. So for AF, the source is 0 and the destination vertex is 5. So 0, 5, source is 0 and D is 5. And the index is 1 and the weight is also 5. Now the next edge is AD. Let's copy this and let's edit it for AB. This is the second cell and the source is 0 and the destination is 3. Second cell. And the weight is, let's say, 3. So now without wasting much time, let's paste all the other edges. So these are the total 9 edges that we have in our graph, and now we're going to call Bellman-Ford method And in this method, we're going to pass this graph and the source vertex. Source vertex is the 0th vertex, so we're going to pass 0 here. Let's create this method. And in this method, we're going to take an array to store all the distances. Let's change this to source. And let's take the int array, int array distances, or dist equals to new this int array. So the size of this int array will be equal to the number of vertices, right? So because we're gonna store the distances for each vertex from the source, right? So we're gonna fetch it from the graph and we're gonna pass it here. Now let's take a for loop to initialize all the vertices distance with infinity. And for us, infinity is integer dot max value, right? So we're gonna initialize all the vertex or all the distances for the vertices with infinity or integer dot max value. So distance of I is equal to integer dot max value, and the distance of source from itself is 0, right? So for source s, it should be 0. So we have initialized these distances, and now we have to relax the edges for n minus 1 time, right? And in our case, n minus 1 is v minus 1 because v is the number of vertices, right? So let's take a for loop for I equals to 0 till v, and the inner for loop for e for edges, because we have to go through each edge for v minus 1 time. So for e, we have to fetch it from g. So this should be plus I, and this should be plus j. So we're gonna first increment it, and then now we're gonna fetch the values for u, v, and cost, u, v, and c. U is the source vertex, right? So this is u, int u, and v is the destination vertex, so int v is g dot edge j dot d, and the cost is the weight of the edge, so c is e dot edge j dot w. So now we're going to apply the Bellman-Ford formula. First, we're going to check that du is equal to max value or not. It must not be equal to the max value. So distance of u must not be equal to max value, and then we're going to check that distance of u plus the cost uv plus c is less than dv or distance of v or not. So if it is less than distance of v, we can relax it and we can update the value for distance v. So distance v will be then equal to this sum. That's it. Now the only thing we need to do is to check for negative cycles. So if there is a negative cycle in the graph, we're going to print that the graph contains negative cycle. So after the execution of these for loops, we will be having the optimal solution, right? But even after the execution of these for loops, we're not having optimal solution, or we are able to get the shortest distance using this Bellman-Ford formula, then obviously there is a negative cycle involved. So what we're gonna do, we're gonna copy this code and let's paste it here. If we still get this equation true, that if still the distance of u plus c is smaller than distance of v, then we're gonna print that this graph contains negative cycle. So let's print it here. Sys out the graph graph contains negative cycle. That's it. Now we just need to print the values or the distances from the source to each vertex. So let's take a for loop to print the values. So taking it starting from I, and it will go all the way to v minus 1, and here we're gonna print I and di, the corresponding distance. So plus di, distance I. So now the implementation is complete. We just need to run this program to test this. So let's run this code, hit the run button, and see this is the result. A to A distance is 0, A to B is 1, A to C is 4. These are the shortest distances from A, because A is the source node. So this is how you can solve this problem using Bellman-Ford to find out the shortest distances of each vertex from the source. Now let's talk about the complexity of Bellman-Ford algorithm. First, let's talk about the time complexity. So the time complexity of Bellman-Ford algorithm is order of V multiply E, as we are going through each edge for V minus 1 time. And now let's analyze the space being consumed up. So if the graph is already given to us and we're just told to write the algorithm, then we won't be writing the graph class and filling up the data or edges in that graph. We would only be implementing our Bellman-Ford function, right? And in that function, we're just taking an array to store the distances, which is of size v. So space complexity will be order of v. Hey guys, welcome back. In this video, we are going to discuss topological sort using Kahn's algorithm. So what is topological sort? Topological sort, or topological ordering of a directed graph, is a linear ordering of its vertices such that for every directed edge uv, the vertex u to vertex v, u comes before v in the linear ordering of that graph. Alright, in what kind of problems we can apply this technique? Imagine there are several dependent tasks. They are dependent on each other in a certain sequence. For example, see this graph. Here you have 5 tasks to do. These are named 1, 2, 3, 4, and 5, right? Now here, see that if you want to complete the third task, it has the dependency on the second and the fourth task. So when the second and fourth task will complete, then you will be able to start the third task. And the second and fourth task further have dependency on the first task. So to start second and fourth task, you gotta complete the first task. So do you see this chain that we have to follow? Here we need topological sort, which can convert this graph to a linear ordering. In job scheduling problems, this is a very common scenario that you will encounter if you ever get a chance to work on scheduling. And in large systems, there are thousands of jobs running that are dependent on each other, where this topological sort works wonder. It resolves the dependency problem, it uncomplicates them and arranges them linearly. So a topological sort takes a directed graph and produces a linear ordering of all its vertices. Now, after understanding why and where we use topological sort, now let's go ahead and see how this algorithm is designed to bring these vertices in linear order, or how you can solve such kind of a problem. So the Kahn's algorithm or technique is that first we find out the in degree of each vertex. In degree is the number of edges coming into the vertex, and out degree is the number of edges coming out from the vertex. So let's find out the in degree for all these vertices. Let's start with 1. There are no edges coming into the vertex 1, so in degree of vertex 1 is 0. Next is vertex 2, and there are two edges that are coming into the vertex 2. So the in degree of vertex 2 is 2. Now let's check for 4. It is having one edge coming into it, so in degree is 1. Now see for vertex 3, it's having two edges coming into it, so in degree is 2. Now the last node or last vertex is having one edge coming into it, so the in degree is 1. Now we are going to select the vertex with minimum in degree, or you can say 0 in degree, and after selecting it, we can delete this vertex along with all the edges coming out from it. Now the graph has changed and we again have to update the new in degree. There's only one edge coming into the vertex 2 now, and there's no edge coming into vertex 4. So the new in degree for vertex 2 is 1, and for 4 it is 0. Now pick the one with 0 in degree, which is 4, and delete all the edges coming out from it. Again update the new in degree. 2 is now having 0 edges coming into it, 3 is having 1 edge coming into it, and 5 is also having 0 edges coming into it. Again we have to select the one with 0 in degree, but this time we have two vertices with in degree 0. No problem, we can select either of them. So we can first select 2 and then 5, or we can take 5 and then 2. Because there can be more than one topological sort possible in the graph. Alright, let's take 2 and then 5. Let's delete the edges coming out from 2, and we're left with 3 with in degree 0, and we select it. That's it. So we have arranged these vertices linearly. This is the final linear order, and if you take 5 first, then this will be the final order. So this is how Khan's algorithm does the topological sorting. Now there's few things you can observe here, that for applying topological sort, it is necessary that the graph is directed, right? Else the topological sort can't do anything. If the graph is not directed, then obviously you would never want to sort it in a linear order in the first place. And the second thing is that you cannot apply the sorting on a graph having cycles in it. For example, if the order of two vertices are dependent on each other, see here, we have u and v here, and to start the task v, u must be completed, and also to start the task u, the task v must be completed first. So both are dependent on each other and we are locked here. So we can't do anything in this case. That's why it will not work with graphs having any kind of cycles in them. It can only be applied on DAG, that is on directed acyclic graph. So let's start writing the code for topological sort using Khan's algorithm. So here we're gonna be needing graph, right? So I'm going to create a class graph, a static inner class, because I've already created a class named graph in this package. That's the only reason I'm creating it as inner class. So this graph will be needing the number of vertices and an array that can hold array lists. So this is an array which holds lists of integer. Let's call this adjacency array, and now we're going to create the constructor for this graph class, public graph, and this constructor is going to take the number of vertices as the parameter. Now let's assign this to this dot v. Now we're gonna initialize this array. So this is an array of list, so array list, and the size of this array is equal to the number of vertices basically this array is going to store the adjacency list of each vertex at the corresponding cell. So here we're going to take a for loop so that we can initialize each cell with a fresh array list. So here this is a at j I equals to new array list. So we have created the constructor. Now we have to create a method to add the edges in this graph. So let's create a method add edge, and this will take int u, which is the source vertex, and int v, which is the destination vertex, as the edges are directed. And now here we are going to add v in the list present at u, right? So this is like if you're having edges, one edge which is directed from 1 towards 2, and you have another edge which is from 1 to 3. Then when you call this twice for these two edges, this will have a list at index 1 holding 2 and 3. Okay, so for 1 we will be having 2 and 3 in the list. Okay, now let's come to the main method and let's construct the graph. So graph g equals to new graph, and in the constructor we're gonna pass the number of vertices. Let's pass 6, and now let's add edges to this graph. So g dot add edge. Let's say the first edge is directed from 1 to 2, and second edge is directed from 1 to 4. Third edge is directed from 2 to 3, just like we had in the slides. And then the next edge is directed from 4 to 2, and another one from 4 to 3, and the last edge from 4 to 5. So now let's construct a method that will sort this. G dot topological sort, and let's create this method. So here in this method, the first thing we're gonna do is to create an array that will hold the int degree for each vertex. So let's call it this is array, int array int degree, and the maximum int degree any vertex can have is number v, as you cannot have more int degree than number of vertices, right? So now we're gonna take a for loop and we're gonna fetch the list one by one from the adjacency array, and we're gonna take that in temp. This is v, however both are same, but we can avoid recalculating it. So now here let's fetch the list present at ith index and let's take it in temp. So aj I, this is an array list, so let's say array list, and now let's cast aj I to array list. So now we're gonna calculate the int degree for each vertex. Okay, so let's take a for each. So for each integer vertex present in the temp array, we will take it and we will update the int degree for it. So this is we're gonna do for all the vertices, so this will count the int degree for each of the vertex. and we'll store it in the in degree array. So after calculating the in degree, what we need to do, we need to get the one having in degree 0, right? So we're going to create a queue, and we will see the node or the vertex having in degree 0, and then we will add it to the queue. And there can be more than one vertex having the in degree, so we will add those vertices in this queue. So equals to new linked list, and now we're going to run a for loop from again 0 to v, and here we're going to check if the in degree of the current vertex is 0. If in degree I is 0, then add it in the queue. Okay, so the work of queue here is getting the vertex with in degree 0 and then keeping it until we add it into the result. And then again for the next iteration we'll do the same. It will have the next vertex having in degree, and we are taking this count so that we can know the number of vertices we have already selected. Okay, so this count is 0. Now we're going to add the element present in the queue from this queue to our result vector. So we're going to take a vector that will store the result, vector integer. Let's call it linear order. New vector. Now we're gonna take all the selected vertices from the queue and we're gonna store them in this vector, which is linear order. So while the queue is not empty, poll the element from the queue. So queue.poll, and let's call this element that we are getting x, int x, and let's add this in the linear order. Now what we're going to do, we are going to see all its neighboring vertices and we're going to decrease the in degree for those vertices, as we have deleted that vertex along with the edges coming out from it. So for each vertex present in the array list at jx, remember at jx itself is an array list, each cell is holding an array list. So the vertices that are present in this array list, for those vertices we can decrement the in degree. So vertex, and if this in degree, this new in degree becomes 0, then we're gonna add these vertices in the queue so that they can be processed. Vertex, right? So after this we will increment the count as we have selected the vertex. Now we have to check for if the graph contains a negative cycle, and you know that after selecting all the edges the count will become equal to the number of vertices, that is, it will become equal to v. But if it is not equal to v, that means the graph contains negative cycle. So in that case we're going to print that the graph contains negative cycle. Graph contains negative cycle. And if this is the case, we're gonna return from here without doing anything further. And if it is not containing negative cycle, we will print the final order, the linear order. So we are taking this for each to print the each index, each item present in this linear order, each vertex present in this linear order. So let's print this out, I plus space. So this is the complete implementation. Let's print the linear order as this. So this is complete. Now let's run this and see the order, and let's match it from the one we got. So this is the order that we got. Here we are getting 0. This is because I have taken 6 as the number of vertices to match this result with the explanation video, but we are only having 5 vertices, right? 1, 2, 3, 4, and 5. And as arrays start from 0, we are having that extra vertex at the top in the solution, but it's not having any mapping. So it's coming at the top. Now if we want to have only 5 vertices, we gotta replace these vertices 1, 2, 3, 4, 5 with 0, 1, 2, 3, 4. So let's replace them. If let's say we are only having 5 vertices, and if the name is 1, then change it to 0, 2 to 1, just decrement 1 from every number. This is 2, this is 1, this will be 3, 3, 2, and 4, and 3. Now let's rerun this to see the output. See, we're getting 0, 3, 1, 4, 2. This is equivalent to the result we were getting. If we add 1 to each one of them, we'll get 1, 4, 2, 5, and 3, which was the result. Okay, so this is how we can use Kahn's algorithm for topological sorting. Now let's analyze the complexity of Kahn's algorithm. Kahn's algorithm is going to take up order of v plus e time. This is because we are traversing through the complete adjacency list to fill the in-degrees of vertices. So we are having a list of size v, and this list, each cell of this list is also containing list. Right. So here the outer for loop will go till v, and the inner for loop will run for these lists present at the cells. And inner loops individually will not go till e, but the total number of elements in all these lists present at the cells will be equal to e. We will be having elements equal to number of edges. And as we go through each element, at the end of the outer for loop, we would have traversed e number of elements. So this makes a total of v plus e. So we have the complexity equal to order of v plus e. Now let's talk about the space complexity. Here we are going to consider the auxiliary space, that is the temporary space allocated by your algorithm to solve the problem with respect to input size. So the space complexity will be order of v, where v is the number of vertices, because we need a queue of size v to store the vertices of graph, right? So the space complexity is order of v, auxiliary space. Hey guys, welcome back. In this lecture, we are going to talk about how we can solve problems that ask for maximum flow in the network. And a very famous and well-known algorithm to solve such problems is Ford-Fulkerson. But before starting with Ford-Fulkerson, let's talk about max flow. Max flow, as the name suggests, is defined as the maximum amount of flow that the network can allow to flow from source to sink. So the prompt is we're given this graph, this network flow graph or this flow network, and we have to maximize the flow through this graph or in this network from source to sink. So we're gonna go step by step, but there are a few basic observations to be made. See this graph? Here, to go from source to sink, or we can say from S to T, there are paths. One of them is S to A to B, and B to T, right? So if we're passing the fluid through this path, how much will we be able to transfer? We can pass 3 units of water or 3 units of any XYZ fluid from S to A, right? But we can only take 2 units further to the next pipe, which is AB, because the capacity of this edge AB is 2. And then there comes the third edge, which is BT, having capacity 3. But again, as we will be having only 2 units coming from AB, we would only be able to pass 2 units from this edge BT as well. So the thing is, the amount of fluid, or you can term it flow, in this path or in any path from source to sink is limited by the bottleneck capacity of that path. Here in this path that we discussed, that we have taken from source to sink, the bottleneck capacity is 2. So we cannot transfer more than that through this path. So this was the first path that we selected. If we are selecting this path, that means we are passing 2 units of water through this path towards the sink T. So now we're gonna write this flow across the respective edge along with the capacity. So if you see this edge SA, the capacity of this edge is 3 and the flow across it, the current flow across it is 2. So there's still 1 unit of water that can be sent through this edge SA. And this remaining amount or this remaining space for 1 unit, we term it as residual capacity. So residual capacity for SA is 1 and for this edge AB is 0, as the current flow is 2 and the capacity of this edge AB is also 2. And now this edge BT, the capacity is 3 and the flow is 2, so it can allow 1 more unit of water through it. So this was one path. We can choose more. There's another path right here. It is S to C, C to D, and D to T. Again, the minimum capacity of this path, or what we call the bottleneck capacity, is 2. So this path can also take 2 units of water to the sink. So we chose 2 paths, S to A to B, B to T, and the second one, S to C, C to D, and D to D. So we are getting 2 units to sink through the first path and 2 more units through the second path. That makes a total of 4 units to the sink. But is this the maximum that we can get to the sink? Yes, this is the maximum flow that we can achieve in this network. So this looks quite straight, right? But just wait for a minute. Let's reset this graph back to the original network where we don't have any flow going through any of the edges. Now let's say we pick this path. Or let's say our algorithm finds this path first and traverses it first. So from source to C, C to A to B, and then B to sink. I can pick this one, right? Because this is a valid path too. So if I go like this, the bottleneck capacity for this path we find is 2. So let's pass 2 units from this path. So this path needed 2 units from source to sink. Now let's find more paths. So to increase the flow we are getting at the sink, right? So is there any path? What if we try to go like this? From S to A to B, and then B to T. So see here this edge AB. is already filled up to its capacity. So if we try to push water from S to A, then we won't be able to carry it forward to the next edge. So we will be blocked right at this edge, right at this vertex A. Now, if we try to find some other path, which can only be possible if we go from S to C. But again, see this edge S to C. The capacity of this edge is 2 and the current flow is also 2. There's no space left for more water. So we can't push more water from source to C. Again, we're blocked here. So if we first pick this path, S to C, C to A to B, and B to T, the max flow, should not term it max flow, the flow that we are getting in this network from source to sink is 2. But this is not the max possible flow through the network. We saw it a few minutes ago that the max possible flow through this network is 4. So finding a forward path from source to sink in this original graph may not always work. And here comes the concept of residual graphs. Recursion worked with residual graph to find the paths from source to sink rather than finding paths directly in original network. But how we gonna get benefited by residual graph? You'll get in a minute. Residual graph, as its name implies, is something that has residual capacities. Okay, so to create a residual graph, there are two kinds of edges that we draw: edge with its residual capacity and edge with its shrinking capacity. So let's say this is the network whose residual graph we are going to draw here. So this network is the one we got when we were getting a max flow of 4 by selecting two paths, one from S to A to B, B to T, and the other one from S to C, C to D, D to T, right? So see this graph. To draw its residual graph, first we take all the vertices that we have in this original graph. Now let's draw the edges. Let's start with SA. See, in original graph, the flow in this edge is 2 and the capacity is 3. So this edge is capable of passing one more unit of water from S to A. So its residual capacity is 1. Now comes shrinking capacity. This edge, is having 2 units flowing through it, but this current flow can also be shrinked back till 0 if required. So this vertex A can say no to the source for this flow or for a part of this flow. It's a possibility. So if those units can add more value to some other path in network, we can undo the flow. So we can undo 2 units from A to S. Or we can say the flow can be shrunk back from 2 to 0. This is the way how we show it. 2 units back to source from A. So residual graph comes with the concept of shrinking the flow through edges, which indeed is important. Now let's take the next set of vertices, AB. The current flow across AB, edge AB is 2 and the capacity of this edge AB is also 2. So the residual capacity or remaining capacity is 0. We have no space to increase the flow further. That's why no forward edge. We're not going to draw any forward edge. We can only undo 2 units from B to A. Now let's take next set, which is BT. Current flow across BT is 2, but capacity is 3. So remaining or residual capacity is 1. So it can pass through one more unit. And it can undo its current flow by 2. Now let's take SC. It's not having any residual capacity. It can only undo 2 units flowing through it. So only a backward edge. Next is CD. We can increase current flow by 1 and we can shrink it by 2. So forward edge with 1 and a backward edge with 2. Now this one DT, no residual capacity, but we can shrink it by 2. Now the remaining 3 edges, the capacity and residual capacity both are same for these edges. As the current is 0, current flow is 0 for all of them. So they can allow water equal to their capacities. So we're gonna draw them just like they are in the original graph. So this is the residual graph. After drawing this residual graph, now we can shift back to the greedy way where we now look for the forward paths from source to sink. It does not matter whether the edge the path is covering is one for residual capacity or for shrinking capacity, but it must contribute to make a complete forward path from source to sink. And we call this path an augmenting path. So see this residual graph. Do we have any augmenting path from source to sink? Consider only forward path. We can't include edges going backwards, okay? You'll find no forward or augmenting path from source to sink, which means the current flow through the complete network is already at max. Now let's compare it with the second case where the path we selected was S to C, C to A to B, and B to T. So let's draw the residual graph for this case as well, just to make the concepts clear. So here let's take the vertices and now let's start with SA. The capacity is 3 and currently there's no flow across this edge, so the residual capacity is also 3. And now the next edge, next set of vertices is AB, where we are having capacity equal to 2 and the residual capacity is 0 as it is already filled by 2 units of water. So we can only undo 2 units from B to A. Now BT, where there's space for one more unit of water from B to T, and we can undo 2 units from T to B. Now next is SC, where we have no space for more water, so we can only undo 2 units. Now CD, where there's no flow, currently there's no flow, so the residual capacity is equal to the capacity. And the same is true for DT, the residual capacity is 2. And now next edge, CA, see this edge, there is space for one more unit from C to A, so residual capacity is 1 and we can shrink back the flow by 2. Now the other two edges, they're not used, there's no flow across them, so let's draw them as they are. So this is the residual graph that we're getting. Now again look for the forward path, or you can say for the augmenting path. There is one from S to A to C, C to D, D to B, and B to T. This path is the proof that we're not getting the max flow at the sink yet. There are possibilities to increase the flow at sink. So as we got this path now, let's look for the bottleneck capacity. Bottleneck capacity for this path is 1. We have it with the edge BT, right? So we're gonna increase the flow by 1 in this path. Now look at the original network. This is the path. In this, SA is now gonna have a flow of 1. And now comes AC, it's a backward edge, and the edge that we selected in the residual graph was meant for shrinking the current flow, right? So here we're gonna shrink the current flow by 1. So actually we're gonna eliminate 1 from the current flow. That's why now the flow through this edge will be reduced to 1 from 2. Now let's fill 1 in CD, 1 in BD, and BD as well. So with this, BD is now completely filled. So again, have a look add the updated residual graph. This is the updated residual graph. So let's see again if we still have any augmenting path. So yes, we do have. It's from S to A to C, C to D, and D to T. So let's increase the flow in original network. Now see here, the two units that are reaching at C from source are getting distributed among CA and CD. But after we increase the flow in this path, in this augmenting path that we selected, what we're gonna get? Let's see. So SA, we're currently having flow of 1. Now it will be having a flow of 2 units. And now AC, which is a backward edge. So again, we're gonna eliminate 1 from this edge. And now CD, here again, we're gonna increase the flow by 1, and DT, where the current flow will be 1. So this is the path, and this is the current flow across this path. Now see this edge SC. Here we are getting 2 units. These 2 units were previously getting distributed among CA and CD. Now CD is getting both the units. Remember, I said earlier that we reduce the flow from one edge to adjust it to some other edge. That's what is happening here. If 2 units reach to C, they must leave C towards the other vertices. And that's also what the residual graph takes care of. And that is what shrinking the flow is all about. So in residual graph, no matter what the path you choose, it won't block other existing paths, because here we are having the concept of shrinking the already running flow. So now we are having 4 as the flow at the sink, which is indeed the maximum flow. So now if we create the updated residual network for this network, we won't find any augmenting path. So this was the core part of Ford Fulkerson. Now let's see how we actually going to implement this. We are not going to move back and forth between the original network and residual network. Instead, from the beginning, we only going to stick to the residual graph. So this is the original network. Now we're going to convert it to residual graph, and it's going to be very easy, as initially there will be no flow in the network. That's why residual capacity for all the edges will be equal to the actual capacity of the edges. And again, as there's no flow in the network, we cannot undo anything, right? So the shrinking capacities will be 0 for all the edges. So this is the residual graph. This is the structure or graph with which we are going to start our implementation. And now we're gonna start from source to reach to the sink. Basically, we are going to find out the augmenting path. And for that, we're gonna need a map kind of structure. And we're gonna call it parent mapping, where we can store key values. Basically, this parent mapping is the one which is gonna help us in constructing the augmenting path. And now comes how we're gonna go over these vertices, or how we're gonna traverse this network. So we can either go with DFS or we can go with BFS. It's up to us. So here we're gonna go with BFS. So for that, we will be needing a queue. We're gonna push current vertex in this queue, and we're gonna take a visited set. It's gonna keep track of all the visited vertices while searching for the augmenting path in the network, so that we don't include the same vertex again in the path. Okay, so let's start with S. Let's add S in this queue and to the visited set as well, as we're visiting it. And now from here, loop starts. Until the queue is filled, we pull items from the queue, or you can say we pull vertices from the queue one after the other, and we start finding the forward edges from that vertex in the network till we reach to the sink. Okay, so there are 2 things to be taken care of while selecting the edges. First is The edge must be having value greater than 0. And the second constraint is that the edge must not be already visited. So it must not be already there in the visited set. That's it. So S is having two edges that we can select. One is from S to A and the other one is from S to C. And remember, we only consider the outgoing edges, okay? So now we pull S from the Q, and at the same time we add the connected vertices from S to this Q that we just selected. So we selected A and C, so we add A and C to the Q, and also to the visited set as we are visiting them, and now to this parent mapping along with the mapping. So this says that we came to A through S, and we do same for the other vertex, which is C. We came to C through S, that's why it is C:S. C is the key and the value for C is S. So now we're done for S, and now we select the next vertex that we have in the queue. So next vertex that we have in the queue is A. So now we're gonna look for the forward edges going outwards from this A to the other vertices having value greater than 0 and which are all not already visited. So see, there are three edges going outwards from these are AS, AC, and AB. But as S and C are already visited, and also these edges are having value 0, so we are not going to select them. But this edge, AB, is having a capacity 2, so we're going to select this vertex B while we pull A from the queue. And let's put B in visited set as well. And now let's put it in the parent mapping along with the mapping as we came to B through A. Now the next edge that we have in Q is C. So C is also having CA, CB, and CD, these three edges, but we can only consider this last edge CD as it's having a capacity greater than 0 and it's not already visited. A and B are already visited, so they are not in the game. So let's select D while we pull C from the queue. Let's put D in visited set and also in parent mapping. Now pull B from the queue, and while we pull B, we gonna put the vertices, the connected vertices from it. So the edges that are going outwards from B are BT and BD and BC and BA. But A is already visited, C is already visited, D is already visited. We are left with T, which is sync, and here the loop gonna stop. So while we pop B from the queue, we add sync vertex, which is T, into the queue. And here we stop and we add this mapping to parent mapping saying we came to T through B. So now this parent mapping is going to help us to construct the augmenting path. We start from sync and then we go all the way to source to find out the augmenting path. So we reached to T through B, and then we came to B through A, and we came to A through S. So this gives us the augmenting path. Now this path is from sync to source. Now we reverse it to get it from source to sync. Now the next step is to get the bottleneck capacity. The minimum capacity that this path is having is 2. So we are going to increase the flow by 2 in this path. So we are going to set 2 as the current flow for this path and also as the max flow for the complete network for now. As this is residual graph and we are increasing the flow by 2 in the path, so after increasing the flow, all the shrinking capacities of this path will now have 2 units of water that they can undo, right? And all the residual capacities will decrease by 2 as we have consumed space for 2 units. And that's how we're going to update these values. So we go over this augmenting path, and for all the forward edges, we eliminate the current flow from the residual capacity, and for all the backward edges, we add the current flow in the shrinking capacity. And that's how we get all the updated edge values, and then we repeat this complete process until there is any augmenting path present in this network. And this max capacity, this max flow, this variable gets updated each time we increase the flow in the augmenting path that we get in this process. So we keep adding up the flow for each path in max flow, and at the end this will be having the maximum flow in the network stored in it. So this is how everything is going to work. Let's make it more clear with code. Hey guys, welcome back. So here in this lecture we are going to write code for Fulkerson, and as we are going to perform for Fulkerson using breadth first search, this algorithm or the solution that we are going to implement here is called Edmonds-Karp algorithm. For Fulkerson is more than an algorithm, it's a general scheme with several different implementations. So if we are implementing it with BFS, then it's also Edmonds-Karp algorithm. So this is the given flow network. We need to find out the max possible flow through this network. So let's create get max flow function. Let's pass graph and the source and sink. Sink will be, for in our case, sink is the length of the graph minus 1, as it is present at the last index, or it's the last vertex in the graph. Now here in this get max flow as a parameter, let's change I and j to start and end, or we must take here source and sink. So here source and sink. The first thing that we need to do here inside this get max flow is to create a residual graph. As we know, initially the residual graph is same as the original graph, right? So let's create residual graph, new int array, and the size of the array will also be equal to the main network, the original network. So rows will be equal to graph.length, and now columns will be equal to graph0.length. That's it. Now, after creating this residual graph, now let's copy data from original network into this residual graph. So let's take a for loop starting from 0 and going all the way to the length of graph. Now let's increment I, and now here inside this for loop, take another for loop for columns, which will start from 0 and will go all the way to graph 0.length and increment the j. And now simply copy each element or take each element and place it into this residual graph at ij. So residual graph ij will be equal to graph ij, right? That's it. So this will copy the data from this original network to this residual network. Now what's next? So after creating the residual graph, we have to start finding augmenting paths. But before we start finding the augmenting paths, we need a map having integer keys and integer values, and we're going to call it path mapping, where we will store the vertex coming in the path along with its mapping. So let's call it parent mapping. It's a hash map, so new hash map. Okay, and we also be needing a list to hold all the augmenting paths. So this is again a list of integer, list of integer, because this is gonna have all the augmenting paths that we find in network in it. So this is augmenting paths, and this is a list. array list. Now we're going to say that while there is any augmenting path present in the network, so get augmenting path, and this is a method which gonna return us a boolean, and it's gonna take the residual graph. And here inside for this function we will be needing pattern mapping, we will be needing source, and we will be needing sync. So until it returns true, we are going to do some stuff here. So let's implement this get augmenting path method to find out the augmenting path from the network. So let's create it, and here to find augmenting path we need a queue, as we are going with BFS, and we will be needing a visited set so that we don't repeat the vertices, right? So let's take set visited, it's a new hash set. And now let's take a queue holding integer, let's call it q, and this is new linked list. So we are going to start from source, right? So first we will add the source to the queue and also to the visited set. Let's add source that we're getting as input argument to this get augmenting path method into queue and visited set. So first let's add it to the queue, add source, and now also to visited set, as we don't want to visit it again, right? So add source. Now again we need a while loop. So here we are going to take a while loop, and we are going to say run this loop until the queue is not empty. So until there is any vertex present in the queue, we are going to pull it from the queue. So queue.pull, and let's call this vertex u, pull, and now here let's call it u, and now we need a for loop to go through every vertex present in the network. So here we take a for loop which starts from 0 and cover all the vertices, so it will go till the length of the residual graph. Now let's increment weight. Now here we are going to start selecting the vertices, but there are two constraints that we must consider while we select any edge or any vertex, right? And these constraints are, first is that the vertex must not be already visited. So the visited set must not be already having it, okay? So visited must not contain v. And the second constraint is that the edge must be having value greater than 0. So residual graph, let's copy this, and here residual graph edges UV. So U is for the first call, for the first iteration, U is the source, and V can be any other vertex. So for this edge, the value of this edge must be greater than 0. So if we successfully come inside this if, then we can add the vertex in the parent mapping, right? So let's put V in this parent mapping. We say that we came to this vertex V through U. So the value at this key will be U. Key is the vertex itself, and the value is the vertex from where we came here at V. And we also add the vertex to the queue and to the visited set as well, so that we don't visit it again. Now comes when to stop. When we reach to the sync, we must stop, right? So if v is sync, if we have reached to the sink, then we should stop here. So this function get augmenting path is going to return a boolean. So let's take it here outside the while loop. Let's call it got the path, and set it to false initially, and here when we reach to the sink we are setting it true. Now we can break this loop. So, and finally we can return this boolean value here, got the path, from here. So here, until we keep getting true, that is until we keep getting augmenting path, we are going to do some stuff inside this while. The stuff includes finding out the bottleneck capacity for the current path and setting it as flow for that path. So initially we're going to take max value for it, and we also need to construct the augmenting path from the parent mapping object, right? So for that we're going to take a list to store the augmenting path that we're going to construct from parent mapping. So this is array list. And now let's start constructing the path. So we start from T in the parent mapping, right? And we go towards the source. So let's take a variable. Um, we are going to call this variable T, and we're gonna assign sync to it, and then from here we will start towards S. Or maybe we should call it something else. Let's call it V, and here inside here we are going to say until v is not equal to source, do the stuff inside written inside this while. So inside here let's add the vertices to the aug path variable and get the value stored for that vertex where we need to jump next. So after adding it, let's get the value. We're going to call this value u from parent mapping, which is present at v, right? And along with constructing the path, here we also gonna update the bottleneck capacity or the flow for the current path. So we need the smallest capacity as the flow, right? So if the current capacity for which we are running this while loop, if this capacity or the capacity of this current edge is smaller than the flow that is present in this variable, then we are going to update the value of flow because we need the smaller one, right? So flow is equals to this new capacity. So this is how we are selecting the bottleneck capacity, and this will be the flow in the current selected path. And now after this, jump to u. So we are going to update the value of v with u so that this while again runs with the next value. So this while will do its job except to add the source in the aug path because it will stop right at the source. So we're gonna add source to this path after this while loop. Now the path is complete, but it's from sink to source, right? So we must reverse it to get it from source to sink. So here we are going to use collections utility, and here we are going to reverse this aug path. Now after getting this augmenting path, we are going to add it to the list of having all the augmenting paths in the network. So here add this augmenting path to this augmenting paths list. Now comes the max flow for the network. Each time we initiate flow in any path, we're going to add it to the max flow. So that at the end, we will actually be having the maximum flow in this variable that we are going to create here. We're going to call it max flow. So initially, let's set it to 0. And here, each time we get a flow or each time we initiate flow in any path, we're going to add this flow into this max flow variable. So at the end of this while, we will be having the maximum flow for the complete network in this variable. Now comes updating the capacities. Again, we're going to use parent mapping object for that. So we're going to start with sync, and we will run the while loop until we get to the source. And here inside this while, let's get the value present at v from parent mapping, and again we're going to call it u. And now, okay, and now for all the forward edges, or you can say all the edges having, for all the edges having residual capacities, we're going to decrease their capacities by the current flow. And for all the edges with shrinking capacities, or for all the backward edges, we're going to increase their value. So these are the backward edges. These are from sink to source. These are the edges when we are going from sink to source. And this residual graph UV, having edge UV, is a forward edge. So here we are going to decrement the flow, and in backward edge, which will be from V to U, so here we're going to say residual graph V to U, increase their capacities by adding up the flow in their current capacities. And then again, these are the edges having residual capacities. These are the forward edges, and these are the backward edges having shrinking capacities. And again, at the end of this while, update the value of v with u so that it can run for the next value. So we did everything from finding the augmenting path to setting up the flow to filling the augmenting paths list to updating the max flow to updating the capacity of edges. Now after this while, we are going to print all the augmenting paths that we're having in this augmenting paths list. So let's create this method, print augmenting paths, and here inside this print augmenting paths, let's run loops. Let's use for each on augmenting paths. So let's say augmenting paths dot for each. So for each path present in augmenting paths, we are going to implement something. We are going to basically print something from this path. Again, a for each for all the elements that this path is having, this individual path is having. So for each vertex or for each element present in this path, print that out on the console. So here e plus some space, and that's it. So this was print augmenting paths method, and after printing the augmenting path, here outside this while, we are going to return this max flow, as this method is going to return max flow. Oh, we are doing it inside the while, so do it here. Now let's save this file. So here we are calling getMaxFlow, and this getMaxFlow is going to return us the maximum flow in this network. So here let's sys out at system.out.println, and we are getting error here. This is because getMaxFlow is not returning anything. It must return int. Here let's say the max possible flow is Okay, now let's run this. The max possible flow is 4, but these are the augmenting paths. This output needs some formatting. Let's do a little formatting here while we print the augmenting paths. We don't need to change line while printing one path and change the line after printing the one path, the complete path. So let's run this. So these are the augmenting paths that we're getting. We're getting this one twice. We must be doing something wrong. So here this while closes here and we're printing the augmenting paths inside the while. We must not do this because after the completion of while we'll be having all the paths in this augmenting paths list. So now let's run this. So see, these are the two paths that the two forward paths that we are having in the network that we have selected, and the max possible flow for the network is 4.